event in my life. And in hindsight, there's no question that had I gone straight to a postdoc from my PhD in theoretical physics, my training would have been so narrow that I would not have made a really well-rounded biologist. And so it's invaluable, not only the courses I took, but the various rotations. So I owe the place a great debt of gratitude, and it's a real pleasure to be back. So I've left this slide on throughout this time, partly because these are the people who actually did the work. I mean, sometimes these days when I get asked at a party what I do, I say I'm in marketing. And because I haven't done lab work for probably about 6 or 7 years. And these are people who took real risks, because I already had tenure when I started working on the whole ribosome. But these guys were grad students and postdocs with very short-term horizons, and yet they took on the challenges. So I owe them a great debt of gratitude, and I'll mention some of them individually as I go along. So the problem of the ribosome is really how to take genetic information, which is encoded in DNA, and which is converted into messenger RNA, which is a working copy of the gene, and from there to get to a protein. And the first step in this process was first the prediction and then the discovery of this molecule, tRNA, which is the central player in translation, which, as you know, has the anticodon at one end that base pairs with the triplet codon and brings along the amino acid at its other end. Now, initially when Crick proposed this, he actually envisaged a very short, maybe a trinucleotide adapter that would slide along a nucleic acid template. He didn't even know whether it was DNA or RNA. And he just thought it would somehow spontaneously zip up a protein chain. And of course, that's not what happens. And I used to be a big fan of Colombo when I was, in the US. And in Colombo, you were told the answer before you were shown how it all was solved. And so in that way, I'm going to show you a current view of translation, and then tell you a little bit of the history of how we got from knowing nothing about it to eventually the atomic structures and then what we knew. So here's a little movie of translation which will kind of lay the groundwork for what I'm going to tell you later. So here's messenger RNA, and this object is the 30S subunit, which with the help of 3 protein factors brings along an initiator tRNA, which is a special tRNA that brings in the initiator methionine. And this is followed by the joining of the 50S subunit, and the initiation factors leave. The last one to leave is probably IF2, although IF1 may leave at about the same time. And IF2 is a GTPase, and after GTP hydrolysis, it leaves the complex. And now the ribosome is at the beginning of the elongation cycle. So you have the initiator tRNA with the first amino acid, and the next tRNA is brought along by an initiation factor called EFTU, which hydrolyzes GTP, and then the tRNA swings into the peptidyltransferase center, where a peptide bond is formed between the first and second amino acid. Then the tRNAs have to move with respect to the ribosome, a process called translocation. And so they move first with respect to the 50S, and then with the help of another factor, EFG, move with respect to the 30S. And when they move, the mRNA is also translocated at the same time. So that brings in the next codon into the right position to receive the next tRNA, which is brought along by another EFTU complex. And then the first tRNA at some point dissociates because it's deacylated and eventually leaves the ribosome. And this process happens at the rate of 20 residues per second. But if I were to show you that at real time, it would just be a blur. And the nascent peptide emerges through a tunnel in the 50S and folds, often with the help of chaperones and sometimes spontaneously. And the process keeps continuing until the ribosome reaches a stop codon. And when it reaches a stop codon, essentially what has to happen is that a special factor called a class 1 release factor has to bind to the ribosome, recognize the stop codon, and in response cleave the nascent peptide from the ribosome, where the folded protein then effectively leaves the ribosome. And finally, a factor called ribosome recycling factor, along with EFG, comes and recognizes that complex and splits the ribosome apart so that the whole process can start over again. Now, this is a process in bacteria, and in eukaryotes, some aspects like initiation and aspects of termination are far more complex than they are in bacteria. So there's quite a lot we don't understand. And even in the bacterial case, we don't understand initiation and translocation very well. So how did we get to this picture from the beginning? So when molecular biologists were formulating figured out the triplet code and tRNA and so on, cell biologists like George Palade showed that newly synthesized proteins localized in these blobs on the endoplasmic reticulum. And these blobs were isolated and were shown to be these particles which are about 250 angstroms in diameter, and they all consisted of a large and a small subunit. And originally they were called the ribonucleoprotein particles of the microsomal fraction. But if you tried saying this every time you wanted to refer to it, it was rather a mouthful. And so Howard Dintzes, who's at Johns Hopkins, at a meeting in the late 50s said, why don't we just call it the ribosome? And that's the name that's stuck ever since. Now, many of you know Jim Watson for a variety of reasons. We all know him because with Francis Crick, he discovered the double helical structure of DNA. But of course, we also know him for his rather frank views on various things like race and gender and eugenics and you name it. But one thing that he's not as well known for as he should be is that his lab pioneered a lot of the early work on ribosome biochemistry. And the reason we don't know this is very interesting. Watson was very influenced by the Cambridge tradition pioneered by Rutherford and Bragg and then propagated by Max Perutz, that you don't put your name on a paper unless you've done at least a significant portion of the work or contributed significantly to the ideas. And so because he let his graduate students, Joan Stites was one of them, Ray Jesslin, and Alfred Tessier, Nomura. So all these people worked rather independently in his lab, so they published on their own, okay? But nevertheless, his lab is what, and Watson contributed a lot of ideas to the ribosome. And in 2001, there was a Cold Spring Harbor symposium to celebrate the atomic structures. And here he is talking about the early days.
This symposium is on the ribosome, a little round object which doesn't contain DNA, but contains RNA. And I started studying it with Alfred Tessier, who's halfway here at Harvard, and it was spring 1957. And we knew there was involved in how proteins are made because the newly made proteins were attached to it. So we thought if we solved the structure of proteins as a ribosome, we would know how proteins are made. And that was a big problem, because you had to somehow go from DNA to the information, and DNA to the information and protein. And there was this particle which we thought was round and spherical, and hopefully only contained one sort of protein molecule. If it did, then maybe it would not be easy to solve, but it would be solvable. So over the next couple of years, after I assembled some people, first the protein chemist who looked at it and said, I'm leaving. And because it wasn't simple. And then a protein chemist actually said, gee, there are at least 30 proteins in this little round thing. And so automatically I knew we'd never know its structure.
So of course Jim was right in the sense that in the late 50s it would have been impossible to determine the structure of the ribosome. But fortunately, his lab and many other labs worldwide didn't just sit around waiting for the technology. They started attacking the problem from various angles. And I just want to take you through some of the highlights. I mean, the first thing you had to do with the ribosome is ask, what is the ribosome made of? And Jim's original estimate was an underestimate. There are actually about 50 proteins in bacterial ribosomes, and even more, about 50% more in eukaryotic ribosomes. And they all consist of two subunits which assemble to form the entire ribosome. And they're about 2/3 RNA in most kingdoms, except in certain mitochondria, like mammalian mitochondria. So what did people do next? Well, once the components were in place, Nomura wanted to ask, could you purify the components and put this back together? And so this led to the reconstitution of the ribosome, and that paved the way for a large number of biochemical studies, including assembly, which led to this early assembly map. And I should point out that assembly is a very complex process which is still being actively studied, including by Jamie, who's in the audience, Jamie Williamson from Scripps. So this led to the assembly map of the ribosome from Nomura, and then others did it on the 50S. And then people started sequencing ribosomal proteins using the old-fashioned peptide sequencing method. And then Sanger's group sequenced 5S RNA, and then 16S and 23S RNA were sequenced. I mean, the first really accurate sequences came from Harry Noller's lab. And a comparison of RNA sequences as well as biochemical studies using crosslinkers led to an understanding of which parts of RNA were base paired, and that led to these secondary structure diagrams. This is of 16S RNA, and again, this was a major landmark. Now, while people were doing these sort of biochemical studies, people were doing three-dimensional studies on trying to get at structural information, and the first kind of structural information was on negatively stained electron micrographs of ribosomes. And this is a picture from Jim Lake's group. And it's astonishingly close to what the 70S actually looks like, I mean, within the resolution of that technique. And you have to realize this three-dimensional reconstruction was really done in Jim Lake's head. You know, it was not done by computation. The first evidence that ribosomes were identical particles and might actually be crystallizable came from the observation that they formed two-dimensional crystalline sheets. And Nigel Unwin, a colleague of mine at the LMB, began a systematic study using these 2D sheets of ribosomes, and in fact was the first person to show the exit tunnel that I showed you in that movie. At about this time, people wanted to locate where the proteins were on the ribosome. And this was done using a couple of techniques. Neutron scattering, a technique that I worked on as a postdoc in Peter Moore's lab. I like to joke that 1/3 of these balls are mine. And then there's a technique called immune electron microscopy, where antibodies were formed to individual ribosomal proteins and then localized using electron microscopy. Subsequently, there was a phase when people started solving the structures of individual ribosomal proteins. And Steve White and I collaborated on a number of these proteins. And then using these proteins and site-directed cleavage, as well as chemical footprinting techniques, primarily Harry Noller's lab, as well as Richard Brimacombe's lab, identified which proteins interacted with which regions of ribosomal RNA. And at about this time, small RNA structures began to be solved by NMR, and a number of these were solved as well. So in the mid-90s, another very important technique began to take off, and that was the technique of single particle reconstruction using electron microscopy, initially negative stain, but then using cryo-EM. And this led to much more detailed images of the ribosome. And of course, at the time, it was at about 20 angstroms or so resolution, primarily from Joachim Frank's lab, as well as Van Heel's lab. And so because even in the mid-90s, it was not clear that you could solve the crystal structure of the entire ribosome, people started modeling using the fact that they knew the approximate location of the proteins, they knew which parts of ribosomal RNA was double helical, and they also knew which proteins interacted with which parts of RNA. So it was sort of like solving some sort of puzzle, and they tried to
we will have a pause now, and we will continue this one later. Thank you. We will now move on to the next session, and we will continue this one later. Ladies and gentlemen, please join me in thanking Professor Venki Ramakrishnan for his invaluable speech, for addressing the audience, covering all the aspects of science, technology, society, setting the tune for this symposium, that is Science Beyond Boundary. Your lecture is highly stimulating and inspiring and motivating. And in fact, he has sent an email message which has to be read out. So, okay, all right. So I'll just read out. I am pleased to send my greetings to the organizers, participants, and awardees of the International Symposium, Science Beyond Boundary, Invention, Discovery, Innovation, and Society, RASAYAN-23. Organized by the Department of Chemistry, Saurashtra University, Rajkot, and Chirantan Sanstha CRS during 8th to 10th July 2026. Progress in science depends on curiosity, rigorous inquiry, and the open exchange of ideas. Meetings such as this bring researchers together, encourage new collaborations, and help translate scientific discoveries into broader societal benefit. I extend my congratulations to all the awardees for their contributions to science and technology, and I wish RASAYAN-23 every success. Dr. Venki Ramakrishnan. Thank you very much, sir, again for being with us and sending your impactful message to us. The Society CRS would like to honor you now with the medal, memento, certificate, and Auditorium. So I invite the Secretary CRS, Professor C.V. Alagmagad, to join, and also Professor Kunt also kindly come over. Professor Bua, please come. Professor Kakodkar, and also Honorable Vice Chancellor, sir, Professor Joshi. So this has to be displayed so that he will see all this. Thank you all once again. Our next award lecture will be delivered by Padma Shri, Padma Bhushan and Padma Vibhushan, Dr. Anil Kakotkarji. Sir, the floor is yours. So I welcome you and start your lecture.
I can start? No? Okay. Good morning to all of you. Distinguished colleagues and members from Chirantan Sanstha as well as Saurashtra University. Let me first of all express my gratitude for this invitation to come and speak here. I have a little dilemma, and the dilemma is I'm not a chemist, as you all know. But then this particular meeting has a much broader scope, almost straddling science and society. So I thought maybe that's a justification for me to come here and speak. So what I'm going to do is to talk about a particular energy challenge that is in front of our country and how thorium, that has been my passion throughout my professional life, can address that particular challenge. So can we have the, yeah. Now, as you all know, the atomic energy program in the country has been, it's an indigenous program, it's a self-reliant program, and country has achieved self-reliance despite technology embargoes. Achieving self-reliance by itself is very important, but when there are constraints in making progress towards self-reliance and you overcome those constraints, I think you do get a special strength for the country. Okay. Can you go back to the previous? Yeah. So this program has been going on almost since the days of independence. Dr. Bhabha, who is the founder of India's atomic energy program, he recognized on one side the role nuclear energy would be required to play, and also he recognized that there is not enough uranium in the country, and so that's how the three-stage program came into existence. And of course, everything has to begin with uranium. So we have mastered the first stage, essentially comprising of pressurized heavy water reactors. We have also mastered the second stage, and you must have heard the 500 megawatt prototype fast breeder reactor just started the chain reaction some weeks back. The next challenge is towards thorium. And while we have achieved self-reliance in spite of constraints, fact remains that what we have done in first stage and second stage is something which other countries had done, we have also done on our own strength. When it comes to the third stage, thorium stage, there is actually no parallel anywhere else. And so the challenge before the country is to get into that technology despite the fact that there is no parallel anywhere else. Now, of course, they have started emerging, but to me, we should not lose on that opportunity. Here is an opportunity for India to be a front runner on a key technology which will be very important for the country as a whole. And so, if I had to sum up the atomic energy program, I think we have done extremely well in terms of technologies. Countries' expectations in terms of delivery of electricity through nuclear means are very high, and perhaps we are falling short of it. And going forward, it's the kind of rapid scale-up of deployment of nuclear power on one side, and on the other side, development of new technologies going towards thorium. So that's the challenge as we have today. Next one. So let me start with this problem. What is the problem we have? And I think it's not sufficiently understood in my view. This correlation which you see on the slide, I'm sure you would have seen it many times over. This is simply a correlation between the status of development, quality of life of people, human development index, correlated with the per capita energy consumption. And on that graph, on the top of the figure, you would see blue triangles, which are essentially along a horizontal line at the top. These are all advanced countries. They are sitting at a human development index nearly the theoretical maximum. Maximum is 1, and these people are at around 0.95. So, we also have aspiration to be counted among them. We talk about Vikasit Bharat. We want to be a developed country. In the true sense, if you want to be counted as a developed country, then you should find a place around those blue triangles. Now, so at least on those blue triangles, we should be able to access minimum per capita energy consumption to be a developed country. Now that tells you where you want to go on per capita terms. Then you multiply the steady state population of India. You also make correction for the improved efficiency which will take place with the growth of technology, and you will end up in a number something like 28,000 terawatt hours per year. That is the energy India requires to be a developed country. Today we are consuming something like 10,600 odd terawatt hours. That's where we are. So that is the gap that we need to bridge. Now, what are the energy resources? mind you, we are now talking about net zero. We can't be allowing too much of carbon dioxide going into atmosphere. We are going through the clean energy transition. And in that clean energy transition, the one that naturally comes to mind is the renewable energy. Solar, wind, biomass, hydro, and the like. Now, if you really sum up the total renewable energy that we can find on our Indian landmass or Indian territory, that number is around 8,000 terawatt hours. Now, this is the maximum in my view. So, the only other source which will not emit carbon dioxide but provide you energy is nuclear. So, between 28,000 and what we can get by renewable energy, there is a large gap, 20,000 terawatt hours per year. And that is what we need to derive from nuclear. And in Indian context, because we don't have much of uranium, we have to be able to derive from thorium. And this is where I think there has to be adequate awareness in the country. You know, nuclear has become a buzzword, but people have not, in my view, understood the gravity of this situation. Next slide. So, in the new clean energy transition, the what are the sources? I said you have solar. Solar can produce heat, solar can produce electricity, but somehow in our country it's all heat. It's all electricity, very little heat. Wind can produce essentially electricity. Biomass can produce heat. Hydro can produce essentially electricity. Nuclear can produce heat as well as electricity, but we are all focused on producing electricity. Now on the demand side, the picture is quite different in that in the earlier time when we were, or even today we are dependent on fossil energy, the energy used to appear primarily as heat and then we used to convert it into many other forms. Now, a larger part of energy would first appear as electricity and then we'll have to convert it to whatever forms you require at the demand side. More particularly hydrogen, because the chemical energy, if you cannot make use of coal, then of course biomass can give you something, but hydrogen would become an important contributor, and that is what is going to be the transition. So it is not just making use of it's not just making use of available energy sources, but one has to also work on the energy transitions to make sure that this energy supply can be properly linked to the energy demand. And that itself is a lot of work. And I think scientific community, again, is a lot of work to be done to develop related technologies in each one of those areas. Can you go further? Now, in that context, in that background, now let us see the nuclear fuel. We are all talking about nuclear fuel is an abundant source of energy, but that is every atom of uranium or thorium. Of course, it has maybe million times or more energy compared to coal or other fossil molecule. But that is not the way we use nuclear energy today. Today, we can use only uranium, and essentially we use the small fissile content in uranium. Out of 1,000 parts, 7 parts are uranium-235. So that is all that can fission. Although the remaining part, the larger part, uranium-238, can be converted to plutonium, and which is fissile, and you can derive energy. And also thorium can be converted to another fissile element, uranium-233, and derive energy. But actually what is happening today is only the first part which I said. You use uranium, you use the 0.7% fissile content, produce energy, and most of the countries consider the uranium coming out after that much of energy generation as waste. So, of the 6 to 8 million tons of uranium that we have in the world, or 6 million tons of thorium that we have in the world, these are commercially viable quantities, otherwise the quantities are huge. Out of that, in India, we have 0.4 million tons of uranium, but of course it's a very, very lean ore, so, and there are constraints there. And of course we are endowed with this large quantities of thorium, and that's the basis of India's three-stage program. Now, there is this renaissance, nuclear renaissance, and everybody, many countries have said we will triple our nuclear generation. World Nuclear Association has said that by 2050 they expect the global nuclear generation to reach around 1400 gigawatts. Now, if you look at 1400 gigawatts, and you look at this once-through use of uranium, which is what is prevalent today, then, and if we start using uranium in a particular reactor, a reactor can easily run for 60 years or even longer. So let's say 60 years. So how much uranium you have to provide to support that capacity, and or how much of capacity can be set up using the total uranium that is there in the world. And that comes to only 550 to 750 gigawatts, way short of the expectation. And this is the uranium challenge which the world is going to experience. Of course, the answer is they will have to resort to recycle, because then the 93 parts of 1,000 in uranium, that also can be made to use of for production of energy, and then suddenly 3 orders of magnitude higher energy we get. But that today, with notable exceptions of India, France, Russia, most of the countries are not doing, because of fear of plutonium getting diverted to weapons, nuclear weapons, and more particularly for by people who have malevolent intentions. Now, this is the kind of fix the world is in. Now, on the other hand, if you start recycling thorium, then thorium fuel cycle has an inherent what is known as proliferation resistance. In the sense, uranium-233, of course you have to design the fuel cycle that way, but you can make sure that it is always accompanied by small trace quantities of uranium-232, and which has highly radioactive daughter products. And so while you can generate energy, but you can't divert it for weapons purposes. And if you organize things that way, then actually you have solved the problem of finding the adequate energy for the world. So this is what I have been kind of talking about, or you can say shouting about, that we must shift to thorium as fast as we can, because we can't afford to delay this shift. Because as we, the so-called powerful countries, so-called advanced countries, they will have enough uranium for themselves, and they will leave the developing countries to fend for themselves. And India, with all its technological capability, I think we must organize things based on our own interests and our own capabilities. So this is the key message that I want to leave with you. Next one. So the key is transition from uranium to thorium as a priority. Now, as I mentioned earlier, the global uranium market is currently experiencing a structural deficit as the demand from nuclear power growth driven by decarbonization goals outpaces the primary mine production, and that is the challenge we are. The intention behind opening international civil nuclear cooperation, I was involved in it right from beginning. There was a time when we were running literally hand to mouth in terms of uranium availability. There was a time when our capacity factor of our reactors had started dwindling down. And then, of course, we went through the whole international civil nuclear cooperation. But the intention behind that was to remove the hurdles in accessing uranium, but the priority for thorium was never to be compromised, but rather it should be speeded up. And that is what I am arguing right now. Now, as a part of the three-stage program, we have made progress. First stage is mastered, as I mentioned. Second stage, the reactor is started now. But large-scale thorium utilization through that mode, because fast reactor has to stabilize, you have to go through 2 or 3 more technology changes. So today's fast reactors are based on oxide fuel, plutonium, uranium oxide fuel. That has to change to metallic fuel to give you larger breeding ratio. And that means the whole technology, it has its own gestation period. Now all these things are important. But on the other hand, countries' power needs are staring at us. So I think it's important that we should find alternate ways of accelerating thorium deployment. And can you go to the next slide? So here is a proposal which I have been championing. The figure on the left hand side, the top figure, is the traditional 3-stage nuclear power program. Now, the figure at the bottom, all it says is you have in the earlier 3-stage program, we are talking about developing fast breeder reactors, because by breeding fissile material, you can enlarge the capacity where you can irradiate thorium. You want to irradiate thorium on large scale to produce uranium-233 and create fuel for meeting our energy needs. Now, with the new program, we are anyway going to deploy uranium, and we are talking about 100 gigawatt nuclear energy mission the government has announced. So 100 gigawatt nuclear energy, you have a platform ready. So you can as well irradiate thorium on this large PHWR capacity. And so that is what has been done, in the sense you can have in a PHWR, instead of natural uranium as a fuel, you can use thorium and enriched uranium as fuel, and then that will give you the capacity to produce uranium-233 as you produce energy in PHWRs. And that allows you to go forward in terms of building the energy source for the country. So the only change is you have the original 3-stage program. We continue to work on that. You dovetail the bottom part because you have large capacity of PHWRs. Yeah. So because you have large capacity of PHWRs, you can irradiate and produce that fuel and get on. And of course, you will require more fuel that will come. So the original 3-stage program will eventually start feeding into this new configuration, and you can get on with meeting our energy requirements. So that's the proposal which I have been advocating. The current program is written there on the right hand side of the figure. Next one. Next one. So this is that fuel bundle which has been designed. It looks exactly same as natural uranium bundle, but it will do that miracle which I have been talking about. Next one. And this has been qualified by irradiation testing, and it has gone to something like 6 or 7 times more burn up, the energy extracted per ton of uranium compared to the natural uranium. So it is not only designed but actually qualified. Next one. And it has a lot of advantages. It's not as if you spend money to do this. For that matter, you get a lot of economic advantages, you get safety advantages, you get, as I mentioned earlier, proliferation resistance. So it is it's an economically attractive proposition to do that to address our long-term energy security. Next one. So, the thing which I am arguing these days is to leapfrog to third stage by kind of bypassing the second stage and then bring that second stage into the equation as we go along. And I think that was the last slide. Next one. Yeah. So that is my simple proposition. I know this is not quite chemistry, but I must tell you that the new reactors that will be required, so normal reactors are a mechanical engineer's paradise. The solid fuel, complicated mechanisms and all. Thorium reactors are going to be what are known as the molten salt reactors, which are essentially chemistry-based design. So I think time is not very far off when you would get into nuclear reactors done the chemist way rather than the physicist or mechanical engineer's way. So maybe some of you may have interest in future. Thank you very much.
Thank you very much, sir, for your highly informative and kind of visionary lecture. And we are really, enriched by your expression and deliberation. And based upon your achievement, CRS would like to honor you with its highest award, the CRS Lifetime Achievement Award, which will be given to you during the award ceremony. But now, in fact, the organizers would like to felicitate you.
Both the chairs and organizers would join us to felicitate him, including Vice Chancellor.
By Dr. Harish C. Vashilia from the Surface Engineering Division of CSIR, National Aerospace Laboratories, Bangalore. Sir, the floor is yours.
Good morning. Check, check. Can you put my this one? Very good morning to all of you, distinguished delegates, invitees, the office bearers of CRS, students, and my dear colleagues. I thank CRS for this honor. I am humbled to be standing here today in front of you. Thank you once again. Today what I am going to do is that in next 20 to 25 minutes, I am going to take you through some of our research which we have been doing in the area of renewable energy. Like Professor Rajkot, I am also a physicist, but then I'll try to give you a glimpse of how the chemistry and physics can be married together to develop these kind of technologies. The outline of my talk is as follows. I will just dwell upon the solar energy as a sustainable energy solutions. The fossil fuels, they have been driving our industrial growth since 1760. Yeah, there is some problem. So basically what I will do is that I will touch upon the solar thermal technologies which Professor Rajkot was mentioning that in the country not much progress has been made. And then I will take you through some of the physics-based approaches to design these materials and technologies, and then subsequently to make the processes cost effective and their manufacturability. I will take you through some of our research in the area of zero-dimensional, one-dimensional and two-dimensional materials, and subsequently one of our technology which we have designed and developed out of the research and which has been commercialized very recently. So the fossil fuels, they are the driver of our industrial revolution and growth since 1760, and they create a large amount of air pollution as well as the greenhouse effect. In fact, as per the International Energy Agency report, in last year worldwide we contributed about 38 billion metric tons of carbon dioxide in our atmosphere. And as a result of that, in last 100 years, the average temperature of the earth has risen by 0.74 degrees Celsius. And that leads to extreme climate change. Right now we are facing the El Nino effect and other kind of climate changes which are encountered in all parts of the world. Now, solar energy is an ideal solution to address this pollution related issues apart from the nuclear energy. But if you see the statistics, still as on today, 60% of our energy needs are met by coal. The news is good in terms of the solar energy. We get about 5,000 trillion kilowatt hour of solar energy per year in the country throughout the year, and the DNI, that is the direct normal incidence of the solar radiation, is very, very high in the country. And a fraction of this, if you can harness, it will serve our energy needs in the country. As per International Energy Agency report, by 2050, the solar will constitute to about 34% of our energy needs, and this is being taken care under the National Solar Mission, which started sometime in 2010 and 2011. And of course, we need to develop a variety of newer technologies to make India net zero by 2070 as per the COP26 conference. So in the context of the solar energy, we have two technologies to convert the solar energy either in the form of heat or in the form of electricity. The first and foremost is, of course, the photovoltaic, wherein the photon is converted into electron, and then you can generate the electricity. But there is a problem. Even though we have a installed capacity of about 160 gigawatt as on today, the technology is not available in the country. But we are very fortunate that in next few years this is going to change, because of the fact that the government of India has launched a national semiconductor mission in 2021, and we will have in next few years the silicon foundry in the country itself. The efficiencies which we are talking about in the case of silicon technology is about 25 to 26%. The other technology is which Professor Rajkot spoke about was briefly the solar thermal, wherein the heat is converted the solar radiation is converted in the form of heat through these lattice vibrations, and then you can have either, if the temperatures are very high, you can have electricity or you can have the hot water. For this technology, the ecosystem is available in the country, and we can develop these technologies in the country very easily. The efficiency, if you see, from solar to thermal is about, say, 70%, but then the solar to electricity is about 30%, which is high compared to that of the silicon technology. Of course, it is a function of temperature, as I will discuss a little later. Now, to harness the solar energy, we need specialized surfaces. So we call them spectrally selective surfaces, meaning thereby their absorbance should be very high in the solar spectrum region, that is 0.3 to 2.5 micron, and their emittance should be very low in the infrared region, that is 2.5 to 30 micron, because the power losses are proportional to the temperature to the power 4. So if I take typical metal, wherein the reflectance are very high in the UV visible and NIR region, or if I take the semiconductor, the reflectance are very high in the infrared region. So if I want to convert these, either the metal or semiconductor or the insulator, we need to tailor their compositions. So that is what I'll just try to take you through, that how it can be done. So from this operational point of view, the solar absorber coatings are divided in three categories. The first is the low temperature, wherein the process temperature is about 100 degrees Celsius. It is used for hot water applications. Then the mid temperature, wherein the process temperature is about 100 to 350 degrees Celsius. It is mainly used for the industrial heat processes. And of course the high temperature, wherein the process temperature can vary from 400 to about 1000 degrees Celsius. It's mainly for the power generation. We are talking about a surface which is about, in the physics terminology, lambda by 4, that is about 125 nanometer coating technology, which should be stable at, say, about 400 to 1000 degrees Celsius. So it is a very, very challenging. That too, it should have very high absorptivity and very low emissivity, because there will be power losses when the temperatures are very, very high. So this is the region that we need to design highly or advanced materials to harness the solar energy. And of course, we need the suitable collectors to harness the solar energy, which is known as the CSP technology. Of course, today's talk, I'm not focusing on the CSP technology in detail, but briefly, I'll just take you through depending upon the time. So this is a solar thermal power plant. We have the solar field, wherein we have the reflectors, parabolic reflectors. The parabolic reflectors, they have very high reflective coatings, and at the focal point of the parabola, we have the receiver tubes, which are coated with high temperature solar absorber coating, and then a suitable fluid is allowed to pass through these tubes, and the moment the solar radiation falls on these reflectors, the heat is extracted away from these receiver tubes, and which is fed to a large number of heat exchangers to generate very high temperature steam and high pressure steam, which can be used to generate the electricity by way of the turbines. So as on today, there are hybrid technologies wherein you can combine either the fossil fuel or the biomass to run the plant 24 hours, because whenever the sunlight is not available, you can have these hybrid systems. Now, coming to the low temperature segment, we have two important technologies. The first is the evacuated tube collectors. I'm sure that most of you are aware of these technologies, wherein the absorber coating is applied on the external surface of the glass tube, and it is covered with another glass tube to minimize the conductive and convective losses. And this technology is mainly dominated by Chinese market. And the other technology is that you take simple metal fins, and then you apply the absorber coatings, and subsequently you can develop or you can harness the solar energy. Of course, it's a very low cost intensive, and already in the country the expertise is available. So as far as CSRNL is concerned, in the area of solar energy, we have been working for last 3 to 4 decades. Our seniors, they have developed a Nalson black chrome coating technology, which has been transferred to about 29 industries, and it is a cost-effective electrodeposited black chrome with very high absorptivity and very low thermal emissivity. And the variant of this technologies have been developed by our seniors. Now, even though it's a very commercially successful technology, there are problems when you're talking about the sustainability and circularity. The Nalson technology consists of black chrome, which uses the hexavalent chrome. And as you are chemist, hexavalent chrome is not good for our human health, as well as for the disposable becomes very, very challenging because it contaminates the groundwater. So this technology is almost banned in almost all the Western countries. In the country also, we have only 1 or 2 isolated plants wherein they use the effluent treatment plants to dispose of these chemicals. And of course, the technology is not compliant to RHS and REACH regulations of the European Union. So to address that issue, in 2006, when I was a very young scientist, we are working in the area of transition metal nitrides, carbides, and oxides for the metallurgical applications. So we thought that why not to tailor these high temperature materials for the solar energy harvesting. So for the first time in the literature, we came up with an idea of the tandem absorber, wherein titanium aluminum nitride, titanium aluminum oxynitride, and silicon nitride, they were deposited on a given metal substrate with a thickness of about λ/4, that is about 120 nanometers. And this exhibited very high absorptivity and very low emissivity with a very high temperature stability. And this was widely patented and published, and a large number of publications and other kind of compositions were developed based upon this technology. Subsequently, we evaluated this and under various conditions, including heating in vacuum and air, and also the accelerated aging tests such as the UV radiation test, the salt spray test, the adhesion test, thermal shock test, erosion test, and so on and so forth. And it was also validated by the industry giant, Stott Solar from Germany, as well as Arriva Solar in USA. The coating was found to be stable up to 600 degrees Celsius for long durations in vacuum, and about 325 degrees Celsius in air. Now, one of the problem in these high temperature coating is that, as I mentioned, that the radiation losses are proportional to the temperature to the power 4 as well as the emissivity. The measurement of emissivity at high temperature becomes very challenging, and which is very, very important. And these facilities are not available in the country, so we just collaborated with the experts in Europe as well as in the United States to evaluate the emissivity of these coatings, and we find that even up to 500 degrees Celsius, we don't have the emissivity remains less than 0.2, meaning thereby the coating is still spectrally selective. Now this is our journey in last 20 years, starting from 2006 to 2026. We have developed about 15 new compositions, and they are based upon oxides, nitrides, carbides, borides, and the latest coating, which is yet to be published, is stable up to about 800 degrees Celsius in air. And this has resulted in 6 patents which have been filed in 14 countries and more than 80 articles under this activity. So now the question was that we have the proof of concept, but we could not commercialize this because of the fact that the vacuum-based processes and the sputtering is a very expensive process. So what we did was that we looked into the chemistry-based approaches. So we wanted that the cost of the material, whatever you are using as a raw material, should be very high, and whatever the chemicals we are using, they should be eco-friendly, and the technology, the service life of these processes should be more than 20 years. Towards that, for the first time in the literature, we thought that why not to use these graphene-based materials. Graphene is nothing but a flat monolayer of carbon atoms which are tightly packed into a 2D honeycomb lattice. So we can have, depending on the folding, we can have quantum dots, we can have carbon nanotubes, we can have bilayer, multilayer, or single layer graphene. And these materials are highly interesting because of broadband absorption as well as the good thermal conductivity and high thermal stability. So towards that, in 2014, first time, we investigated the use of carbon nanotubes. Carbon nanotube, I'm sure that all the students might have seen, this is jet black. It consists of very high absorptivity and very high emissivity, meaning thereby it acts as a black body. But we came up with an idea that just by controlling the thicknesses of these CNTs, we can make them spectrally selective. And then we found that they were stable up to 650 degrees Celsius in vacuum. Then we also looked into use of graphene. Graphene we deposited on copper foil at a temperature of about 1000 degrees Celsius, and it was characterized using a variety of techniques such as micro-Raman, cross-sectional TEM, and so on and so forth. So once the graphene was available to us, so we gave a concept in the literature that whether the graphene can be used as the spectrally selective. So what we did was that we took a very thin layer of copper, which is about say 30 to 40 nanometer, and it was sandwiched between 2 blocks of graphene multi-layers, and then because of the destructive interference, this gave a very high absorptance and very low emittance. But the problem was that the CVD is not a very industry-friendly process, and the other thing is that the process temperatures are very, very high, and the transfer of graphene onto the engineering substrate becomes a very, very challenging. To address that, we used the commercial methods such as modified Hummer's method to design and develop the derivatives of graphene, such as graphene oxide and reduced graphene oxide. So under controlled oxidation condition, we can either design reduced graphene oxide or the graphene oxide. So this is what we did. We prepared the suspension of RZO, one in sodium silicate, and the other one was the dispersion of the RGO in polyurethane paint, and they were applied on a given surface, but there were certain observations. One is that the emissivity was very, very high to the tune of about say 0.88, and then when the coatings were deployed in the field, they degraded after 1 year because of the fact that the sodium silicate is hygroscopic in nature, and then you don't maintain the optical properties. And then in the case of PU based materials, the material gets degraded because of the UV exposure. And the other thing which we are very conscious about our decision to develop the technology was that RGO uses very, very high quantity of water, and whereas in the case of graphene oxide, the consumption of water for the industrial use is only 1/3. So this is this is for the sake of the student, that whenever the UV, the polymeric material is exposed under UV, you get the chemical change in the structure, the polymer crazing. I'm not going to the detail because I've been asked to wrap up my this thing. And of course, the most important is the impairment of the transparency. And because of this fact, our strategy was to design a material which is mostly or 100% inorganic. So to address that issue in 2022, we came up with an idea that we prepared a suspension of ZO in water, and then it was sprayed on a given metal substrate, and we got very high absorptivity and very low thermal emittance. And as ZO is hydrophilic in nature, so we gave another protective layer to protect this this coating. And this is the from concept to prototype. I'm not going to the detail. This is the raw material, and subsequently the probe sonication spraying at about 175 degrees Celsius on a given metal substrate, and then we can achieve very high absorptivity and very low thermal emissivity. So the other thing is that when we wanted to deploy this technology for the industry, we wanted to show them that the accelerated aging tests. So we have done a large number of accelerated aging tests to determine the service life. The first is the ROHS test, Reese test, VOC test, adhesion test, the humidity test, the accelerated weathering test, the corrosion resistant test in the sulfur dioxide, and the conversion efficiency test that was done in MNRE approved laboratory. And all these tests were, our coating qualified all these tests, and the estimated service life of this coating was about more than 20 years, and it has been widely patented, and we also have the trademark for this coating technology. Now this has been transferred to two industries. One is in Supreme Solar in Bangalore in 2025. They have already started exporting this technology to Middle East as well as in the African countries. And recently in 2026, we have transferred this technology to Helix Solar in Mysore, wherein they have started their production. So to conclude, we have developed the core competence in the country in the area of solar thermal for spectrally selective coatings. We have used newer kind of materials, 1D and 2D materials, such as graphene and carbon nanotubes, and all the chemicals used in the processes were eco-friendly to focus for the sustainability. And this is research has led to about 80 publications and 3 international review articles with 6 world patents. And under this activity, we have trained 7 PhD students, 2 postdocs, and about 20 MTech and BTech students. I've also established the collaboration with leading researchers such as Professor Basu from IISc, ARCI, BRC, CGCRI, and JNC. We have also collaborated with international experts such as Professor Raman, Professor Matthias, Dr. Audrey, and Dr. Professor Roberto. So we got from proof of concept to a prototype to a transfer of technology with a TRL of about 8. So just to conclude that as on today, the country has the solar thermal installed capacity of about 6.8 million meters square. It consists of both the flat plate collector as well as the evacuated tube collectors. And this is equivalent to about 14.8 gigawatt of solar power. Of course, this is not very high compared to that of the photovoltaic, wherein the installed capacity is about 157 gigawatt as on today. So with this, I'd like to thank two of my core team members, Dr. N. Selvakumar, for developing this Nalson Energy technology, Mr. Srinivas, who is the technical officer, and this research has been funded by a large number of funding agencies, my management, my colleagues, my co-workers, students, and the project staff. Thank you very much for your kind attention.
Thank you very much, sir, for your highly stimulating, inspiring, and informative visionary lecture. Based upon your achievement, CRS would like to honor you with CRS Leadership Award,
Thank you.
which will be awarded during the award ceremony. Just before that, the organizers would like to felicitate you. So I invite Professor Yelamagad and other dignitaries.
Namaskar. Once again, good morning, one and all present over here. I, Dr. Stuti Pandya, Assistant Professor, Department of Pharmaceutical Sciences, Saurashtra University, feels privileged to welcome you all on behalf of the Saurashtra University, CRS, and on my own behalf to the inauguration function of the International Symposium on Science Beyond Boundary, Invention, Discovery, Innovation, and Society, RASAYAN-23, jointly organized by Saurashtra University and Chirantan Sanstha, held from 8 to 10 July 2026. Today marks the coming together of brilliant minds from countries united by one purpose: to exchange ideas, build collaborations, and shape the future. It is my honor to request the coordinator of this event to escort and welcome all the dignitaries on the dais. Before we proceed, let us honor the spirit of our host institution. The Saurashtra University anthem reflects a commitment to learning, research, and building a better future for all. Also, it is our pledge to knowledge, integrity, and service beyond borders. I request the gathering to kindly stand in the respect.
विद्यापीठ सदाए पावनकारी नाम दरिया जोड़ी घूघरे अहिया जग विद्या तमाम जय हो जय हो जय जयकार जय हो जय हो जय जयकार सर्वधर्म संभाव हृदय में नरसैयानी भक्ति छे सावज दल कुमार वीर में देवी युवान शक्ति छे गिरनार जेवो स्थिर जीवन हो ध्यान मंत्र कुरान जय हो जय हो जय जयकार जय हो जय हो जय जयकार नो लय प्रेम झलहळे राखे गारनो तेज सोमनाथ ने द्वारिकानो महिमा एनो एज बागीश्वरी नी वीणा बागी झंकृत गाने गा जय हो जय हो जय जयकार जय हो जय हो जय जयकार बुद्ध महावीर गांधी नो पथरायो छे अजवास निर्बल ने बलवान संग में खेले दांडिया रास वल्लभी विद्या याद राख तू जीव तू विद्या धाम प्राचीन विद्या साधे वस्तु नवो यंत्र विज्ञान नवी दिशाओं नवा विचारों नवा युग निशान वृक्षों नी हरियाली बच्चे सरस्वती नु धाम सौराष्ट्र विद्यापीठ सदाए पावनकारी नाम दरिया जेवी घूघरे अहिया जग विद्या तमाम जय हो
Thank you. Please be seated. In India, we say Atithi Devo Bhava. The guest is equivalent to God. As a mark of our respect and gratitude, we now request our dignitaries to accept a token of gratitude. To honor our torchbearer, we now proceed with the welcome ceremony. To welcome our chief guest, Professor Dr. Anil Kakotkar sir, I request Dr. Ranjan Khoot, coordinator of this event, to come forward and welcome our guest with token of gratitude. To welcome our guest of honor, Professor Dr. Utpal Joshi sir, Honorable Vice Chancellor, Saurashtra University, I request Dr. Y.T. Nalyapara, co-convener of this event, to come forward and welcome sir with a token of gratitude. Guest of Honor, Dr. Ajay Singh Jadeja, Registrar, Saurashtra University. I request Dr. M.K. Shah, co-convener of this event, to come forward and welcome our guest with a token of gratitude. I request Dr. Nikesh Shah, Head, Department of Physics, to come forward and welcome sir with a token of gratitude. To welcome our guest, Professor Brij Gopal Bag, President CRS, I request Dr. Ramesh Kothari, Head, Department of Bioscience, to come forward and welcome our guest with a token of gratitude. To welcome our guest, Professor C.V. Elamgat, Secretary CRS, I request Dr. Pooja Pandari, Assistant Professor, Department of Chemistry, to come forward and present the token of gratitude.
I'll do it myself.
Dr. Bharat sir, to please come forward and present the token of gratitude. To welcome Professor Dr. U.C. Puya, Head, Department of Chemistry, I request Mr. Pirang Shah, Assistant Professor, Department of Chemistry, to come forward and welcome sir with a token of gratitude. I request Vice Chancellor Sir Professor Dr. Utpal Joshi to present the awards to our guests and a memento with love. Dr. Anil Kakodkar Sir. I request sir to present the memento to Bag sir. And I request VC sir to please present the memento to C.V. Elamgat sir. Thank you all the dignitaries. These tokens carry our gratitude for your time, wisdom, and for gracing this global stage today. The success of any international gathering begins with vision and ends with an execution. And behind this symposium stands a leader who has turned both into reality. Professor C.V. Yalamgad, Secretary CRS, is a distinguished scientist and the driving force behind CRS. Under his guidance, CRS has become a hub for research, innovation, and global collaboration. I now have the honor for inviting Professor C.V. Yalamgad, Sir, Secretary CRS, to deliver the welcome address. Please.
Thank you. Ladies and gentlemen, a very good morning to one and all present. Once again, ladies and gentlemen, good morning. Sound is not correct. Hello, can you hear me? Yes. Okay. It is my great pleasure and privilege as the Secretary of Chirantan Sanstha, CRS, Vidyasagar University Campus, West Bengal, to extend a warm and heartfelt welcome to each one of you to the 3-day International Symposium, Science Beyond Boundary, Invention, Discovery, Innovation and Society, RASAYAN-23, being held at this prestigious Saurashtra University, Rajkot, which has a huge history of excellence. We are truly honored to have with us an august gathering of distinguished guests, eminent scientists, researchers, academicians, administrators, students, and delegates from CRS, Saurashtra University, and other renowned institutions across India and abroad. It is now my privilege to formally welcome our esteemed dignitaries who are on the dais. Our honorable chief guest, Padma Shri, Padma Bhushan, Padma Vibhushan, Dr. Anil Kakodkar, sir. May I request all of you to raise and give a big round of applause to him, the kind of contributions he has done to the country that is amazing, amazing, amazing. A big round of applause to sir, a big round of applause to sir. Once more, big applause to him, please. Thank you. Sir, we are deeply honored by your gracious presence. Your unparalleled contributions to the science, technology, and nation building continue to inspire generations. On behalf of all of us gathered here, I extend to you our heartfelt welcome and express our sincere gratitude. Our guest of honor, Professor Utpal S. Joshi, Honorable Vice Chancellor of the Saurashtra University. Sir, it is a privilege to have you with us today. Big round of applause, please. It is he who is, backbone of this particular event, because he has given us a huge fund. Big round of applause. You are comfortable, you are eating good food because of him. Big round of applause to him. He is quite generous. On our guest of honor, Dr. A.K. Jadeja, Honorable Registrar of the Saurashtra University. Sir, we are delighted to have you with us and we warmly welcome you, sir. Thank you very much, sir, for being with us. I extend a very warm welcome to Professor U.C. Bhoya, Head of the Department of Chemistry and Convener of RASAYAN-23, sir. Sir, your dedication and tireless efforts have been instrumental in organizing this symposium. I also have a pleasure and privilege of welcoming the President, Honorable President of Chirantan Sanstha, Professor B.G. Bag. Sir, your visionary leadership, constant encouragement and unwavering support continue to strengthen the society and inspire all of us. A warm welcome to Dr. Ranjan C. Kund, who is here. Madam, can you raise for me? It is this lady, heroine, who has done wonderfully well. She has not slept since, I think, 1 month. Above all, I extend my heartfelt congratulations and a very special welcome to all the CRS awardees. A big round of applause to all of you, who are the true center of attraction today's inaugural ceremony. Through your outstanding scientific achievements, you have brought us a great honor to the scientific community and to Chirantan Sanstha. We are privileged to celebrate your accomplishments. I also extend a cordial welcome to all distinguished professors, scientists, researchers, students and administrative staff, industrial representatives, media people and delegates who have joined us from SU and from other different institutions across India and abroad. This symposium truly a special occasion. It celebrates not only scientific excellence but also the spirit of innovation, collaboration and the spirit of knowledge, pursuit of knowledge. It brings together some of the fine minds who are shaping the future of science, technology and education in our own nation, proud nation Bharat. We are indeed privileged to be in the company of such eminent contributors to research and innovation. I am confident that the scientific deliberations, inspiring lectures and meaningful interactions over the next 3 days or so will enrich our knowledge, foster new collaborations and create lasting friendships. Once again, I extend a very warm welcome to each one of you. I wish you a highly productive, enjoyable and memorable conference, symposium. Thank you very much. Thank you one and all.
Thank you, sir, for the warm welcome. Everything begins with one thing: illumination, an idea, a spark, a light. To formally inaugurate our proceedings, we begin with the ceremonial lighting of the lamp, a universal symbol of knowledge, dispelling darkness. I request our dignitaries on the dais to please come forward and light the lamp.
आरोग्यं धनसम्पदा शत्रुबुद्धिविनाशाय दीपज्योति नमोऽस्तुते दिव्यादिव्यारे दीपत्कार कानी कुण्डलमोतिहार दिव्या मोतिहार दिव्याला पाहून नमस्कार तिळाचे तेल कापसाची वात दिवा तेवे देवा पाशी उजेड पडे विष्णू पाशी माझा नमस्कार सर्व देव देवतां पाशी ये ग लक्ष्मी बैस ग बाजे माझं घर तुला साजे घरातली इडापिडा बाहेर जाऊ दे बाहेरची लक्ष्मी घरात येऊ दे घरच्या सर्वांना उदंड आयुष्य सुख समाधान शांती लाभू दे
शुभं कुरुध्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीप नमोऽस्तुते ॐ
thank you all the dignitaries, coordinating members and students. As this lamp glows brighter, may every idea shared here bring more clarity to the world. May the light of the symposium reaches to the labs, classrooms and communities far beyond this hall. CRS has a story of vision, struggle and purpose. To tell us this story, I am inviting Professor Braj Gopal Bagh, President of CRS. As a president, he has guided his institute from a dream into a center of global research excellence. So please share with us the journey, mission and vision of Chirantan Rasayan Sanstha.
Respected dignitaries on and also off the dais, our guest of honor, Nobel laureate, Professor Venki Ramakrishnan, whose presence in the virtual mode today elevates this forum to a global stage. Our honorable chief guest, Padma Shri, Padma Bhushan and Padma Vibhushan, Dr. Anil Kakodkarji, guest of honor and also the chief patron of this symposium, Honorable Vice Chancellor of Saurashtra University, Professor Utpal S. Joshi, guest of honor, Registrar of Saurashtra University, Dr. Ajay Singh Jadeja, Honorable Vice Chancellors, Deans, Directors and heads of various departments and centers, and other administrative officers, head of the Department of Chemistry and also convener of this symposium, RASAYAN-23, Professor U. Shivua, organizing secretary of the symposium, Professor Ranjan Sikhunt, secretary of Chirantan Rasayan Sanstha, Professor C.P. Elamagad, all the CRS award recipients, representatives from industries, and most importantly, the heartbeat of this conference, scientists, faculty members, postdocs, research scholars, students, staff members, media persons, ladies and gentlemen. It gives me an immense pleasure to welcome you all to the international symposium entitled Science Beyond Boundary, Invention, Discovery, Innovation and Society, RASAYAN-23, organized jointly by the Saurashtra University, Rajkot, Gujarat, and CRS in association with the Society of Materials Chemistry India, Indian Council of Chemists, and also Electrochemical Society of India. Let me tell a few words about the Society Chirantan Rasayan Sanstha, briefly known as CRS, and its objectives. Does it work? Saurashtra University is celebrating its 60th year, and heartiest congratulations for the same. Now, CRS was established in the year 2016, and we are also marking the year-long celebration, 10th year celebration of CRS. Let us give a big hand to all the council members and others who have contributed for the growth of the society. It has the following objectives: to promote research and development in all the branches of science for a better living, to organize seminars, workshops, training sessions, and also similar activities for the promotion of research and development in all the branches of science, and outreach activities, to collaborate with established institutions in India and abroad and other big societies to fulfill the goals, and also to carry out activities that may assist in or be necessary for the fulfillment of the above objectives. The society, since its inception, organized various national as well as international symposia at a regular interval jointly with various leading societies, universities and colleges such as American Chemical Society, Royal Society of Chemistry, IJAR Kolkata, Jain University, Christ University, Vidyasagar University, Minapur City College, RNLK, Women's College, and so on. 22 conferences have been organized already by CRS. We have honored outstanding scientists by offering medals and arranging their award lectures. Over 300 scientists have already been honored with CRS medals from India and abroad in such a short span of time, including Bharat Ratna Professor Senar Rao, Nobel laureate Professor Joachim Frank, Professor Mongi Vivendi, Padma Vibhushan Professor R.A. Maselkar, Padma Shri Professor Govardhan Mehta, Padma Shri Professor P. Balaram, Padma Shri Professor K.N. Ganesh, Professor G.U. Kulkarni, Professor B.L.P. Prasad, Professor S. Chandrasekharan, Professor T. Pradeep, Professor A.K. Tyagi, Professor Richard G. Weiss, Professor Duncan Bruce, Professor Ajan Bhindu, and so on. The Society publishes one online journal named Pragic Rasayan. It means Applied Chemistry in English and Angewandte Chemie in German. It is a quarterly open access peer-reviewed journal where the publication of articles is free of charge. Students are the future leaders of science, technology, and society. Hence, we have organized different programs for the students, including yoga sessions, lab on wheels to train students in open air during pandemic period, and also the felicitation of performance and so on. Moreover, during pandemic, the society distributed food and other materials to the needy people in remote villages. CRS this time has organized the first ever symposium like this here at Saurashtra University, where the 2009 Nobel laureate in chemistry, Professor Venki Ramakrishnan, addressed the audience a couple of minutes ago. We are grateful to Professor Venki Ramakrishnan for addressing the audience and giving his consent for accepting the CRS honor, the CRS Lifetime Achievement Award. CRS is grateful to the Honorable Vice Chancellor of Saurashtra University, Gujarat, for his constant encouragements and supports. The CRS live membership has been increasing steadily, the number becoming almost double during the last 1 year. Being pleased by the activities of CRS, everyone wants to be associated with CRS. We from the CRS family will welcome you and welcome all the new members. Let us make this 3-day international symposium a grand success with fruitful academic exchanges, collaborations in various fields of science, technology, and society for a better living. Thank you very much. Namaste, Dhanyavad, Abhar, Jai Hind.
Thank you, sir, for introducing us about the spirit of CRS. We are now honored to have with us a leader who bridges academia and administration with equal excellence. His leadership in academic administration and his commitment to taking this university onto the global stage resonate deeply with the spirit of this symposium. I now have the privilege to invite our guest of honor, Professor Ajay Singh Jadeja, Registrar, Saurashtra University, Rajkot, to address this gathering.
Namaskar all. First of all, welcome to the Saurashtra, the land of Mahatma Gandhi. It is a moment of pride and joy for all of us to welcome this particular symposium jointly organized by CRS and Saurashtra University. Respected dignitaries on the dais, Padma Vibhushan, Dr. Anil Kakodkar sir, our Honorable Vice Chancellor, Professor Joshi sir, Dr. Professor Bagh, most energetic CRS Secretary, Dr. C.V. Elgam, our organizing Secretary, Professor Boya, Professor Ranjan Ben Khot, respected invited dignitaries, senior scientists, faculty members, students, ladies and gentlemen. Once again, warm welcome to all of you. I congratulate every awardee for receiving their prestigious award. It gives me immense pleasure to be present at the inauguration of RASAYAN-23 the International Conference on Science Beyond Boundary, Invention, Discovery, Innovation and Society. I extend my heartfelt welcome to all of our distinguished guests, eminent scientists, academicians, industry experts, researchers, and students who gather here from different parts of the country and abroad. Your presence has truly enhanced the significance of this academic event. At the outset, I congratulate the Department of Chemistry, Saurashtra University, and Chirantan Sanstha for their dedicated efforts to organizing this particular prestigious international conference. I sincerely appreciate the organizing committee, faculty members, research scholars, students, and every volunteer who has worked sincerely to make this conference a reality. University play a vital role in nurturing the innovation and creation and ecosystem where ideas can flourish at Saurashtra University. We remain committed to promoting excellence in teaching, research, and innovation. We encourage our faculty members and students to pursue meaningful research that not only advance scientific knowledge but also contribute to solving real-world problems and improving the quality of life. I am confident that the technical session, keynote lectures, invited talks, and poster presentation over the next few days will provide an enriching academic experience for all participants. I hope that the discussion held during this conference will generate new ideas, strengthen research collaboration, and inspire innovative solutions for the benefit of the society. Before I conclude, I once again express my sincere appreciation to all the sponsors, collaborators, invited speakers, delegates, and members of the organizing committee for their valuable contribution. Your support and participation have made this conference possible. Thank you once again. Jai Hind.
Thank you, sir, for your insightful address and for guiding us about the university's role in building global knowledge network. A university rises when its leadership has both vision and courage. Today, we are privileged to have the chief custodian of one of the premier universities with us. He is an eminent academic leader and researcher whose commitment to quality education, research excellence, and global collaboration has strengthened Saurashtra University's reputation worldwide. His presence today underscores the importance of the symposium. I now have the honor of inviting our guest of honor, Professor Dr. Utpal Joshi, sir, Vice Chancellor, Saurashtra University, to please come forward and address this gathering.
Namaskar. First of all, a warm welcome once again at this campus. It is really a proud privilege to host all three Padma awardees, Professor Anil Kakorkar ji, on our campus, and it was possible because of this CRS efforts, and I really congratulate and thankful to you as well, Professor Bag and Yalamagar ji. My fellow colleagues, Bhange sir, is the Vice Chancellor of MS University, Vadodara, and other distinguished leaders from different various institutes. Thankfully, today there is some little break in rain. Otherwise, when the dates came to me, I was a bit worried about how to go about it, because, you know, when it is in a rainy season, the efforts of the organizer become double, in fact. But thankfully that God is with us, at least for the inaugural session, and hopefully that everything will move smoothly. You know, this is like in the morning we had a video lecture by Professor Venki, who is going to be the recipient of, in fact already recipient of the Lifetime Award from CRS, Achievement Award.
I was listening carefully to what he was talking, and he made one, Watson's remark that in his laboratory, he was, unless and until his contribution is very high, he don't claim the authorship. In fact, the authorship goes to the student, and that is how, and then the brilliant work came out of students' effort. That is something, they started the tone of this event, in my opinion, that this is something what one must learn, that, without the supervisor, supervisor gives you the free hand to publish by your own, unless and until he, intellectual or any other way, contribute to that. It is indeed set a tone and really very nicely organized first initial, again CRS has done that. You see, Saurashtra University, we have a legacy. We are into the 60th year of our establishment. 23rd May 1967, with the Gujarat Government Act, we came into existence. And since then, there is a legacy of, giant stalwarts. We have presently right now in the university 29 postgraduate departments and about 300 affiliated colleges spanning into 5 districts of Saurashtra. So it's one of the biggest in the, in fact, in the western region, I would say, not only Gujarat. And the chemistry department is one of the forefrontiers in the development of the university as far as the, the achievements and academic leadership and, guiding the next generation is concerned. About nearly 500 PhDs have been produced in chemistry department alone over the period of this many years. And UGC and DST funded very specially to this particular department on the pharmaceutical science, the medicinal chemistry. That was one of the flag bearers was Saurashtra University in entire country, and this is really a proud moment of that. They have been organizing such kind of event at different scales, but really it is a matter of pride for all of us to host you here. And I hope that, and also one more point that I want to bring here is out of 35 universities in the country, we are Meru University. Full form of the Meru is Ministry of Education. It's a multidisciplinary education and research university. Only 35 universities are there, and we got into 100 crore club. For 5 years, we got 100 crore for research and infrastructure. We have almost 60-40 ratio. So in, I think, 2 years down the line, we can see that the research facility infrastructure here, as far as the equipments are concerned, we will be at par with any of the national institutes like IITs and all that. That is in the pipeline. So we are going to procure that very soon. And this is the right platform actually to, many of the collaborators. We are wholeheartedly welcome you to collaborate with us. Not only chemistry, but we have in physics also, we have the first area is material science, and your material science is nothing but, chemistry, and in fact chemistry comes first, then comes the physics for characterization. So that way also we welcome all the, in fact the CSIR sir has already mentioned about he is a physicist, but what he mentioned all about the surface sciences, which is part of the, inorganic chemistry. So we welcome all the delegates for even, not only this is going to be three days are not going to end here, but it should be beginning for the collaborations at large. And if CRS is the right platform actually to collaborate with the various institutes. And as a Vice Chancellor, I wish that the university, although we are working in silos, but the national education policy is not believing in those silos. We have to cut across the, multidisciplinary right from the beginning at the +2 level. It has to come into foreplay. And that has been the motto of this national education policy, and we have been, taking utmost care that all the fulfillments of this or the expectation of the NEP 2020 is met, not only at UG level, but now we are into postgraduate level. So I welcome all of you individually also to collaborate with any of the department. We have a department of nanoscience and applied physics. So that is also doing, much of the chemistry like CNT and all those problems. So all in all, every laboratory is, we wish to collaborate. We have collaborations going on, but we want to strengthen that in future course as well. And thanks to CRS for their nice efforts and choosing us in the western part of the country to organize this 3-day event. And I was just looking into these things. There are 75 awardees, so I thought in fact one day will go in award ceremony itself. But made the presentations quite brief, so that is very nice, and really looking forward to deliberations in the days to come. Dr. Sangeeta is here, and we had a very long time that we meet here. Thank you for this nice, giving us the chance to host. In case of any problems in accommodation or any other thing, please feel free to talk to any of the volunteers. We will try to rectify it as soon as possible. As I said, because of this rainy season, there are some insects and all these things, because we are completely green area of 336 acres. So there may be some little bit of problem, those who are in the campus. But please feel free to tell us, and I apologize in case if you have any inconvenience. Thank you.
Thank you, sir, for your inspiring address and for reforming the role of universities in shaping a knowledge-driven future. It is now my privilege to introduce the towering personality whose presence elevates this symposium for an academic event to a historic occasion. Professor Dr. Anil Kakotkar is a renowned Indian nuclear physicist and mechanical engineer who played a pivotal role in positioning India as a global nuclear technology. He spearheaded the 1998 Pokhran-2 test and was instrumental in developing India's indigenous three-stage nuclear power program to harness domestic thorium reserves. A stalwart of the Department of Atomic Energy, he served as a director of the Baba Atomic Research Center and chairman of the Atomic Energy Commission of India. He was awarded the Padma Shri, Padma Bhushan and Padma Vibhushan, India's second highest civilian honor. I now request sir to please come forward and address the gathering. I request everyone to please give a huge round of applause to you.
Honorable Vice Chancellor of Saurashtra University, Professor Utpal Joshi, the President of Chirantan Rasayan Sanstha, who is our host for this conference, Professor Rajkot Bagh, Registrar of this university, Dr. Jadeja, Honorary Secretary of CRS, Professor Yellamagad, Dr. Bhoya, distinguished participants to this very important meeting. I think the theme speaks for itself: science beyond boundary, inventions, discovery, innovation, and society. So I think there is nothing left, everything is included. So distinguished participants, ladies and gentlemen, there is always a when we do science, there is always an issue. Science for pushing boundaries of knowledge, frontiers of knowledge, or science for development, or the theme that you have. And while both are important, clearly both are important, but we all have come up in traditions, in groups, under the mentoring of our seniors. And so they say the that many times going forward in science, on one side you have the rigor of science, on the other side you have a liberal approach. And it is only the maturity among the scientific workers, researchers, that would decide how a group, how an institution, how a particular program would go forward. And I think this issue is particularly important for a country like India, in the sense we have a huge development deficit. At the same time, we want to be counted among the best in the world in terms of research. And it's a challenge. Of course, we have this new education policy, which I think is very well thought out, but sometimes I wonder the top-down approach in terms of directives of how to implement would cut away all the flexibility, all the innovation at the grassroots level, and I think we need to be careful. So, I for one have always considered the science as a continuum. The research and its translation, all the way to benefit the common man as the total domain. And I was very happy that that seems to be the focus of this particular conference. I was actually quite apprehensive about coming here, and it was my friend Dr. Tyagi who insisted that I should come. Otherwise, I actually felt that, look, not being a chemist, I have no place. I know, but I think compliments to you for a very broad and very holistic look. The second point that I wish to make is, we have this discipline boundaries, physics, chemistry, biology, what have you. And as I mentioned in my lecture, if we treat the whole development in a traditional way, in the sense talking about nuclear reactors, there is a way nuclear reactors have been developed. There are experts and experts. And if you stick to same way of doing it, you are actually unlikely to solve the new problems. On the other hand, if we keep an open mind and put the problem solving first and bring the discipline next, I think many things can be achieved. And as I said, to me it looks that future way of building nuclear reactor would be the chemist's way. It's quite likely. So I'm not here to make a long speech, but I wish to compliment all of you, particularly CRS, for what you are doing. And I think you seem to have achieved a lot within a short time. You said 23 conferences in 10 years. Is that right? Yeah, so I think doing that in a sustained way and keeping the interest of participants alive speaks volumes. So congratulations to all of you. Of course, I would also thank Saurashtra University for, for an institution like that, they have to move and they need hosts year after year. And it's nice that all universities are coming forward. So and finally, to you all participants, I do hope and expect that your being here, the deliberations that will take place here, and the way CRS is moving forward will usher in perhaps a new way of doing collaborative work. Thank you very much.
Thank you, sir, for igniting minds. Not just the ceremony. We carry your message forward into every session. Your address prompts us that science without purpose is incomplete and research without service is directionless. Every great beginnings needs a gracious close. The inaugural session of RASAYAN-23 now draws to a close, but the spirit it has exploded will carry us through these 3 days. To express our gratitude to everyone who made this beginning possible, I now invite Professor U.C. Bhuya, head and convener of this event, to please come forward for the vote of thanks.
Good morning, everyone. Distinguished dignitaries on the dais, eminent scientists, academicians, delegates, faculty members, researchers, and my dear students. It is my privilege to propose the vote of thanks on this memorable occasion of the inauguration of our International Symposium RASAYAN-23. First of all, I would like to thank CRS for giving us this opportunity to organize such wonderful international symposium on science beyond boundary, invention, discovery, innovation and society, RASAYAN-23 at Department of Chemistry, Saurashtra University, Rajkot. I express my heartfelt gratitude to our esteemed chief guest, Padma Vibhushan, Dr. Anil Kakodkar sir, renowned nuclear scientist and former Chairman of the Atomic Energy Commission of India, for gracious accepting our invitation. Sir, your inspiring address, remarkable vision, and invaluable contribution to science have truly motivated us all. I sincerely thank our Honorable Vice Chancellor, Dr. Utpal Joshi sir, for his visionary leadership and constant encouragement, and our respected Registrar, Dr. Ajay C. Jadeja sir, for his unwavering support in making this symposium possible. My heartfelt appreciation goes to Professor Braj Gopal Bagh, President of CRS, and Professor C.V. Yelamagad, Secretary of CRS, for their valuable guidance and continued support in promoting scientific excellence. I also thank all invited experts, session chairpersons, delegates, and participants for academia, research institute, and industry for enriching this symposium with their presence. A special note on gratitude goes to our organizing secretary, Dr. Ranjan Sekhut, along with our co-convener, Dr. Y.T. Nalyapara and Dr. M.K. Shah, whose dedication and teamwork made this event possible. I thank CAS, SES, SMC, GSBTM, DST, JOL, SNJ Group, INCARP, Krishna Scientific Traders, Camphorya, Savitur Laboratories, JSK Chemical, and Sieve Chemical and Manufacturing for financial support for this international symposium. I also thank every member of the organizing committees, volunteers, faculty, staff, and media representativeness for their tireless efforts. Finally, I thank each one of you for your enthusiastic participation. I wish you all a productive, enriching, and memorable symposium. Thank you.
Thank you, sir. As the busy schedule of our dignitaries now will proceed for the award ceremony. With this, I, Dr. Stuti Pandya, concluding this inaugural session of RASAYAN-23 and hand over this stage to Dr. Krishna Joshi from Atmiya University to carry forward the award ceremony. Thank you, everyone.
Most awaited moment is here. As our eminent guest, Dr. Anil Kakodkar, has some busy schedule, and so we directly move forward to the award ceremony, and that way the high tea is cancelled. Very humbly, I request, postponed, sorry, it's postponed. Very humbly, I request all the dignitaries to please take their seats off the dais. Now I request all the dignitaries please to take their seat off the dais, so that we can start the award ceremony. Good morning, ladies and gentlemen. I, Dr. Krishna Joshi, Head Department of Life Sciences, Atmiya University, behalf of Organizing Committee, extend a very warm and cordial welcome to our distinguished guest, eminent scientist, academician, industry leaders, faculty members, research scholar, and dear students, to a morning of a pride, purpose, and celebration. RASAYAN-23, an international award ceremony organized by Chirantan Sanstha, CRS, and Department of Chemistry, Saurashtra University, Rajkot. Friends, this is a land of Aryabhata and Charaka. This is a land of Professor C.V. Raman, Bharat Ratna Professor C.N.R. Rao, Homi Bhabha, Kalpana Chawla, Dr. APJ Abdul Kalam, and many more eminent personalities. Today, in same unbroken legacy, we honor the scientists of today, men and women whose research, innovation, and lifelong dedication have advanced science and served the society and the nation. To brief about the significance and the origin of the award, may I request Professor Yellamagat, Secretary, Chirantan Sanstha, to come over the dais. Over to you, sir.
Thank you very much. At the outset, I would like to express my deep sense of gratitude to all the awardees. Despite their busy schedule, they come over here to receive a CRS honor. In the interest of time, there's a long history how we started and our struggle. You know, we struggled a lot, a bit, for a long time, but it is during the 3-4 years, because of the blessings of Professor A.K. Taggi and Professor Kakodkar and other stalwarts, we have been able to do well. And we are sure that in the days to come, most of the Nobel laureates will be invited in personally. The next conference is in KIT, Bhubaneswar. We are hoping to get 2 Nobel laureates physically. The plans are on, and I hope things will, the cosmos energy with us to bring them over here. And with this brief introduction, in the interest of time, as a Professor Dr. Anil Kakodkar has to leave shortly. So, given the fact that each one of you, if you receive, award from him, I think there is nothing more than that. I think that's in the interest of that, I have cancelled. My apologies, my sincere apologies. I cancelled your, mouth-watering high tea. Okay. So I request now Surya Prakash and Dinesh Rangappa to be on the dais. Now we'll begin. Okay.
Some people work for a living, a very rare few made for their work. And in doing so, they lift an entire nation. Our first and foremost prestigious honor, the CRS Lifetime Achievement Award, celebrate one such life of excellence. This award recognizes scientists whose lifelong contribution have transformed their fields and inspired generation of researchers. May I request Honorable Dr. Anil Kakodkar to be on the dais, please, to receive the award. Kakodkar sir, please. Ladies and gentlemen, let's give a round of applause. Let's give a standing ovation to the sir. There must be clapping, please. Dr. Anil Kakodkar is one of the India's most distinguished nuclear scientists and eminent architect of the nation's atomic energy program. Padma Shri, Padma Bhushan, Padma Vibhushan awardee, a former chairman of the Atomic Energy Commission and Secretary, Department of Atomic Energy. Currently, he is serving as a Chancellor of Homi Bhabha National Institute and Chairman of Rajiv Gandhi National Institute. It's our privilege to confer upon Honorable Dr. Anil Kakodkar the CRS Lifetime Achievement Award in recognition of his extraordinary leadership, scientific excellence, and enduring service to the nation. Heartiest congratulations, sir, behalf of all of us. I now request Mrs. Kakodkar to be on the dais, please. Let's give a huge clap, friends. Let's give a token of love and appreciation and respect to Mrs. Kakotkar. Thank you very much, madam. Thank you very much, sir, for your gracious presence. We are very honored to have you, sir and madam, over here. Many, many congratulations once again. Thank you so much, all the dignitaries. Okay. The next category of the award is a leadership award. The next slide, please. Leadership Awards honors those who have led from the front, in the laboratory, in the classroom, and into the service of the nation. I request our first awardee in this category, Dr. Harish Barshilia, Chief Scientist and Advisor, CSIR, National Laboratory, Bangalore. Honorable Sir, I request you to be on the dais to receive the award. Let's give a big round of applause, ladies and gentlemen. Many congratulations, sir. Thank you so much for your presence, sir. Ladies and gentlemen, clap must not stop. Thank you so much, sir. Thank you all the dignitaries. May I now call upon the second awardee in the same category, Professor Divan Singh Rawat, who is a Vice Chancellor, Kumaon University, Nainital, Uttarakhand. I request sir to be on the dais, please, to receive the award. Ladies and gentlemen, let's clap for them. Many, many congratulations, sir. Congratulations, sir. Thank you so much. May I now request the third awardee in the category, Honorable Vice Chancellor, Professor B.M. Bhange, Vice Chancellor of MS University, Baroda. May I request sir to be on the dais, please. Ladies and gentlemen, let's clap. Many, many congratulations, sir. These are the leaders whose visionary leadership make them stand different in the positions, help in developing the place where they are. Many, many congratulations. I now call upon the next awardee, Professor Dr. Pramod Patil, who is a Research Director, D.Y. Patil Education Society. May I now request Dr. Pramod Patil to be on the dais, please, sir. Let's give them a big round of applause. Many, many congratulations, sir. This is a moment of pride and pleasure. This is a moment of celebration of our leadership. Congratulations, sir. Let's give them a big clap. Sir, as we have not given a high tea, there is a less clap. May I now call upon the next awardee, the dynamic Vice Chancellor of Saurashtra University, Professor Dr. Uttal Joshi. Please to be on the dais, sir, to receive the award, whose dynamic leadership has shaped the university the way it is today. Many, many congratulations, sir. Let's give a big round of applause to the sir. Sir has already assured we'll get a high tea that can be in the double amount. Congratulations, sir. Your visionary leadership will definitely shape the university much more the way it is today. Thank you so much, all the dignitaries. May I now call upon the next awardee in the category, Professor Ranjit Kumar Verma, who is a founder Vice Chancellor, Munga University, Bihar. Respected sir, I request you to be on the dais, please, to receive the award. Let's give a big round of applause to the sir. Many, many congratulations. Congratulations to all our distinguished awardees in the category of the leadership. May your leadership continue to light thousands of more lamps of the knowledge and inspire the young researchers too. Many, many, many congratulations to all the awardees in the category. You are truly an inspiration to all of us. Next slide, please. The next category of the award, that award for gold medal. Unfortunately, none of the awardees are present today with us because of their prior commitments. May I now request Honorable Vice Chancellor Dr. Uttal Joshi sir. May I now request Vice Chancellor sir of the MS University, and may I now request Vice Chancellor sir Dr. Ranjit Kumar Verma, please to be on the dais to give away the awards. None of the awardees in the gold medal category are with us today because of their prior commitments. CRS will okay. We have the awardee, Dr. Pramod Patil, sir. I request, sir, to be present on the dais, please, to receive the award. Let's give a big round of applause to the Pramod, sir.
Next category.
Okay.
So, gold medal over.
Okay. Today's era needs a translational research. So, the next category of the award, that is a research partnership and translation. May I now request Dr. Thampi, who is a founder and CEO of Accelerates.ai, to receive the first category of the award in the era of the research translation, research partnership and translation. Okay. We now move forward to the Silver Star awardees. Okay, now we move very fast to the next category of the award, Silver Star awardee. May I now request Dr. Nagaswarupa HP, the first awardee in the category, to receive the award. Please give a big round of applause to the sir. Dr. Nagaswarupa HP, who is a professor, Department of Studies in the Chemistry. Let's give a big clap. These people who are a Silver Star awardee, who has even made a significant contribution into the field, into the institution, into the place where they are. Many, many congratulations, sir. You can see on the slide, you can find out the profile of every personality, eminent personality, and you can find out that they have n number of research papers. They have the H index and citation. Even it is a dream of a young researcher. So these people are true inspiration for the students, researchers who are sitting here. Your research, your translation, your innovation, your contribution to the field is remarkable and commendable. Many, many congratulations. The next category of the award is Dr. S.T. Aruna. Dr. S.T. Aruna. May I request Madam to be on the dais, please? You can find on the slide the profile of Dr. S.T. Aruna. She has H index of 41. Those researchers who know the significance of the H index. Madam has H index of 41 and citation is 11,900. It is a big and huge number. So, Madam has contributed a lot in the field of the research. Many, many congratulations, Madam. Let's give a big clap. તાલીઓ ઓછી ના થવી જોઈએ, હા? Okay. May I now request the third awardee in the category, Professor Dr. Sangeeta Kale. Professor Dr. Sangeeta Kale to be on the dais to receive the award. Professor Kale is a senior professor and dean of research. She has over 245 publications. She has a technology transfer that is a 6 in number, and Madam has H index 41. So Madam, your commendable contribution to the academics and research are truly acknowledged and recognized. You are inspiration for all of us. Many, many congratulations, Madam. Huge round of applause to all our awardees, please. They have given their significant portion of their life to the field, to the academia, to the research, to the society, and in turn to the nation. May I now request the next awardee in the category, Professor Anantaraju K.S. May I now request the next awardee, Anantaraju K.S. to be pleased on the dais, sir. Who is a professor and head, Department of Chemistry, Bengaluru. Sir has H index of 46 and citation of 6155. So again, all of the academician researchers, they have good publications, H index and citations. That is an inspiration for all of us. Many, many congratulations, sir. Let's give a huge round of applause. Thank you so much, all the dignitaries. May I now request the next awardee in the category, Professor A. Nirmala Grace. Professor A. Nirmala Grace to be on the dais, please. Who is a professor and director, Center for Nanotechnology Research, VIT Vellore. Professor A. Nirmala Grace. Many, many congratulations, Madam. Madam has 190 publications, 67 H index, and 13,800 citations in her account. So many congratulations for your significant contributions to the academia and the research. Let's give a huge round of applause. We forget to clap in between. May I now request the next awardee in the category, Professor Manoj Kumar. May I now request next awardee, Professor Manoj Kumar, to be on the dais, please. Who is a CSIR Emeritus Scientist, Department of Chemistry, Guru Nanak Dev University, Amritsar. Sir has H-Index 52, 225 publications, patents and citation in his account. Many congratulations, sir, for your contributions to the society, to the field of academics. Let's give a huge round of applause. May I request Professor Harish Bashilia to please on the dais to give away the awards. Please, sir, join with the dignitaries on the dais. May I now request the next awardee in the category, Dr. Anita Rajesh. May I now request next awardee in the category, Anita Varghese. On the dais, please. Dr. Anita Varghese, who is a professor, Department of Chemistry, Christ University, Bangalore. Madam has 38 H-Index, 170 publications, 4,372 publications. Ladies and gentlemen, if you can notice all of the academicians who have significantly contributed not only in the field of academics but also in the field of research also. So let's give a big round of applause to all our awardees. Many congratulations, madam. Next category, next awardee in the category, Dr. Suman Singh. May I now request Dr. Suman Singh to be on the dais, please, who is a scientist F, CSIR. Dr. Suman Singh. May I now request Madam to be on the dais, please. Madam has 3 patents, over 173 publications with the H-Index of 38 and citation of 5012. Many congratulations, Madam, for your significant contributions. Let's give a huge round of applause to the Madam. Whatever the amount of efforts all the awardees have made to the field, to the society, we only have to put the little effort just to clap. So we should not forget that. Many congratulations. Next category, next awardee in the category, Dr. Ramesh Gardas. Next awardee, Professor Ramesh Gardas, who is from Indian Institute of Technology, Madras, Chennai. Let's give a huge round of applause. Sir has 270 plus publications, patents, 55 H-Index and citations of around 11,000. So again, we all are teaching fraternity, scientific fraternity. We know the significance of what has been stated onto the slide. So let's give a huge round of applause. Sir has done the education from Gujarat. So it's again a proud matter for all of us. So sir must be knowing Gujarati also. Many congratulations, sir. Next I would like to call upon Dr. Shiva Kumar Vaidyanathan. Dr. Shiva Kumar Vaidyanathan from Indian Institute of Technology, Hyderabad. Dr. Shiva Kumar Vaidyanathan. Sir has 4 patents 170 plus publications, 34 H index, and 3,000 plus citations. Dear all, you know the significance of patent, citation and everything. So let's give a huge round of applause. Many, many congratulations, sir. Clap must not stop. I can see here many students who might not be knowing what has been mentioned into the slide. It is a greater and significant contribution to the field, and hope you all will achieve the same in future by inspiring all of this eminent personality today here are felicitated. Many congratulations, sir. May I now call upon the next awardee in the category, Dr. Y.S. Vidya. Dr. Y.S. Vidya, who is Associate Professor, Government Science College, Mandi.
A special mention to her. She is in the college, but she has done wonderfully well. She is in the college. Give a big round of applause to her. Such women are needed to our country.
You can find the number H index, that is a 32. Publications are 150 plus and citations are 3,000 plus. So again, it's a big deal. And let's give a huge round of applause to Dr. Vidya. Many, many congratulations, madam. Next awardee in the category, Dr. Shovan Majumdar. Dr. Shovan Majumdar from Rajaramanna Center for Advanced Technology, Indore. Give a huge round of applause to the sir. Continue with the legacy of the teaching fraternity, academician. Sir has 150 plus publications, 36 H index and 3,000 plus citations. So many, many congratulations, sir, for your contributions. Here you can find all our eminent awardee, all our eminent academicians who have extraordinary contributions to the scientific community, to the scientific fraternity, society and in the nations. A true inspiration for all of us. Many, many congratulations to all of them. I hope as they have received a Silver Star Award today, may they keep shining and keep showing the way to all young minds, all young researchers, and lead India the top in the world. Many, many congratulations to all the awardees in the category of the Silver Star Awards. Let's give a huge round of applause to all of them. Next category, we move to the next category of the award, which is a Silver Medal awardees. I would request first awardee in the category, Dr. Durga Prasad Hari. Dr. Durga Prasad Hari, please to be on the dais. Okay. Next awardee in the category, Dr. Sridhara MB. Next category in the awardee, Dr. Sridhara MB, to be on the dais. Next. Okay. Next awardee in this category, Professor Baswaraj Padmashali. Sorry, Dr. Baswaraj Padmashali. I am sorry for mispronunciation. Professor Baswaraj Padmashali, to be on the dais, please, sir. Sir is a senior professor, Department of Chemistry. Sir has 33 H index, 170 publications, 4,000 citations and 5 patents on his account. Many, many congratulations, sir, for getting the silver medal from CRS. Let's give a huge round of applause. May I now request the next awardee in the category, Professor R. Kothandaraman. Professor R. Kothandaraman to please on the dais. Okay. May I now request the next awardee in the category, Dr. Shri Panna Chatterjee. Dr. Shri Panna Chatterjee, who is a scientist, CSIR Institutes of Mineral and Material Technology, Bhubaneswar. Big round of applause to the madam. Dr. Chatterjee has 3 patents on her name, 69 publications, 21 H-index and thousands plus citations. Many congratulations, madam, for your contribution to the scientific fraternity. Let's give a huge round of applause when the felicitation is going on. Ladies and gentlemen, many congratulations. May I now call upon the next awardee in the category, Dr. Prasanna Shivaramu. Dr. Prasanna Shivaramu to receive the Silver Medal Award from all our dignitaries. Dr. Slide, may I request to change the slide, please? Yeah. Who is Associate Professor, Department of Applied Sciences, Bangalore. Dr. Prasanna Shivaramu has 24 H-index, 1000 plus citations and 95 publications. Many congratulations, sir, for your contribution to the scientific fraternity. Let's give a huge round of applause to the sir. Thank you so much all the dignitaries for such felicitation. Congratulations. May I now request the next awardee in the category, Dr. Subra Singh. Dr. Subra Singh, who is a Deputy Director, CSRC, Anna University, Chennai. Dr. Subra Singh. Next awardee in the category, Dr. Subra Singh. Madam has 100 publications, 22 H-index, 1000 plus citations and 3 patents. Okay, may I now request the next awardee in the category, Priyankar Pera. Dr. Priyankar Pera. May I now request the second awardee in the category, Dr. Priyankar Pera. Sir has over. Many congratulations, sir, who has 30 H-index, 3000 plus citations, 3 patents on his name, who is Associate Professor, Department of Chemistry, School of Advanced Sciences, VIT, Vellore. Let's give a huge round of applause. Many congratulations, sir. May I now request the next awardee in the category, Professor P.C. Ravi Kumar. Professor P.C. Ravi Kumar, a huge round of applause to the sir. Dr. Ravi Kumar is from Indian Institute of Science, Education and Research, IISR. Sir has 19 H-index, 2000 plus citations and 85 publications. Many congratulations, sir. Let's give a huge round of applause when the awardees are felicitated. May I now request the next awardee in the category, Dr. Sunaja Devi KR. Dr. Sunaja Devi. Okay. May I now request Professor T.S. Mahesh, the next awardee in the category, to be on the dais to receive the award. Professor T.S. Mahesh. May I now request Professor T.S. Mahesh, the next awardee in the category, to be on the dais. We move to the next awardee, Dr. Shashidhar Somappa. Dr. Shashidhar Somappa, who is a scientist F and professor, CSIR, National Institute of Interdisciplinary Science and Technology, Dr. Shashidhar Somappa, to receive the award. Many congratulations. Sir has 32H index, 100 publications, and 7 patents on his name. A big deal. Let's give a huge round of applause, ladies and gentlemen. Many congratulations, sir. May I now call upon the next awardee in the category, Dr. Nirmal Majumdar. May I now call upon, okay. Because of some transportation issues, some of our awardees are unable to present at this moment. They may stuck in their train or maybe flight somewhere. So sir is also not with us. So may I now call upon the next awardee in the category, Professor Sanjeev Patra. Professor Sanjeev Patra, who is a professor, Department of Chemistry, IIT Kharagpur. Sir has 27H index, 65 publications, 1 patent, and 2000 plus citations on his name. Many congratulations, sir, for contributing to the scientific fraternity. Let's give a huge round of applause. Many congratulations, sir. May I now call upon our own, the organizing secretary of the event, Professor Ranjan Khut. I am the former student of Madam also, the person who is behind all of this. As sir has rightly said, the person who has tirelessly made the efforts to make this event a success. Let's give a huge round of applause to Ranjan Khut Madam. Professor Ranjan Khut, Professor, Department of Chemistry, Saurashtra University. Madam has 16H index, 800 citations, 6 patents, and over 100 plus publications on her name. Many congratulations, Madam. You have contributed significantly to the scientific fraternity. You even have made a tireless efforts to make this event a huge success. And because of that, we all are here today. So many congratulations. Let's give a huge round of applause to her contributions for not only the scientific fraternity, but for event also. May I now call upon the next awardee in the category, Professor Hitesh Patel. Professor Hitesh Patel, who is a professor and head, Department of Chemistry, Gujarat University, Ahmedabad. Dr. Patel has 170 plus publications, 32H index, 4,000 citations, and 32 out of them 6 are granted. The number of patents is very huge, 32 patents. Ladies and gentlemen, you might be knowing the significance, how big the number is. So many congratulations, sir, for your contributions to the academics and to the research. Dr. Hitesh Patel, Professor in Head, Department of Chemistry, Gujarat University. Let's give a huge round of applause. Next awardee in the category, Dr. Naval Kapuria. Next awardee in the category, Dr. Naval Kapuria, Associate Professor, Department of Chemistry, BKNMU, Bhakt Kavi Narsimeh Mehta University. He is a proud alumni of the Department of Chemistry, Saurashtra University. So let's give a huge round of applause to Dr. Naval Kapuria. Welcome, sir, to your own department. He has 7 patents, 50 publications, 19 H index, and 1,000 plus citations. So many congratulations, sir. Ladies and gentlemen, let's give a huge round of applause. Next awardee in the category, may I now call upon Dr. Priyanka Shah. Congratulations, Naval sir. Dr. Priyanka Shah, who is Assistant Professor, School of Forensic Science, National Forensic Science University, Gandhinagar. Madam has 22 H index, 2,000 plus citations, 6 patents and 70 plus publications. Many congratulations, madam, for your contribution to the field. Let's give a huge round of applause. I now call upon the next awardee. Happy to announce the name of my senior, Professor Ramesh Kothari, who is a professor and head, Department of Biosciences, Saurashtra University, Rajkot. Sir has 20 H index, over 72 publications, 1,000 plus citations, and 3 patents on his name. Sir is a receiver of many awards and honors, including the USA and UK Travel Awards. So, sir, many congratulations for your consistent contributions to the field of the science, to the Saurashtra University Department of Biosciences. So many congratulations. Let's give a huge round of applause to Professor Ramesh Kothari. Thank you so much, all the dignitaries. I once again congratulations all the awardees, all the eminent scientific academic personalities for their wonderful contributions and inspires us to do the more better in the life for the society as well as for the nations. Now we are moved to the next category of the award, that is a bronze medal awardees. In this category, may I now call upon the first awardee in the category, Dr. Navya Rani M. May I now call upon the first awardee in the category, Dr. Navya Rani M, who is from Nagarjuna College of Engineering and Technology, India. Dr. Navya Rani, who has 40 publications, 17 H index, around 900 citations and 12 patents on her name. Madam is also having a membership and affiliations to various professional associations. Many congratulations, madam, for getting the bronze medal in the category.
I must mention, this is a lady who it was possible to hold last RASAYAN-23 in a very big way. It is she who did very well, and Rangappa is a hero, she is a heroine, they are wife and husband.
Nice to know the story. Huge round of applause to both of them. Many congratulations, madam and sir. May I now call upon the next awardee, Dr. Mahesh B. May I now call upon the next awardee, Dr. Mahesh B, who is from JSS Academy of Technical Education. He has 17 H index, 1,000 citations and 80 publications. Sir has a membership and affiliations in various professional associations. Dr. Mahesh B. Many congratulations, sir, for achieving CRS Bronze Medal 2026. Let's give a huge round of applause. Congratulations, sir. Thank you so much all the dignitaries for giving this award. May I now call upon the second awardee in the category, Dr. Soumya De. Dr. Soumya De. The next awardee in the category, Dr. Soumya De, who is the Department of Biosciences and Biotechnology, IIT Kharagpur, India. Dr. Soumya De, who is from Department of Biosciences and Biotechnology, IIT Kharagpur.
I am very happy to announce that he has joined the editorial board of CRS. Big round of applause to him. Big round of applause.
Wonderful to know. Huge round of applause to the editorial board member of the CRS, Dr. Soumya De from IIT Kharagpur. He is from Department of Biosciences and Biotechnology. Many congratulations, sir, for your achievement. Next awardee in the category, may I now call upon Dr. Richa Tomar. Dr. Richa Tomar. Very humbly I request Honorable Registrar of the Saurashtra University to be on the dais, please, to join all the dignitaries to give away the awards. Registrar sir, may I now call upon to the stage. Thank you, sir, for joining the dignitaries on the dais. May I now call upon Dr. Richa Tomar. Okay. May I now call upon the Head of Chemistry Department, Saurashtra University, Dr. U.C. Bhoya, the person without whom the event has not been shaped off, the person who is behind the curtain, Professor and Head, Department of Chemistry, Professor U.C. Bhoya. Sir has 12 H-index, 600 citations, 78 publications. Sir has membership and affiliations in the Professional Association. Sir is continuing the legacy of the Department of Chemistry currently. So many congratulations, sir, you and your entire team for wonderful organizations of this international symposium as well as this award ceremony. Let's give a huge round of applause. May I now call upon the next awardee in the category, Dr. Gautam Ghosh. The next awardee in the category, Dr. Gautam Ghosh.
Gautam Ghosh has discovered something new. Of the peptides, he has shown the ferroelectricity generation. Big round of applause to him. A recent addition to big science.
Let's give a huge round of applause. May I now call upon the next awardee in the category, the person who is from Department of Chemistry, the alumni, Dr. Yashwant Singh Jadeja. My former colleague and friend, Dr. Yashwant Singh Jadeja, who is Associate Professor, Department of Chemistry, Marwari University. Sir has 14 H-index, 60 publications and 500 citations. Many congratulations, sir, for your contribution to the field of academics. Sir is currently handling all research criteria, research-related activities at the Department of Chemistry, Marwari University, Rajkot. So many congratulations, sir. May I now call upon the next awardee, the own member of the Department of Chemistry, Dr. Mrulan Ambasna. The alumni of this Department of Chemistry, Dr. Mrulan Ambasna, who is Assistant Professor, Department of Chemistry, Forensic Science, Bhakta Kavi Narsimha Mehta University, Junagadh. May I now call upon Dr. Mrulan Ambasna. May I now call upon the next awardee, Dr. Praveen Kumar Patel. May I now request the next awardee, Dr. Praveen Kumar Patel, Head and Associate Professor, Industrial Chemistry Department, VP and RPTP Science College, Vallabh Vidyanagar. Dr. Praveen Kumar Patel. Sir has 11H Index, 600 citations and 62 publications. Many congratulations, sir, for your wonderful contributions to the academics, to the fraternity of the science. All these categories are bronze medal awardees, the academicians who have contributed significantly to the field in terms of either patents, publications, in terms of their research. So it is a very big thing for all of us and inspiring things. So many congratulations to all the awardees. May I now call upon the next awardee in the category, Dr. Mukherjee. Dr. Mukherjee, who is an Associate Professor, Vidyasagar University. Dr. Mukherjee. Dr. Channa Mukherjee, Assistant Professor. A very huge round of applause to the madam. She is doing very great in the field of academics. She has been doing a wonderful task. So huge round of applause to Dr. Mukherjee from Vidyasagar University. Ladies and gentlemen, we will get the high tea very soon. So we must not exhaust of clapping. So next award in the category is a Best Thesis Awards. We would like to appreciate all the young researchers who have started making a huge contribution to the field in this category. So,
This was there in our, file for 4 years. This year only it happened because of Kunt. She could make all the efforts and she brought it happen. And she made it happen. She brought everybody here. Thank you.
okay, Dr. Pooja Bhanderi. May I now call upon Pooja Bhanderi to please be on the dais. Pooja madam has also worked tireless to make this event possible. We have one WhatsApp group and she used to float all the messages before the events, what to be done and what not to be done. So thank you madam for your tireless efforts, even for this shaping of this event. Many congratulations madam for your wonderful work during your PhD tenure. Dr. Pooja Bhanderi, Department of Chemistry, Saurashtra University, Rajkot. May I now call upon the next awardee in the category, Dr. Pooja M. Dr. Pooja M. Okay. This award category is a Best Thesis Award. The researcher who have made some significant contributions to the field, in that way their thesis reflect that. So this is a Best Thesis Award. Under that category we have presented first award to Dr. Pooja Bhanderi, Department of Chemistry. Next Best Thesis awardee is Dr. Pooja M. Dr. Pooja M. Dr. Pooja M from Manipal Institute of Technology. All these are young researcher, the budding researcher who has started contribution to the field with their thesis. So many congratulations. Let's give a huge round of applause. They have already got the inspiration from all the eminent personalities and scientific fraternity. The next awardee in the category, Dr. Suman Patra. Dr. Suman Patra, who is from Vidyasagar University, West Bengal. Okay, Dr. Manikanta PN. May I now call upon the next awardee, Dr. Manikanta PN. Vishweshwarya Technology University, Dr. Manikanta PN. The thesis title is, which is mentioned to the slide, it is pyrolysis assisted CNT based functional coating for a space and other applications. These young budding researchers have contributed significantly during their research, which is reflected into their thesis and thesis title. So many congratulations to the awardee for the Best Thesis Award category, Dr. Manikanta PN. Let's give a huge round of applause. Next awardee in the category, Dr. Jaideep Paul. Dr. Jaideep Paul. Next awardee in the category, Dr. Jaideep Paul, who is from CSIR Center for Cellular and Molecular Biology, CSIR CCMB, Hyderabad. The thesis title is Structural and Functional Study of DRB3 in Plant RNAi. Those who are from life sciences, they might be knowing the significance of the work title which is mentioned for the thesis. So it has been a huge contributions to the budding researcher, Dr. Jaideep Paul. Many congratulations, Doctor, for your wonderful contribution into your research thesis. Let's give a huge round of applause. Next is, may I now call upon Dr. Akanksha. May I now call upon Dr. Akanksha. Next awardee in the category of the Best Thesis Award, Dr. Akanksha. I request next awardee to be ready, Dr. Akhidas. I request next awardee to be ready, Dr. Akhidas. Dr. Akanksha, who is from Punjab University, Chandigarh, with the thesis title of NMR Dynamic Study and a Nano Inhibitor Development for RNA. Dr. Akanksha from Punjab University, Chandigarh. Many congratulations. Next awardee in the category, Dr. Akhidas. Next awardee in the category, Dr. Akhidas. Next awardee in the category, Dr. Nupur Nagar. Dr. Nupur Nagar. Next awardee in the category, Dr. Nupur Nagar, who is from IIT Roorkee, with the thesis title of Molecular Insights into Binding Interactions and Conformational Landscapes of the Chemokine Proteins. So again, the life science fraternity will come to know what the significance of the title is. So many congratulations, Dr. Nupur Nagar, for your wonderful work during your research tenure. Let's give a huge round of applause. Many congratulations to all the budding researchers. They have already got the inspiration and started working towards the goal to rise the India, to rise the society. Ladies and gentlemen, with this, we have came to an end of the insightful, inspiring and memorable Dr. Somen Patra is there in the hall. Dr. Somen Patra. Before we conclude this session, may I now call upon all the awardees to be on the dais for the group photo. May I now call upon all the awardees for the group photo, and then formally we conclude our session with the national anthem. So I request all of you to remain present in the auditorium, but I request all awardees to be on the dais for the group photo before we conclude the session. Thank you so much, all the dignitary. We are very much grateful to you. We can play the music. नहीं पर त्यारे तो म्यूजिक करे अब फोटा में શું બોલવાનું. Many congratulations to all the awardees.
class now. I had to say that.
Hello. Okay. Hello. Yeah, very good afternoon to all of you. And let me thank CSR for this wonderful opportunity and for the honor. And since my time starts now and there is very little audience here, but it's their loss because first part of my talk was beautiful pictures of Nainital, which I wanted to show you. As you know, currently I am the Vice Chancellor of Kumaon University, Nainital. It's a very famous tourist place. Hello. So I have two affiliations. I am basically from University of Delhi and currently on deputation with the Kumaon University Nainital. So can you please turn off the light? Light off kar dijiye. So the university was established in 1973. We celebrated its golden jubilee year. And this is the administrative block of Kumaon University Nainital. And you can see it's a lush green area, dense forest. We have 10 faculties, 33 departments, and student strength is about 70,000. 83 colleges are affiliated to it. And my residence is somewhere to this side. And when I joined the university, I was thinking to go for a walk to the market side because I am alumnus of this university. But I was not allowed. I said, I was told that no security guard will follow you. I said, I don't need security guard. Next morning, I was told, sir, bina guard ke mat jaiye. I said, no, I will not take. Then they said, please don't come out at odd hours. Reason being, we have couple of leopards to this place. On and off, you can have their darshan. And this is the beautiful city called Nainital. And if you visit sometime, people will say Tallital and Mallital. So the lower end is called Tallital, the upper end is called Mallital, and this is the middle side. So this is where our main campus is located, and this is where my office is there. And we have another campus that is called the Bhimtal campus, which is about 1 hour drive from Nainital, and this area is a plain area called Haldwani, and train comes up to here. From there, it's about 1 hour drive to the hills. Third campus, we recently started construction, which is about 12 kilometers from the headquarters, and that's the third campus what we are starting now. It's cold place. It doesn't snow that much now, but good old days when I was a student there 30 years back, it used to snow heavily. So this is how it looks in the winter, and this is how it looks in the night. It's a mesmerizing picture. So joining Kumaon University, I thought why Vice Chancellor don't take classes, so I started teaching. So I take 2-hour class every week to teach MSc students. And this is the same classroom where I studied actually, where I was a student in 1993. This is for younger generation. Before going to the classroom, I still make my notes, so I still read. And this is one of the beautiful collection. This building was constructed in 1882. The museum was established in 1987. It has very old collections. And this is how the museum looks like in 2023. And this is how the museum looks like now, completely renovated in 2-3 years. This Nanny Lake has the fish called snow trout, the native fish. But the snow trout got extinct about 30 years back. And as a science student, when I joined Nainital, I thought we must work on this. We established at DSB campus, in my campus, and a professor was given the responsibility to try to revive the fish at the campus first, and if that works, take this to the lake side. So finally, we could revive the fish in our experimental setup, and now it has been taken to its natural habitat, and there is no mortality at all. So can I have this presentation, please? This is switch on. Yep, no. So the basic chemistry lecture which I will be coming bit later, I will use few of those slides. I will inform you what I am going to talk on that area. So, as a human, for the treatment of sickness, we use a drug molecules, right? The first organic compound that was synthesized was urea in 1882. Before that, there was no organic molecule known. Okay, this comes. So now we have the experimental setup in the lake, and we revive the fish. And because it's a leadership award, so we could save about 5 crores per year from printing jobs. These are the old rates, these are the new ones. Not only that, the honorarium pay to the employees was 18.36 lakh was brought down to 5.3 lakhs. So we saved quite a lot of money, and that money was pumped for the research related activities. This is the maths building. When I was a student there, it was like that. It vibrates actually if 3-4 people goes inside, it vibrates. So this is the new building we constructed. I've been there now close to 3 years. So we got Meru study of 100 crores as Saurashtra University got. We got ANR peer project of 100 crores. We are establishing a new campus, save this much of money. We are giving 2.5 lakhs rupees per year to every faculty for research purpose. Conference support to the students, PhD students, and the faculties. Free education to orphan student, SSB training. 12 academic blocks we constructed. 4 skill center, 38 cash promotions, 7 new appointments, indoor firing range, and rowing simulator. For that I got the NCC colonel rank. Though we did this much, there was no work at VC office and residence. This is what the problem comes sometime. People make issue that vice chancellor apne ghar mein itna kaam kare, so we didn't do that. So in drug discovery, till the mid of 19th century, for the treatment of sickness, we used to rely on the natural products. The first oldest written evidence for the medicinal plants uses for the treatment of sickness is found in the Sumerian clay slab, this is what it is, and it is about 5,000 year old. It comprises 12 recipes of the drug preparation referring about 250 various plants. But synthetic chemistry starts from here. This is the first synthetic drug that was reported in the literature. Now let me tell you, till 1900, what was the average life at birth in India? It was about 23 years. Now this has gone up more than 66 years. So it means the chemistry and biology interface has played a pivotal role on this. When we talk about drug discovery program, this is one of the golden slide every medicinal chemist would like to show you, so that at the end of the talk you don't ask the question whether you have developed a drug or not. If you want to work in this area, out of 10,000 compounds, one compound comes to the market as a drug. It takes 16 to 18 years, and average cost of one drug development is about 1 to 3 billion US dollars. There are few approaches by which the drug discovery program is done. I will be talking a little bit about the hybrid drug discovery. I hope you people have seen this plant. This is called Sadabar in Hindi. And from this plant, 120 alkaloids have been isolated. These are the two structures isolated from the same very plant, and both of these compounds shows poor anti-cancer activity. Same plant generated two more molecules wherein these two molecules are hooked up by a covalent bond. This is called vincristine or vinblastine. And vincristine and vinblastine was approved by US FDA for the treatment of leukemia in 1963. What does it mean? You had two pharmacophores, pharmacophore A, pharmacophore B. Both were poor anti-cancer compounds. But when you hook up these two like this, it became a drug. So it means what? It is the hybrid technology, right? And nature has it, but synthetic medicinal chemists did not utilize this concept till late 1990s. So before going to the talk, what is my training on medicinal chemistry? During my PhD, I worked on non-covalent interaction. There was no medicinal chemistry. Afterward, I joined pharma industry, work on process chemistry, wherein my job was to improve the synthetic protocol to take up in the commercial plant up to 100 kg scale or 200 kg scale. During my first postdoc at Indiana University, we modulated the reactivity of the ene dyeing using metals, more academic kind of work. 1 year I worked at Purdue University, that was FTA's inhibitors, typical medicinal chemistry work, but I did not copy this work in my career afterwards. So when I joined Naipur Mohali in 2002, my director wanted me to work on malaria. Since I am PhD from CDRI Lucknow, I knew about the malaria in two contexts. One, this molecule called artemisinin was heavily being studied by a group called Dr. Chandan Singh at CDRI Lucknow, and another molecule I studied during my MSc course, this is called chloroquine, which is about more than 100-year-old molecule. So as a beginner, if you want to work on this molecule, no funding agency will fund you. So I thought, let's consider something related to this. But if you want to work on this molecule, you have to compete with a big established group. So I did a literature search. In 1999, this molecule was reported. This is called tetraoxane. We submitted a proposal to CSIR making these kind of tetraoxanes, proved that it can work. But in 2008, we started working on the hybrid molecules of these two antimalarials, making these kind of hybrids. When these kind of hybrids we made, the first, I will show you this example. So this is the hybrid of aminoquinone and triazine. And what we proved here, this is the IC50 value of chloroquine. This is the IC50 value of our compound. So what we proved, that if you make a hybrids, you can have better antimalarial activity than the individual counterpart of these hybrid molecules. So as a medicinal chemist, we substitute this nitrogen by CH and made these kind of molecules. Now it is the pyrimidine and aminoquinone counterpart. Okay, when we did this, the activity was up to 7 nanomolar. So once you have that good activity, people will ask, what about in vivo activity? So in vivo, the treatment was 80%. We could prove that in malaria model. We published this paper in 2012 in ACS Medicine Chemistry Letter. One fine morning, I received an email from Professor Kwang Soo Kim from McLean Hospital. He was interested to screen these molecules for Parkinson. So malaria and Parkinson disease has no correlation. Why he wanted to do that? Because the paper published in Nature 1987 concludes that chloroquine and related molecule can retard the progression of Parkinson disease. There was no further study on this. What Professor Kim did at that time, he screened 960 FDA approved drugs, found few hits. Out of these few hits, the structure of two molecules I have shown it here. If you look at this, both has 4-aminoquinoline pharmacophore. And based on this study, what they proved actually, these molecules activates the NERV1 receptor in our brain. When NERV1 receptor is activated, the death of the dopamine neuron is arrested. So dopamine neuron has a function to produce dopamine in your brain. That makes you happy. So if the dopamine concentration in your brain is less, you will have Parkinson's disease. To show you pictorially, this is the normal human being. You have a dopamine here. You have alpha-synuclein protein, looks like this. But when you have the Parkinson's disease, the dopamine is gone. You have a movement disorder. At the same time, this protein undergoes for misfolding, forms this kind of lumps. So if you want to work on the Parkinson's disease, what you need to do? Stop the death of the dopamine neuron, number one, or stop the aggregation of this molecule. Based on this published result, this Journey with Parkinson 2015 wrote that clearly there is a real potential for future application moving from rat model of Parkinson to one day testing clinically in humans. This is what I did in 2015. We started collaborating with Professor Kim in 2012. Initially we got few hits, not very good. Then the massive structure activity relationship studies on this molecule was started, and we synthesized more than 700 compounds. And the project was funded by MJ Fox Foundation 2014 to 2016. Now, the chloroquine has, time reduced?
No, not reduced, but you have to stick to that.
Okay. Just 5 minutes maybe, maximum. Okay. Okay, chloroquine is 50 micromolar and our compound is 0.5 nanomolar. Okay. So I will skip this also. But what I want to show you here. So this is the full length of NERV1 ligand bind domain. Our molecule activates the NERV1 5 times better than chloroquine. And this red dot is the dopamine neuron. When this is treated with these two compounds, red dots are gone. It means the dopamine neuron dies. But when this is treated with chloroquine, you can see little bit red dot appears. But when this is treated with our compound, 67% of the neurons survive. So in animal model, this is the cerebrum part of the mice brain. This is the mice brain with Parkinson. This is when it is treated L-DOPA, almost same. But when this is treated with our compound, you can see first and the fourth one, same. So what we prove from this study, that Parkinson can be treated. This is what we did. So it stops the aggregation of alpha-synuclein. So it is doing two things now. One, stops the death of the dopamine neuron since it activates the NERV1. Number two, it stops the aggregation of alpha-synuclein. Third one, autophagy. Autophagy is the concept for which the 2016 Nobel Prize was given to Japanese professor. So if you look at these are the red dots, it means autophagy. When this is treated with this compound, red dots gone, autophagy stopped. But when this is treated with chloroquine, 22% autophagy was stopped. But when this is treated with our compound, 64% autophagy was induced. So this appeared for the phase 1 human clinical trials. From the Indian academia, this is the first molecule which got US FDA approval. I will skip this. In 2023, the first human phase clinical trial were declared successful by these companies. So this is what it was written in 2015. 2023, that became a reality. So these are the group of students who made this story successful. Not one molecule, we have 2 more molecules in the pipeline. This is the website of Hanol Biopharma, which shows our compound has cleared phase 1. Now it is in the phase 2. The story was reported by Bloomberg, Wall Street Journal, and the Parkinson News. It says this group of scientists from Harvard and University of Delhi did this work. Couple of slides. After joining as a vice chancellor, we are still trying to, be alive in the academia. So we have published quite a lot of paper in this. We work on different areas also in the sustainable synthesis, because in Parkinson 2012 we started working. 2023 we got Nature Communication, only 1 paper. So you cannot keep your students working when you don't get a paper. So we work on sustainable synthesis also. And these are my collaborators, and these are the funding agencies. And these are the group of students who made what I am today. These are current batch of students, but most of them will be gone by the time I come back to Delhi University. Thank you very much, and this is my village from where you can see the complete Himalaya. Thank you very much.
Sir, thank you very much for a wonderful talk. The molecules are interesting. So synthetic approach is very interesting. I'm basically organic chemist, so I understand the kind of pen you would have taken. And Manoj, we were talking how nice work it is. So that's the kind of work one would expect. So you deserve more than this award, sir. You deserve more than this. Hopefully you'll get many more. Thank you, sir. Thank you very much. Yes, sir. Sir, we would like to, the way the Nainital is placed geographically, very interesting. So we, CRS people approaching you for the next conference. Yes. Most I think all of you will come. Okay. And we will try to get the, I spoken with sir also. Yeah. Would you like to come to Nainital for the next conference? No, Kate is fixed already. Yeah. So thank you, sir. I think you are waiting. He is waiting for you. Sir, 1 second. Sir, you should be felicitated. I'm sorry. It's my mistake. Ladies and gentlemen, we have another a stalwart in the field. Now we have Professor Bhange, who is a VC of MS Baroda University. Sir, dice is yours, sir.
See the okay? Okay? Fine? Yeah.
Battery is low.
So good afternoon, and first of all, thank you organizers for inviting me to deliver talk here. Actually, I have again two affiliation. One is from Institute of Chemical Technology, Mumbai. I am on lean to the MS University, Vadodara as a Vice Chancellor. So I will today talk on the catalysis using carbon monoxide, carbon dioxide, and how we can prepare various value-added products from these gases. Because quite often, it's not working. स्लाइड नहीं हो रहा, स्लाइड मूव नहीं हो रहा. Okay, so at ICT we are working on the sustainable catalysis involving the gas-liquid reactions. Most of our work is focused on gas-liquid reaction, and as you know that today carbon dioxide is a big issue. So how we can utilize carbon dioxide into value-added product is also topic of our research. We are working on preparation of various homogeneous complexes and developing homogeneous catalysis in which homogeneous catalysis can be separable also. So these are our strategies, and over the period we have published lots of paper in the sustainability in various journals like Green Chemistry, ChemSusChem, ACS Sustainable, and many more organic chemistry based journals also. But basically catalysis related to sustainability is our approach. So today I have taken a topic on carbonylation first, and if time permits, we'll go for the carbon dioxide utilization. As you know, carbon monoxide chemistry is well established for industrial application, and today all acetic acid is coming from the carbonylation of methanol. And industrial scale synthesis of carbon dioxide is possible, but when it comes to small scale synthesis, everyone is afraid because carbon monoxide is a toxic, very difficult to handle, and people are requiring lots of sophisticated instruments. So therefore, we have developed different strategies for carbonylation. For example, carbonylation can do variety of functionalities, like you can prepare esters, amides, thioesters, biaryl ketones, so many molecules you can prepare, but again, to react carbon monoxide, we need specific catalyst, and that catalyst is the heart of any catalytic process involving carbon monoxide. So over the period, our group developed different strategies in which one can use carbonylation with gaseous form of carbon monoxide, non-gaseous form of carbon monoxide. When I want to say non-gaseous form of carbon monoxide, it means that we can use surrogates which generates carbon monoxide in situ. In this case, you can have gaseous CO2, or you can also have alternative modes of carbon monoxide in which you can do the cyclization reactions. So you can see here, whatever the red CO you can see, it is coming from the gaseous carbon monoxide. So the strategies which we have developed, I would like to discuss today. Now when you want to avoid gaseous CO, definitely certain molecules can release the CO in situ, and those are called as CO surrogates. And some of the popular CO surrogates are methanol, formaldehyde, formic acid, formate esters, formamide, even metal carbonyls one can use, or one can have N-formyl saccharin. So all these molecules, with the help of catalyst, can release carbon monoxide. And that carbon monoxide, with simple glassware, you can do the carbonylation reaction. You don't need any high pressure reactor. And that is the research work which I would like to talk today. Now, when you want to have CO surrogates, there can be two strategies. there can be two-chamber glass reactor in which one chamber is generating CO and it goes to the another chamber. Or you can have in situ CO generation and carbonylation together. So that is also possible. So based on that, I would like to focus on what type of reactions which we have developed. For example, here we have developed palladium on carbon, just palladium on normal activated carbon we have deposited, and we could able to do the N-formylsaccharin as a CO surrogate. So this is N-formylsaccharin. This CO will transport here to prepare phenyl esters. And the catalyst is palladium on carbon. So what will happen? Phenol and iodobenzene can be reacted in presence of N-formylsaccharin. We did it at gram scale synthesis also. Palladium on carbon, simple base like sodium carbonate, and you can prepare phenoxycarbon esters very easily. And this catalyst is recyclable. Just separate it, palladium on carbon, so there is no need of specialized organometallic palladium phosphine based chemistry wherein palladium is soluble. You can just separate like a heterogeneous catalysis, and one can do the carbonylation reactions very easily. Now for carbonylation reaction, when you look for the previous reaction, here we need iodobenzene. And iodobenzene is an expensive component, again halogen. So it's not environment friendly. So we have developed another strategy in which you can take boronic acid, CO, and here we have developed dendrimeric palladium nanoparticles, and again same carbonylation surrogate, that is N-phenylsaccharin, and you can do the biaryl synthesis very easily. You can prepare biaryl ketones using such type of specialized N-palladium on dendrimeric silica. So what happens here, you can prepare biaryl ketones very easily. You don't need Friedel-Crafts reaction. Otherwise, you know that if you want to prepare traditional way of preparation of biaryl ketone, you need Friedel-Crafts reaction. And here it is possible without aluminous salts formation. And you can have palladium on carbon or dendrimeric silica. Here we have shown that how you can prepare the biaryl ketone. For example, many commercially important molecules we have taken, and we could able to do the carbonylation reaction without any halogen, and just boronic acid is coupled with the help to prepare the biaryl ketone. So catalyst is heterogeneous, CO surrogate is used, recyclable, and we showed wide range of substrate scope for this reaction. You can see lots of different types of substrate can be coupled. So you have to take corresponding biaryl aryl boronic acid, and you can do the coupling reactions very easily. Now same approach we have continued, and here we have used the green solvent like propylene carbonate, and N-phenylsaccharin is N-formylsaccharin is our surrogating agent, and one can do biaryl ketone synthesis very easily with such type of reaction. Again, gram scale synthesis, catalyst is recyclable. Then here we have developed another strategy. In this case, we have taken dicobalt octacarbonyl as a CO surrogate. So CO surrogate is changed. Now it is metal carbonyl. And you can have coupling of iodobenzene and phenol or amine. If you take phenol, you will get esters. If you take amine, you will get the amide. And again, you can have a catalyst which is a recyclable, and you can prepare such type of carbonylation chemistry without use of carbon monoxide. So several reactions we did, and important part in this particular reaction, we get unusually high turnover number, like turnover numbers are in the range of 10 raised to 4. So you can see that very high turnover number. So since this catalyst is homogeneous, but it gives huge turnover number, so we need not worry about separation and recyclable strategies, because catalyst is in very small quantity. So you can see the high turnover numbers which is there for this particular reaction. Even phenoxycarbonylation gives very high turnover number, and that's why this particular protocol is useful. We showed gram scale synthesis also, and we have synthesized some drug molecules using this particular strategy, that is bitol and lintrin. Then continued with the same CO surrogate, that is dicobalt octacarbonyl. We did carbonylative Suzuki-Miyaura coupling reaction. So this is a traditional Suzuki-Miyaura coupling partners, and if you introduce metal carbonyl with palladium catalyst, you get Suzuki coupling along with CO insertion. So you get biaryl ketones, and this is also possible. We showed this, that you can prepare such type of biaryl ketones using carbonylative Suzuki-Miyaura form coupling. Again, catalyst required is very small quantity, and it's in really ppm, ppb level catalyst is required. So this is highly active catalyst. Again, we showed POP pincer xanthos catalyst, in this case alkyne and 2-iodophenol was coupled together to produce here the synthesis of flavons. So you can see that synthesis of flavons was possible with the help of such type of carbonylating surrogate, that is dicobalt octacarbonyl. So this is the catalyst structure which is used. Again, this catalyst is highly active. Now, so far, if you notice that we have used palladium catalyst, and palladium is well known for the coupling reaction. But now here, we could able to replace palladium with simple and cheaper catalyst like nickel. Now nickel is also active for the coupling reaction, and nickel cost is very negligible. So we showed here that you can have nickel on alumina as a catalyst, and you can do the same chemistry, and it replaces expensive palladium catalyst. So again, it's a very useful strategy for the carbonylation reactions. Again, magnetically separable, another nickel catalyst, but reaction is different. We can show that phenoxycarbonylation also you can do with the nickel on iron, which is magnetically separable catalyst. Now, this is so far we did is a monocarbonylation. Now, whether we can introduce two carbon monoxide molecules together, and that is called as double carbonylation. So, here you can see that two carbon monoxide molecule and simple molecule like secondary amine and alcohol were taken together, and we have prepared here oxamates. Traditionally, by conventional organic synthesis, preparation of oxamate is a very difficult task. Here we could able to do this with the help of palladium catalyst and ligand-free, base-free. There is no co-catalyst is involved, and we can do the oxamate synthesis. Importance of this oxamate synthesis in the ethylene glycol synthesis, which is a commercially important product. For example, you can take primary amine and alcohol and prepare the corresponding oxamate. And this oxamate, you can do the hydrogenation, you can get the ethylene glycol, and all these molecules are coming back. So when you see the net reaction here, you can have carbon monoxide, hydrogen, and half oxygen giving you ethylene glycol. So this is a very good alternative route for ethylene glycol. Otherwise, if you want to prepare ethylene glycol from all these gaseous molecules, you need very high pressure and temperature. Here it is possible at relatively ambient conditions. Then we showed that we can prepare two carbon monoxide molecules together. Now, here first time we could able to show that you can also couple three carbon monoxide molecules together. For example, this is tertiary amine. This is monocarbonylation, well established. I showed you that with palladium and with nickel you can do it. Double carbonylation also I showed you, and I showed you its importance in ethylene glycol synthesis. Now here three carbon monoxide molecules are coupled together to prepare the class of molecule which is known as oxomelanamide. And this is very much easy, and you can do the single triple carbonylation reaction. Additionally, you are also breaking the carbon nitrogen bond. So this is a CN bond activation reaction and triple bond carbon, triple CO formation. So we prepare many novel molecules using this particular strategy, and many triple carbonylated products were prepared for the first time. So this is the possible reaction mechanism for this particular reaction. Then we are also working on other areas of which I would like to focus is on that we prepare ionic liquid and use it for different esterification reactions. Then, in this case, we have prepared alpha beta alkylamides using palladium catalyzed oxidative de-alkylation and carbonylation reaction of tertiary amines with terminal alkyne. So what we did here, terminal alkyne, furfural is act as a CO donor here. So another surrogate molecule, that is furfural. Furfural is biomass-based product, and you can do the carbonylation reaction, and again this is a recyclable catalyst. So I will skip through quickly. Recently we also showed that you can do the hydroformylation of eugenol. This is a biomass-based olefin, and you can have very selective hydroformylation product with very good N/iso ratio, and this is biphasic reaction in which catalyst can be recycled. Again, we did another biomass-derived olefin, that is R-carvon, and we could able to do the hydroformylation of R-carvon to prepare the corresponding aldehyde. Then we could able to do the another R-carvon synthesis in which we showed that you can do hydroformylation also and hydrogenation also together. So that is also possible. Additionally, we have also developed hydroformylation of biorenewable allyl benzyl derivatives via nanoporous metal organic framework using rhodium catalyst, and you can see that here allyl benzenes were taken, and you can see that these particularly internal olefins could able to do the hydroformylation to give you the aldehyde product. So that is also possible, and very high turnover number was obtained. Then, as I told you, we are working on CO2 chemistry. We have developed several products based on the CO2 and the catalysis required for the CO2 to different value-added products. So, if you look at this slide, we can see that CO2 to prepare benzimidazole, N-formyl amines, cyclization to cyclic carbonate, again benzimidazoles, and different types of materials which is required for the activation of CO2 is developed by our group. So you can see here bifunctional ionic liquid, so epoxide to cyclic carbonate transesterification with methanol to dialkyl carbonate, or you can have aminobenzonitriles to prepare antihypertensive drug molecules like this. So CO2 chemistry also we have developed in our lab. Again here you can see that we have prepared 2 benzimidazolone scaffold using 2 nitroaniline. So this nitro group is also simultaneously reduced with the PAMHS, and you can have benzimidazole synthesis. Then with the help of graphene oxide catalyst, in graphene oxide we have anchored amino group, and since amino group is anchored here, CO2 can dock here, and you can have epoxide to cyclic carbonate synthesis very easily using this particular strategy. And there are so many synthetic strategies for CH activation or palladium cycle synthesis we have developed. For example, in this particular carbonylation reaction, we have developed a palladium cycle catalyst which gives turnover number of 10⁹, which is the highest turnover number for this particular chemistry. So many things which we have developed. We have also worked on biomass derived molecules and did the catalysis for different biomass derived molecules to develop so many different type of chemicals from the biomass. So I think due to the shortage of time, I would like to wind up my talk, but there are lots of things on biomass derived molecule our group has developed. Thank you very much.
To interrupt, sir, sorry. Though the fantastic chemistry we have been following, everybody knows, most of the organic chemists follow his work, we know, everybody is laughing. So there's a big smile on the organic chemist who follow his chemistry. Sir, thank you very much for accepting our honor and also delivering a fantastic lecture. Thank you very much indeed. Thank you. So, no, on behalf of organizer, we would like to honor sir with some memento. No, that
chemistry, not on exactly
no, organic chemistry. See, carbonylation is not easy. Yeah. Okay, sir. Dinesh. Thank you. Dinesh? Big round of applause to sir, as he has agreed to host one of our conferences in MS Baroda University. So from CRS side, recipients, give a big round of applause. So we have already 2 proposals. Okay, thank you very much. Sir, I have announced it.
Yes, sir. You are welcome. You are welcome.
As a,
When they plan, you are always welcome to Vadodara.
no, as a secretary, it is my job. Whether they agree or not, but I make them to agree. Okay, thank you. Very well done. Now we'll break for lunch and then we'll come back. So next chair, you are the chair, sir. You have to collect all the talks. Your job. I'll help you rather. Yeah. Organizers, please help. Please help him to get the talks.
The list is there.
Please.
Hello, microphone test. Hello, hello.
Hello. Check. Good afternoon, everyone. Welcome back to the post-lunch session of day 1. Before we proceed for the session, I would like to call upon the stage Dr. Rangappa sir and Dr. Piyush Solanki to introduce Professor Pramod Patil sir.
Thank you. Good afternoon, one and all. I thank organizer giving me this opportunity to chair the sessions of stalwarts. And back to the sessions after lunch. Hope you are all charged with some energy now. So, session 2, we are having 2 talks. Plenary lectures. First, plenary lecture 4 by Professor Pramod Patil, Research Director, Vice Patil Education Society, deemed to be University Kolhapur. He is also former Vice Chancellor of Shivaji University, and he is a distinguished physicist and academic leader, internationally acclaimed material scientist, currently serving as a director, as I mentioned, and he has over 34 years of excellence in teaching, research, academic administration with more than 600 publications, and he has supervised more than 51 students, PhD scholars. It is really wonderful to see, and he is also top 2% scientist, and he has more than 800 lakhs fundings for his excellent research accomplishment. And sir, thank you for being with us today, sir. And now the stage is yours. So please go ahead. Thank you.
Thank you very much, sir. Am I audible? Thank you very much. At the onset, I would like to thank Chirantan, RASAYAN, Sanstha for bestowing me with a very prestigious leadership award this morning. I am very happy to be here on the occasion of this international symposium organized by Saurashtra University in collaboration with CRS. And I am also thankful to my friend Dr. Magat, who was after me to come over here offline and contribute to this particular conference. I am really very happy to be here, sir. Thank you so much. Today I am going to talk on this particular topic entitled From Silicon to Perovskite Solar Cells, Evaluation of Photon Harvesting Technologies Towards a Sustainable Future. I have selected this topic because my PhD topic was also on solar cells, and that was on photoelectrochemical solar cells. And till today, that is in 2025, till 2026, I am still working on the same field. There are about 15-20 students, they got PhD in the same field. I remember the first topic I had given to my very first PhD students who was working in the silicon solar cell. He got the efficiency, because this is called the photon conversion efficiency of the solar cell. I remember still it was only 0.0024%. That time the field was new, everything was new, and he got a PhD because there was a lot of science and a lot of characterization was there. But we could not get higher efficiency than 0.0024. In the year 2025, we reached up to 24. So within the last 30 years, we are struggling a lot in this particular field to achieve the appreciable efficiency. That was the point that I wanted to emphasize on. So this field is not very simple. It looks very simple, but it becomes complicated, and therefore it has grown over the last 7 decades. I am going to tell you the story of the 7 decades of research in the photovoltaic solar cells. In the first session, the 2 speakers, they have emphasized on the energy. Anilji Kakadkar has emphasized on the solar energy as well as nuclear energy, and the second speaker also spoke about the thermal energy. This is electrical energy that has come from solar energy. In solar energy, as far as Viksit Bharat 2047 is considered, we have to think differently. We have to look at the photon as a national asset. We should not waste any photon. That is the idea that we have to take forward. And can we convert each house into powerhouse, so that our dream of converting photon into electrical energy for the Viksit Bharat will come true. And if it is the aim, then what exactly we should be doing in India. क्या हो गया? Sorry. Okay. So I am going to start because since there are a lot of PhD students and MSc students, I would always like to start with some very basic and simple things related to solar cell, because this topic may be new to most of the students. So this is the basic operating principle of a typical photovoltaic solar cell, which has been divided into 7 steps. 8th one is the sustenance. So sustenance depends on the 7th step, which is a power output. So in case when we have a photons, that is light energy, then what exactly happens? Absorption, generation, separation, transportation and collection. This is very, very simple to understand. First thing that is happening is the absorption of photon that are coming from the solar spectrum. Then the photon is absorbed, generation of electron hole pairs, then separation of photo-generated electrons and holes, transportation of these electrons and holes, collection at the contacts, thereby we get a power output, and the power output, if it is sufficient, you can go towards sustainable future. It is called as a green energy technology. And everything depends on how much power output that we get here. So this 7th point is very, very important. Other steps, they keep on occurring in the material and devices, but how much power output, that is very, very important, and our sustenance depends on the power output that is measured in terms of photon conversion efficiency. So this looks very simple, right? Sequence is very, very nice to remember and recall some of the things. But the story is not that simple. It is much more complicated because of the losses, which are bottlenecks in that particular aspect. Okay, so if I want to increase the absorption of photons to n times, okay, to its theoretical limit, but what happens? There are reflections, transmissions, thermalizations. So wherever there is one step, there is a loss. Okay, then for generation, we have recombination and incomplete exciton dissociation. If we have to have separation effectively, but there is a bulk recombination, surface recombination, weak electric fields and interface carriers. So you name any step which is an important step to understand the basic operating principle of photovoltaic cell. In that particular step, it is limited by the losses. There are inherent losses that we cannot avoid, but with the intellectual solutions, if you have very good knowledge, if you have some very good idea, you can overcome those ideas, get published those ideas in good journal like Nature, etc. And you can overcome those losses only if you have some intelligent solution. Then for transportation also, this OJ recombination, radiative recombination. For collection, there are series and contact resistance. You cannot bring down the series resistance to 0 because only in superconductivity we bring down the resistance to 0. Otherwise, there is some series resistance and contact resistance. And since for power output, series shunt resistance, field factor, loss. Then for sustenance, again, if at all you get a very good power output, but is it stable? What is the stability in air, humidity, temperature, harsh ambient condition? That is another problem that we have to see. So if you fabricate a device with good power output, then only we can go to the sustenance, provided we overcome those losses. And the research to find the solution to losses, overcome the barriers, and break the bottlenecks is going on since 1955 till 2025. So there is a 7 decade of research has gone into the finding out the solutions to some of the bottlenecks that they are there inherently. Okay, so and during these 70 years of research, more than 600,000 papers have been already published on the different kinds of solar cells. And number of photovoltaic absorber materials investigated, because here I have written only one sentence, absorption. But if you have to have maximum absorption, you know how many materials they have studied? More than 500 materials, distinct materials people have tested. And number of reported device configuration architectures are about 100 with thousands of variation. Why we require 100 device configuration and thousands of sub configurations? Because to minimize the losses and maximize the output. That is the only one thing. So that is the only main area thrust to go ahead in the photovoltaic solar cell. So tomorrow if you want to start work in this particular area, first of all you have to target which bottleneck you would like to target and what solution you have. And do you have sufficient infrastructural facilities in your laboratory to do that particular research? All these questions have to be answered before taking up the research in this particular direction. So I am going to tell the story of 70 years in 20 minutes. I think Sir Elamagas sir is very strict on this timing, so I will be very, very fast. Please bear with me. So these are some of the materials, because these materials are at the heart of the technology. First generation, thin film generation, 3-5 semiconductors, organic materials, then dye molecules, quantum dots and perovskites. Okay. So I am going to cover from silicon to perovskites very briefly, and I am going to highlight only very important points in that. What are the device configurations? It is a silicon. There are 4 or 5 device configurations which are there in the market. Thin film, dye sensitized solar cells, organic solar cells, perovskite solar cells. You can see lot many variations are there, and finally people have reached up to tandem devices where they have got immense success, and they have even broken down the theoretical Shockley-Quasar limit, and I am going to tell you how it is possible. So these are the materials you go. So whenever we select material, these are the parameters which are very important that determines the property of the material. For example, alpha is the absorption coefficient, tau is the lifetime of the charge carriers, and so on and so forth. So whenever you select a material, you have to look at the magnitude of this particular properties and then select. Okay. So I will check. I will tell you next. This is a little bit of device physics. So you have materials. These parameters are very, very important. Mobility, that is absorption coefficient, time, lifetime, thickness, and so on and so forth. And if you put and combine these parameters together, miracle appears. Miracle in terms of physics. Because what is happening in the device depends on these 3 equations. I am not going to explain in detail, but very apparently I am going to tell you that number of electrons and holes after absorption of photons will increase. And that increase depends on G, that is generation rate. That depends on how much is the absorption coefficient, thickness of the material, and many other aspects like light trapping and presence of anti-reflective coatings. But again, there is a negative R. So G is subtracted from recombination level. Recombination rate is electronic property, and Shockley-Reed Hall SRH recombinations are very popular. Less are these recombinations, more better will be your efficiency, more better will be your device. So all the efforts have gone into minimizing this SRH type of combinations, which are bulk recombination as well as surface combination. So surfaces, interfaces and bulk, they are very, very important. You have to fabricate the material in such a way that it should be defect free, otherwise there will be loss. So I will not go into the hardcore this mathematics. And the third parameter that is here, that is called as a diffusion current. If the electrons are generated, they will diffuse away. How much is the diffusion coefficient? That depends on the mobility. So mobility is more, diffusion constant is more. Then the last term is called as a drift current. So diffusion current and drift current, and this drift current depends on the F, that is electric field, which is produced inside the device, and this electric field depends on this Poisson's equation, which is again in turn depends on the charge density. Okay, I will not go into the details, but this F determines the shape of the band diagram inside the device. And what exactly is the band diagram? This is shown here. This is PN junction silicon solar cell, and PN, and if we make a contact, then there is a band bending, and the amount of band bending depends on this field, electric field. Higher is the electric field, which is called as a built-in electric field. You do not apply any field from outside. This field is generated within the device. That is therefore called as a built-in device, built-in potential. So built-in potential depends on ND and NA, that is donor density, acceptor density, and much more physics is there. So this should be as strong as possible for effective separation. So after all these things, you probably get this particular type of IV curves. This is the output in dark without any light. So without any light, you should exhibit, your device should exhibit the IV characteristic like, which is similar to that of a diode, and when we put a light, it should shift into the second quadrant. With this open circuit voltage, I can calculate short circuit current, then fill factor, and many parameters we can calculate from this particular IV curves, and you can have the judgment of how good or how bad is your device. But you know, this is IV characteristic, here I have shown. It is expected that VOC, that is open circuit voltage, is equal to the band gap energy. For example, silicon is 1.1 electron volt, it should exhibit 1100 millivolt or 1.1 volt as a open circuit voltage, but it is not because of the losses. Thermalization losses, isothermal losses, and some of the losses where the photons will not absorb at all. Okay, I am going to tell you and explain more about these, why they are not absorbed, why there is a transmission rather than absorption in the next figure. And because of this, from of course the report is there, from 1975 till 2025, many device configurations have been tested, and in fact there is a race of producing more and more efficient silicon solar cell devices. You can check here, many device configurations people have found out, and those device configurations have different efficiencies. So starting from almost zero till say 47%. But this 47% is for multi-junction. We are not considering any multi-junction. We are considering only single junction. For single junction, it is mostly about 32%. So these are some of the laboratories, probably you will see here. So these are some of the laboratories in the world. They have very good facilities of fabricating the materials and the devices, and they have published very record efficiencies in the world. Most recently, Longi is a Chinese company. They have reported world record high efficiency for the perovskite silicon tandem solar cells, that is around 34%. So this is for perovskite silicon tandem monolithic solar cells. So these are some of the milestones. Therefore, this technology is very important. From 94 to 70, everything, the market was dominated with the silicon. But you know, for one silicon solar cell module fabrication, you need at least 1,000 crores of rupees investment. That production line is so costly that we cannot afford to have it in our university or in our state or in our country, right? And therefore, there is a problem, and people have shifted to some low-cost solar cells. And therefore, from 1980s onward, thin film low-cost solar cells have been fabricated. Very simple dye-sensitized solar cells, which can be fabricated in the college or university like this, and you can have this. So with this, people were thinking about building integrated photovoltaics. So you can fit these solar cells in the curtain, in the table, in the wall, everywhere. So every side of the building will harvest photon energy. Then the era came to quantum dot solar cells, organic solar cells, and perovskite solar cells. And today we are here up to next frontiers. Okay. So I have already talked about these dominant bottlenecks. Okay, so this figure is very interesting, which indicates that I have considered 20 highly cited research groups in the world, what they were doing in 2005 and what they are doing today. They were all doing in different types of devices and materials, but today everybody is working on the perovskite solar cells. That means how attractive is this option, you can understand. And this is our group, Pramod Patil group. We also worked on different things and now finally settled in perovskite solar cells. Very recently we have published in Nature Energy. So this is from 2005 to 14. You can see different colors. All the people, prominent groups, research groups in the world were working on different materials and different device configurations. But after 15, everybody in the world has started working on the same, that is PESC. So these are very prominent indications to all of us. So if we start working on OSC today, nobody will read your thesis or read your paper. How much time I have? I think you have come here, so how much time? 2 minutes? 1 minute over? Okay. Just I wanted to show this, but I will just go ahead and go to the last slides. Here I will just one sentence. Dye-sensitized bottleneck is 15%. Though if you really want to work on dye-sensitized and go beyond 15%, you will get very good grants in that. Voltage loss, long-term stability, dye degradation. Another is polymer solar cell, and I will just bottleneck is 20%. You cannot go beyond 20%, and there is limitation on the stability. So this is engineering, morphology engineering, and then perovskite. I have not touched the main topic here. Anyway, this is the planar perovskite I was talking about. This is the efficiency record. Within the less than 10 years, it has become world famous, and it is very cheap. Even in this college, in this university, we can do this in the lab, and therefore they are extremely good. But still, there are some bottlenecks that we need to break ahead. Sir, one last slide I am going to. This is tandem silicon solar cell, which has very huge absorption, very widest absorption spectrum in the UV, visible and NIR. And 34.85% efficiency has been reported by a company from China, not India. But you know, ID Tech X is one of the premier institute. They have predicted some 12 billion US dollar will be the market in 2035. So there is a lot of futuristic predictions. And you know, while I was living for this Rajkot, I just checked my mail, and I subscribed some of the good amount of perovskite literature. So 1, 2, 3, 4 path-breaking news I got, and all of them are from China. So they are coming to first large size perovskite module, they are scaling up and they are very soon, they will be in the market very soon. So 1 megawatt pilot plant in even gigawatt scale as emphasized by Honorable Kakodkar sir. So perovskite can be fabricated and scaled up, that has been shown by these 4 companies. But where are we? That is a question mark. We are still lagging behind, but not very far behind today. We are up to 24, 25, some very prominent groups in India also working wonderful. They are doing wonderful research in the field of this. So this is a significant step towards a sustainable future, which we can connect to the Viksit Bharat. Thank you so much.
Thank you very much, sir. Thank you very much, sir. I think it is really very difficult to wind up in a short time, and unfortunately organizer has given only 25 minutes. And we can take only any one questions? No questions? Okay. Yeah. Okay then. So I would like to thank Professor for giving overview about solar cells development from various materials to latest challenging champion material perovskite materials. Thank you very much, sir, for your wonderful talk. Yeah. You can contact him during dinner time or any other free time. Yeah. Sir, any memento for him? Yeah. Sir, just please come over the dais to accept memento.
We are going to felicitate him on behalf of the organizers, sir.
So let us move on to another legendary talk by Professor Ranjit Kumar Verma. Professor is distinguished chemist, visionary academic leader, and a pioneer in popularizing thermal analysis in India. He is founder Vice Chancellor of Mangera University and former Pro Vice Chancellor of Patna University. He has devoted over 4 decades to advancing inorganic chemistry, analytical chemistry. He has pioneering research on nanoferrites, aluminate spinels, chromides, and other thermo-oxidative degradation edible oils. He has earned more international recognition for this work. A former secretary of International Confederation of Thermal Analysis and Calorimetry, a fellow of Royal Society of Chemistry, and president of Indian Council of Chemists. He has provided exemplary leadership to the scientific community in India and abroad. So I would like to welcome you, sir. Please take the dais. Sir, as requested, you have 20 minutes time.
Sorry, Mr. Chairman, I will take 2 more minutes for this, to make up this. Thank you. At the outset, I must thank the organizers and also Chirantan, the CRS Society, for inviting me, for honoring me and giving opportunity to talk to you. So, we have been because the topic that has been chosen for this event is science beyond what? Beyond what boundaries. And today we are always talking about the interface between two sciences, two different branches of knowledge. So I shall be discussing thermoanalysis beyond boundaries, and before that let me tell you one thing, one experience. Out of the 4.5 decades that I have spent in chemistry, teaching and also in administration for about a decade, including that administrative experience, why did I opt chemistry to the youngers? Incidentally, in young days, my father, who was a chemistry professor, he was also chairman of the department where I served most of the time later on, he was interested in getting me to physics. But I had opted for chemistry because of many factors. I will just point out the uniqueness of the subject. It is the most versatile. You just you just mention a problem. Chemistry might be having some solution to a problem. It is the most standardized subject, a standardized field of knowledge. I had seen philosophy professors talking too much and making heated arguments because one was supporter, one was from Western philosophy, the other was from Indian philosophy. I had seen political science professors fighting because one was follower of Plato, the other was follower of Aristotle. In chemistry, there are no two schools of thoughts anywhere. We have one monitoring agency, IUPAC. There are IUPAP, International Union of Pure and Applied Physics, IUPAG, IUPAM. You can check it in the ICSU website portal, UN portal. And you can find their standard bodies. But how many of the students, even doing masters, are aware of those bodies? But in chemistry, any student who are going to class, even in school days, they are aware of what IUPAC, what it does mean. So this is the standardization. Now, regarding the versatility, I mentioned somewhere, I think he was there. It can solve, it can talk to, because if you are well versed in chemistry, you can go and teach history students also, chemistry of history. What does this mean? Chemistry means what are the chemical explanation to the Bronze Age coming before Iron Age. Because the explanation is, because although iron ores are abundant on the earth crust, the answer is because the reduction of iron ores required much higher temperature, which we could obtain, we could achieve only after thousands of years before. But bronze, copper was not much abundant, but it was getting reduced at 400 or 450, which were being achieved in a jungle fire. So there are explanations. Chemistry is not creating problem, as most of those persons who have simply seen chemistry and who have not learned chemistry, they say that chemistry creates problem. Chemistry creates environmental pollutants. Chemistry creates this and that. No. If you know chemistry, you will argue that no, chemistry and only chemistry can solve the problem of pollution. Chemistry and only chemistry can solve the problem of even the disease, molecular. We have been, Rawat has left because he had to catch flight. See, when you apply chemistry to any branch, it becomes modern. We have introduced chemistry in physics, it became modern physics. We introduced chemistry in biology, it became molecular biology. And most of the medicine Nobel Prizes in many decades have been won only on the basis of chemical speciation, chemical studies, chemical structural elucidation, or even the Google person got Nobel Prize on the basis of some basic concepts in the field of protein synthesis, applying knowledge of chemistry. amino acids and doing only on the computer. Anyway, so if you apply chemistry, you can solve any problem of the world, even in energetics. He was talking about perovskite and how to get those perovskite. And Bhange Sahab was talking about the catalyst, how to obtain those catalysts. Now I am taking you back to inorganic chemistry. But before that, let me conclude the old story. Since I was more influenced by the impact of chemical knowledge in the society, and because I had access to chemistry books in my home, that's why I took chemistry and I forced, it was a sort of bullying, my younger sibling to physics. And she retired as professor of physics in a Delhi University recently. She was always complaining why you sent me to physics, but she did excellently well. She was a good author. Anyway, now similarly, in the field of there are numerous methods which are analytical techniques and methods which are used either for synthesis or for characterization or for studies of various possible applications. Among those, thermoanalysis is one of the most versatile. I think no other branch of analytical technique is as versatile as thermoanalysis is. Because thermoanalysis means any technique. It means it represents a group of techniques. A group of techniques in which temperature dependent property is monitored as function of temperature. While a substance, a material, anything is subjected to temperature change. Any heating, dynamic, isothermal, any thermal change. And what happens? And in the process of any synthesis, whether it is material synthesis or in a drug or at the micro, not only micro, nano level, he was talking about ribosome synthesis. Our Nobel laureate was talking about the difficulties that was being failed by going for a structural elucidation of ribosomes. Now we have, not me, we have introduced it into cell, and there we are doing chemistry on the basis of nano thermal analysis, nanocalorimetry. Let me start it afresh. So the topic that I have chosen is thermoanalysis beyond bodies, and I shall be taking it as a special case of evolving thermoanalysis, studying thermo-oxidative decomposition, decomposition which is taking place in presence of through oxidation, and I shall be, and also effect of heating and suddenly going to the minus temperatures in convenient synthesis of some nanomaterials, and also in understanding healthier use of foods, edible oils I shall be talking about. Now, the world body, the international body, the IUPAC body in the field of thermoanalysis is ICTAC. It is an affiliating body, and it has one of office bearers is present. Ramesh is here now. He is now office bearer, and I had the opportunity. I was lucky in becoming the secretary of this body, international secretary for 4 years, 2012 to 16. I organized the conference in Orlando, Disneyland in 2016. So it is an affiliating body, and it has branches in many dozens of countries. We have in India, we have Indian Thermoanalysis Society. And it is responsible for standardization, all the sort of activities that IUPAC does for chemistry in solving any problem, any conflict in the field of chemical knowledge, ICTAC does in the field of thermoanalysis knowledge. So it holds quadrennial conferences in different parts of the world. Last time it was held in India, and that was for the first time. And Ramesh was the organizing secretary. It was held at IIT Madras here. In the history of ICTAC, it was held here for the first time. So he is his director. And in our country, as I told you, it is our Indian Thermoanalysis Society. It is based at BRC, Mumbai, and it organizes biennial conference and workshop. If you have any problem, if you want to adopt this thing, you can go there, you can contact there. Their workshops are held everywhere. We have also symposium on thermolysis and applications of thermolysis and calorimetry SATAC every 2 years, almost every 2 years. So these are the two events and opportunities. This is from picture of the last biennial event of Indian Society. It is from BRC campus last year. This picture has been published in Q1 Journal of Thermolysis by Springer Nature. This has been published yesterday. This picture is there from there. Now, what about the properties which we monitor when a substance, a material, whether it is food or drug or biological material, it may have any dimension, whether if it is heat, it is scanning calorimetry, if it is temperature, thermometry, like that. Different properties monitored, the techniques are named as such, the abbreviation like is there, and the applications have been mentioned here. Similarly, this is from the, just like IUPAC, ICTAC had formed a nomenclature committee, it had nomenclature committee, and that published this report recommendation. This was published, one of the most cited papers in Thermochemica Acta. You can find out ICTAC nomenclature, Google search, you can find this paper. This table has been finalized by ICTAC when I was secretary, and it is from that report. So if it is mass, it is thermogrammetry. If it is dimension or DMA or TMA, it is electrical property. Electrical properties also change. You know the critical, everything. I think many physics persons are also here. If you are going for mass, then dimension, yeah. Optical parameters, acoustic parameters, gas flow, magnetic property, it is thermomagnetometry, and it is, now we have many properties which can be studied. So these are techniques, about 5 dozen techniques are there. Depending upon the program of temperature change and the techniques, how are we measuring it, and the magnitude and the quantity that we are interested in, whether it is micro level or nano. For example, if it is calorimetry, it could be microcalorimetry. On the basis of its dimension, it could be nano calorimetry. Now we can have simultaneous, two techniques can be taken together, and we can also have coupled. So for complete understanding, these two techniques are there, and this is there in elsewhere Encyclopedia on Analytical Sciences. This special chapter is there. We have authored it. This diagram is from there. Now, a cursory glance of the papers that appeared in Scopus in 2025, we had almost 233,000 research papers in Scopus in 2025, which mentioned thermoanalysis, and out of that, about 46,000, so almost 1/4 you can say. So you can see out of the many techniques, we had differential scanning calorimetry against the most versatile of the thermoanalysis techniques. So I shall be coming to calorimetry. Before going to differential scanning calorimetry, let us discuss something about the calorimetry. Calorimetry, measurement of calorie, the heat change, heat measurement. As the subject, if you heat a coal substance, it requires some excess heat to convert to carbon monoxide or carbon dioxide, depending upon the environment. You are aware. But after the transformation starts taking place, the process becomes exothermic, and if you have to maintain the heating rate at 10 degrees Celsius per minute, then you will have to take out heat out of it, so that the temperature gradient that we have planned is maintained. And so beginning with calorimetry, it could be bump calorimetry, it could be isoperibol solution calorimetry, like that ITC flow calorimetry, and then differential scanning calorimetry. It is the most popular. Now, what does this mean? Differential scanning calorimetry is the most powerful. Commonly, because material scientists are here, and we initially, most of the persons are aware that it is used for understanding glass transition, particularly in the case of polymer chemistry, in medicine, in the field of pharmaceutical chemistry, the phenomena like relaxation, polymorphic transition, the crystallization, these are the things, glass transition, temperature, melting temperature, these are characteristic. This can be used for qualitative analysis, not only qualitative, for quantitative analysis also. Now we have flash. If we have to use a substance in the outer layer of a spacecraft, now as the propulsion is taking place, the outer jacket, the heating will be taking place at many thousands per second. So we have to see whether the substance, the metal, the alloy which has been used in the outer jacket can bear that temperature or not. So before putting it to use, we have to find out, go for flash DSC or like that. So DSC, many applications are there. Simply the modulated and other DSC methods are there. So the physical chemical changes, to sum up, not only the phase transition, solid liquid gas transition, glass transition, denaturation, like denaturation of protein if you heat it, and this is the method, this is the technique that is used for pasteurization in milk. You know, it is heated and again cooled, you know, how the pasteurization is made. We don't have time to discuss those in detail, very interesting thing. Polymeric conversion, oxidation, decomposition, thermal curing, annealing. Now the strength, you know, Gujarat is the world center of recycling, of getting recycling for iron and steel. The scrap from entire world is coming to the Gujarat coast, and now it is going to the entire country. Now the recycled iron and steel, it contains active metals, and that enhances exponentially the corrosion rate. So to counter it, now we have devised a method of sintering. Now thermomechanical treatment, you know, I will not go in detail, but sintering enhances the mechanical strength, you know, the time and the temperature that is used. But DSC graph taking only one technique at a time, it is complex if you so, but still it is very useful. And we have done, I will mention some of the things that we have done, our team has done. Now it is used for optimization of temperature. If you have to synthesize nanomaterials, perovskite or another thing, so we have to, if you have to go for sintering, now which temperature will be chosen for at what temperature you have to optimize. Randomly we can't do it, we should not do it. So for that we can go into thermoanalysis, optimization of annealing temperature, and it is done if you understand the curing portion of the DSC. So we have done good large volume of works in the field, not good, large volume of works, ferrite, aluminate, chromite and yttrium aluminum borate, some good patent also, and in the field of oxidative decomposition of edible oils. What happens when in air, in frying pan, edible oil, any groundnut oil, peanut oil or mustard oil, it is used for cooking, or coconut oil from South India, if it is used for cooking, what happens if high temperatures are there? What happens if the heating rate is very fast? What happens in some spices like turmeric and other things are added? So what happens to the oxidative decomposition and the chemical changes, formation of free fatty acids, aldehyde, ketones, they can affect not only, but many toxic materials are also coming up. So these are mustard oil that we have done. Now, thermo-oxidative decomposition in edible oil, what happens? Oxidation, isomerization, polymerization, hydrolysis, because moisture is there in edible oil, and formation of volatile, non-volatile, how to, so this is a typical DSC curve. So these are the features, and we could succeed in getting good technological applications of the materials that we could synthesize through simple method. And the piezoelectrical sensors, we are aware that the material properties, the material in material size, the piezoelectric properties, the dielectric properties, and thermolysis in sensors, they are used. And we are aware of the applications of nanoparticles. You just mentioned in the field of materials, nanoparticles are the most versatile. Field, you just mentioned in biomedical research, healthcare, environmental, energy, sources, agriculture, consumer, everywhere. So this is even in drug delivery. Not only that, you can have good engineering strategies for lymph node against targeted immune activation So the material science, what would be the size, how to transport, whether it could be used as carrier, how to bind, and what will happen in physiology and immunology. These are the applications. But if you have to prepare nanoparticles, the property will depend upon the preparation strategy, and the properties will be dependent on it, and properties will determine the applications. Because if it melts earlier, you can't put on the rocket jacket. So this is the thing. Property.
Sir, I think.
I am concluding. The properties of such materials are dependent on the method that are used. So we have done some work on multifunctional materials, because multifunctional materials, they have ability to react upon external stimulus, hence ability to respond to their environment in a useful manner. If they are behaving normally, they are not useful. They are behaving abnormally, then they become useful, as we are aware. Now smart materials having good optical, electrical, mechanical. So in this category, ferrites are the most popular because they fit most. So low temperature synthesis, we have succeeded in making a series of ferrites, magnesium, cobalt, barium, samarium, and properties, all optical, electrical, optical and magnetic properties. They could give some good, bring some good prospects of their particle size, what was happening in the particle size. Ferrites, So the samarium, these some interesting features were there. Cobalt ferrite, some interesting, the photoluminescence properties of, it is very hard. It is used in microwave absorber, in radar and everything. So hexaferrite, it requires thousands of degrees Celsius to prepare it through solid acid, but through sol gel we could prepare it. I would not go in detail. And then very interesting properties in magnesium ferrites and other things there. As I told, simply the cited precursors were subjected to that. Then we went for TGDSE. Then we went for the kinetic analysis, thermodynamics, and then we finalized the optimum temperature at which sintering should take place. After getting the material, the dielectric, magnetic, and other things were there. For kinetic, these methods, normal methods were used for both the things. So thank you very much.
So thank you, sir. Thank you very much for ending the talk. Maybe time is not
20 minutes.
sufficient. So I request
sorry,
now please accept our honor from the organizing committee.
Anyone can access me. Email is PROF RK Verma, Professor RK Verma @gmail, Professor RK Verma @yahoo.com.
So I think with this we are ending the plenary session, and before we break for a different session, that is I have some announcement. For any event, the sponsors play a very important role to make the event successful and also keep us comfortable during our technical deliberations. So today I would like to thank the few of the sponsors. So Elegance Imitation Art Jewelry. They have the message, distinguished scientists, innovators and esteemed guests, may I please have your attention towards Elegance Imitation Art Jewelry. While you spend your days exploring the wonders of science and precision technology, we invite you to experience a different kind of precision engineering today. As many of you may know, Rajkot is globally renowned as the ultimate hub for imitation jewelry, celebrated for its unparalleled craftsmanship, intricate detailing and micro-precision designs that rival real gold. It is a perfect blend of traditional artistry and modern manufacturing excellence. We invite you to take a short break from the formulas and theories to discover the art of science and the science of art. Please visit a stall of imitation jewelry stall to explore our exclusive collection of Rajkot finest imitation jewelry. Come witness how creative meets precision. So they are looking forward to welcoming you at the stall. Please visit them. And another sponsor, Health and Nutrition Camp. Today morning I also visited them, their stall. So with the free body mass index checkup, the visceral fat body fat calculations, nutrition is necessary for all of us. With proper nutrition guidance, they can cure any disease, they can have an amazing medicine-free life. So heartily, Health and Nutrition Camp, they welcomes you for free health checkup. So please have a look at their stall. And last but least, Rajkot Porter sarees are celebrated for their highly intricate hand-woven design and use of the ancient ikat weaving technique. It crafted from pure mulberry silk and are recognized with prestigious GI tag. So GI tag for ikat tech, reversible design, natural dyes and cultural legacy. So I would like to thank their generosity for coming forward and supporting the event, and I would like to request on behalf of organizer to visit their stall and encourage their business. Thank you very much. And now I think we are breaking into two sessions. I request you can announce, no?
Thank you, sir. Moving further, we are having two different sessions. For session 1, as per your breakout, for the session 1, that is happening here for in this hall only, and number 2, that is happening in the English department hall, which is exactly opposite to the place where you all have taken the lunch. Okay, we are having 2 minutes to this breakout. Those who are having any queries may ask, and if you don't know at which hall you have to go, then please ask to the volunteers.
recommend this honors. Please we can welcome her for the next lecture. Thank you.
Dr. R.L. Gardas, Ramesh Gardas, Professor, Department of Chemistry. So, he is a Silver Star awardee today. So, Dr. Ramesh is a distinguished chemist and professor at the Indian Institute of Technology, Madras, internationally recognized for his pioneering contribution to the chemical thermodynamics, phase equilibria and sustainable solvent system. His research on ionic liquids and deep aquatic solvents has significantly advanced the design of environmentally benign solvents for industrial and energy application. With over 250 research publications, 4 patents.
Hello.
Okay. Hello. Okay. So, he is a fellow for Royal Society of Chemistry, associate editor of ACS Journal of Chemical Engineering Data, and recipient of IIT Madras Mid-Career R&D Award and Best Teacher Award. He is exemplifies in excellence in research and education. So, over to Dr. Ramesh. So, you have 12 plus 2 minutes, sir.
ચેન્જ નહીં થતું જો હા થાય છે થોડા આગળ આવી જાઓ ને તો હું છેલ્લા બેન્ચ વાળાને સવાલ પૂછું મોસ્ટલી. Good afternoon. It's a great pleasure to be here, and I would like to thank both the organizers from Saurashtra University as well as the Chirantan Sanstha. So I have kept my topic title as ionic liquids and deep eutectic solvents for advanced sorption and extraction processes. So let me give you, I have a 12 minutes. The chairman sir told, where is chairman sir? So 12 minutes, so you just raise the hand, after that 30 seconds I will stop. So I'll take 30 seconds or 2 lines to tell you before going there. If you allow me, the entire chemical and chemical related research, whether it is industrial or academic, to divide into 3 categories: solid state, solution phase and the gas phase. So I have no doubt to convince you all that solution phase would be more viable and preferred. The reasons are, in the solid state we use very high temperatures, that means very much energy required, expensive. In the gas phase we usually work at very high temperature and pressure, again energy required, means expensive. Whereas solution phase we work usually at moderate temperature and pressure, which is economically viable. In addition to that, wherever or whenever you need mixing, stirring, pumping, dissolving, transporting, separating, precipitating, the energy is so economical, the process become more viable. Having said, the solution phase has a great variety of advantages. One limitation is the volatility. Because of the volatile nature, it creates so many other problems. So people look for no solution chemistry or water-based chemistry or supercritical phase chemistry or sustainable solvent-based chemistry. Each one of them have their own advantage and disadvantage. So let us dive into the ionic liquids. So why we need to look, I have already explained, and I will take you two class of solvents, ionic liquids and deep eutectic solvents. Before that, as I promised to Chairman Sir, I will stop, so I may not have time to thank all of them. I would like to thank all my scholars. The bold letters have been graduated and the other ones are working. I would like to thank all my collaborators and my students and funding agencies and the CRS and Saurashtra University for this opportunity. I asked my student, what we are doing in last 16 years, can we put it in one slide? So my student have put, there was a competition among my students. So we would like to replace volatile organic solvents at the industrial scale with the green solvents. So we tune the structure of the new solvents for the targeted properties and to achieve the desirable application. So we work on ionic liquids and eutectic mixtures, and we study their thermophysical properties, phase equilibria and data generation, and mostly for converting waste to commodity. Then I said, no, let us come up with one equation, not even one slide, one line. What we do? We integrate fundamental science with engineering approach for the socially relevant and sustainable technological development. So this is what we do at IIT Madras last 16 years. If you see, the solvent market is keep on growing $57 billion and compound annual growth rate is 4%. Three sectors are booming: energy, automotive and the construction, and they use huge amount of solvents and the people are looking for the. I will introduce the first class of the ionic liquids, which we call hybrid salts. Why I used the word hybrid? The conventional salts both are inorganic in nature, cation and anion. For example, meethu. Naam meethu pan hoy kharu. NaCl. So sodium plus ion and Cl minus. Whereas here we have a hybrid. Mostly cations are of organic nature and anions are inorganic. They possess unique combination of properties and they have several things. If you just do literature search of patent or this one booming up. So what are the two limitations this field, even though it has gone to industrial scale, still people are addressing two things. One is viscosity, other one is a cost. If viscosity is large, wherever you need mixing, stirring, transporting, phase separation, you need more energy. Again, it is not possible. So, how to address these two problems at a time? Across the globe, few groups are working, including us, Ohno group from Japan, McFarlane group from Australia, Robin Rogers group from Alabama, Coutinho group from Portugal, and we among them from IIT Madras. So, we cannot replace organic solvents so easily. So, what we should do? We want to reduce their amount using them as a performing agent, or what we call additives or performance agents. And then the question comes, sir, just 2 minutes ago I said we want to replace organic solvent. Now I am saying we cannot replace. How both are contradicting or how both are true? The reason both are true. Without compromising on the final products quantity and the quality, if we can reduce the requirement of organic solvent substantially, that is called, it's also green chemistry. So, for a given quantity and the quality of the product, we use very, very less of organic solvent by boosting their performance by adding small amount of ionic liquid, sometimes in ppm level. It is like ek tir do nishan or ek tir anek nishan. So, this is the book. Mark Shiflett, who was at the DuPont company and moved to University of Kansas, it has gone to the industrial scale. This is 3-year-old book, which is published during Corona time, 2023 or so, 6 years now, sorry. And we never purchase ionic liquid, though it is available in the market, because the synthesis is not very difficult, it's very easy. The difficult part is purification and handling. I'll straight away take you to our target. So we design to replace the volatile organic compound based on their combination of properties. We synthesize, we characterize, we purify, we study their thorough thermophysical profile, including thermal analysis, and then we go for application. And if we are happy to announce, we are one among the group from India where our database from ionic liquid thermophysical properties, out of the total this much data, more than 20,000 data published from our group in Q1 journals, where we have already mentioned about the purity of the samples and the calibration of the instruments, and that data has been taken by NIST IUPAC and it has been absorbed. So this is the first website where anybody can go and see what kind of data already available and which is reliable. Another class of solvents, deep eutectic solvents, there you have two ions. Here you have two compounds, one is hydrogen bond donor, another one is hydrogen bond acceptors, and where the melting temperature of the mixture is lower than both of them. If the A and B compound, B has a lower melting point, and the resulting mixture, if this temperature gap is more than 100 degrees Celsius, the term we add instead of eutectic mixture we call deep eutectic mixture. The deep terms denotes that the temperature depression is quite large. The delta T is more than 100. So these are the few example of hydrogen bond acceptors and donors, and these are the different class of DES. We have 4 classes, and then if you compare, they look similar because both of them are subclass of molten salts. It's like a old wine but in a new bottle. Molten salts are known for centuries. These are the new class of molten salts. The only difference is molten salts are liquid about 800,000 degrees Celsius. These are behave like a liquid or remain as a liquid around room temperature. I'll take you one of the 3 applications are there. Probably I will close at 2. So we want to extract micropollutant from the water. The micropollutants are from the various industries, including pharmaceutical, personal care, dye, pesticide, and these are very different size. What happen for any industry, after certain amount of the water they consume, the water bill goes very high and they may not allow to buy new water. Even if you have money, they may not be allowed. So every industry would like to go for ZLD, zero liquid discharge. So they want to reutilize the water. So this water we are purifying to be reused in the industry, not for drinking or for irrigation. There are plenty of conventional methods. Each one of them have their own advantage or limitations. We are going liquid equilibrium. So LLE, water rich with micropollutant. We want to make another liquid, which is, the reason is we want to have a mass transfer easy and the energy requirement will be less. So how a pollutant which already liking water and it is remain in the water, we want to take out from another liquid, probably either organic liquid or again water, where our targeted compound is there. So our ionic liquid be in the upper phase based on the density, should go down to the bottom phase, take out the pollutant and do not stay there. So we need a polarity difference, we need to attack, we need to interact with the pollutant and bring back. So this is the story. To get that kind of molecules where our phase should be non-aqueous, so it will not mix with water. Our ionic liquid should be miscible in non-liqueous, but it should go to the liquid and bring back and again to the non. So this is the target. So we check all the requirement of pi-pi interaction, hydrogen bonding, hydrogen physicity, and our target compound was diclofenac sodium. This is the most micropollutant from pharmaceutical industry. So this is the diclofenac sodium. This is the compound, and we want to extract this from water. So our targeted molecule based on our literature and based on our experience and the computational, this is the what we have done. So here to choose this compound, we had 5 theories behind and we have combined. First one, alkyl ammonium compound, cheaper, with large cation and small anion, likely to be liquid and easy. With having a OH group, it should be making hydrogen bonding with our targeted compound. Having a long alkyl chain length, so it will have a polarity difference, so it will not be completely miscible in water. Having a benzene ring can make a pi-pi interactions. With these 5 theories, this is on the theory and computation and our experience. And we have proved and checked, synthesized with varying alkyl chain length from C10 to C16, and all of them are working. And we wanted to check without ionic liquid, if it is only toluene or dodecane, how much diclofenac sodium from water can come. So the blank results are less than 17%, and this with ionic liquids the results are above 90%. So this is our calibration curve. You simply need separating funnel, rotavapor, and you need UV visible spectroscopy and idea how to synthesize ionic liquid, and very simple ionic liquids. And this is the values what we have taken. Our ionic liquid, targeted ionic liquid, these are the 4 ionic liquid, any one you take, what quantity? 10 micromolar, and in toluene. Our water has a diclofenac sodium, the large range, and then you room temperature, atmospheric pressure, you equilibrate, let's say 300 RPM for 10 minutes and let it be settled down for 15-20 minutes, and you see all the diclofenac sodium, 95% of diclofenac sodium from goes water to the toluene phase, and you can easily separate out. The ratios are 10:90. So water with micropollutant is 90% by volume, toluene with ionic liquid is 10%, and this you can do multiple times. Now everything looks good. So UV visible, the bottom phase, water phase, this diclofenac gone down, alkyl chain length increasing, the extraction capability goes from 90 to 95%, and we have checked with IR also. So we have proved with NMR, UV and IR, and then computation. These are the optimization, then the computational, why it is happening. As I told you, there is a pi-pi interaction is happening, hydrogen bonding is happening, and the phase separation due to polarity change. The surprisingly, what we have done for diclofenac sodium, it is also capable to extract ciprofloxacin, metronidazole, it's more than 95%. Now, we thought, why to use even toluene in small quantity? Can we come up with without toluene at all? So then we went to another work where we wanted to try to extract methylparaboline and pyridine. So these are the personal care product what we use all in our makeup kit and beauty parlors, we use most of them. In that personal care, these are the micropollutants, and we thought, 3 minutes, I'll just go to the last conclusion. Methylparaben and 2-nephthol, we wanted to replace, extract them from water to here just between DES, and we are successful extracting 90%. This is called liquid equilibria. And then last work, it was extracting cobalt and nickel from the used batteries. So I am not talking about here, but leaching agent, and we have shown deep eutectic solvent as a good leaching agent. This is not the picture from Google or anywhere, but this is from my student in the laboratory. So we have extracted, this is the real pictures from spent batteries, these are the real pictures, and then we have gone to cobalt in oxalate form, lithium in oxalate form. This work is published on the cover page in this paper, ACS Sustainable. So to summarize, why it's not going, it's also telling me go away, So this field has a strength. You can tune the property based on your cation, anion or alkyl chain length. So theoretically, millions of ionic liquid possible. Weakness is cost is high, viscosity is high, but ek tir do nishan. Don't use in pure form, but use additive. And the opportunities based on the constituent ions or the starting compound, you can make it nature friendly or green. And the threats are how much energy you spend for reusing or recycling it, how many times. And this is where entire research is stuck now. And that's why out of lakhs of publication in industry, it goes hardly 1%. So let's try to go more, and thank you all for this great opportunity.
Hello, yeah. Hello. Yeah.
Hello.
Yeah. So, just sorry for the interchange. Now we are moving forward for the next lecture by Dr. Sonu Gandhi. Please, thank you. It's online.
Should I start? Can you hear me?
Yeah, you can start, madam. Yes, please.
Okay. Thank you, sir. Yes. A very good evening to everyone, and I thank CRS jury to select for the CRS silver medal, and I am happy to deliver the award lecture today. So my title is Chemistry in Action, Translational Advances from Environmental Sensing to Biomedical Application. Next slide. Next slide, please. Yeah, so I will be talking today mainly on the pesticide detection, though our lab works on the infectious disease diagnostics as well. So coming to the monocrotophos pesticide, which is organophosphate, it is highly hazardous insecticide and it is potent neurotoxic ACHE inhibitor. And WHO has classified monocrotophos as class 1B pesticide, and the acceptable daily intake limit for the adult is 360 micrograms per day, and the MRL value which is set up is up to 0.0221 mg per kg. So as farmers, they are unaware of how much pesticide needs to be sprayed on the crops. So that's why they spray like filled in the tank and spray on the crops. They do not really care about the concentration that should be sprayed onto the crops. So that's how the over spraying of this pesticide happens on the crops which we as a human used it for our consumption. So the systematic pesticide, which means that the pesticides moves throughout the plant and it also percolates into the soil and water. And not only the crops, soil or water is contaminated with the pesticides, the traces of monocrotophos has also been reported in the milk, meat, water and eggs, because animals are also the consumer of the pesticide, not only the humans. So it is a one health problem which we as a human and animals both are facing. Next slide please. Next slide. Yeah, so there are several toxicity reports of the monocrotophos have been reported, which says that 6,000, more than 6,000 farmers died due to the pesticide poisoning, because spraying also leads to the delivery of these pesticides through the skin pores into the body fluid, and it reaches to the bloodstream and also affects the human body directly. Go to the next slide please. So there are conventional techniques for the pesticide detection, which is based on the HPLC, GC and MS, which is time consuming, costly to perform and required a skilled person to operate. So here we propose the biosensing platforms, which is less time consuming, cost effective and easy to perform, does not require a skilled person, and it has the POC capabilities. Based on this we propose our work. Moving to the next slide please. So in this case, how the biosensor works. So the biosensor is the device which has the transducer, for example, the electrochemical, optical or piezoelectric sensor, which we can tweak as per our requirement. And this is coupled with the biorecognition element, which could be your enzymes, antibodies, aptamers. When it interacts with the analyte, here is the monocrotophos, the signal processing happens, which can be read in terms of the reading or the spectra or any kind of value on your smartphone app. Moving to the next slide, please. So in this regard, for the aptamers, what we have done, we have developed the Selex process from the best out of waste approach. So what challenge we were facing before is that if you can look into this Eppendorf tube, the solution is like a black color, where we have used the graphene nanoplatelets as the solution for aptamer isolation. Enriched with the graphene nanoplatelets and the target molecule with the aptamer. So it was not clear supernatant, as you can see from this Eppendorf. The solution is light gray in color, which means the material is still there present in the supernatant. So with this, what we have designed on your next side, you can see in this column we have filled this. So this is the waste column of the plasmid isolation, which all the molecular biology labs used. So after we throw it into the dustbin, we have taken these columns, cleaned it, and again reassembled so here is the aptamer library, which is pre-incubated with the monocrotophos, and then we have loaded this into the column. So we have to do just 1 minute spin in the centrifuge. So the flow through which we have collected is the enriched pool of the aptamer, which has the high affinity for the monocrotophos. So which you can see in the agarose gel, there is the sharp clear band of the enriched aptamer we have observed. By doing this method, we have reduced the Selex cycle from 30 to 35 rounds to the 10 to 12 rounds. So not only we have really used the waste as a best approach, but we have also reduced the cost of the selection of high affinity aptamers for the monocrotophos in this process. Next slide, please. Next slide, please. Can you please change the slide? Slide is not changed, still it is the... Oh, really? I can't see that. One second.
What is the title? It's a comparison of
It is the selects procedure I can see for aptamer generation. It's not moved. Oh, okay. Yes. So then what we have done, we have used the GRNP as the graphene nanoplatelets and also used the graphene oxide and compared the efficiency of the selects process by using the two nanomaterials. So here we have made the graphene oxide as a bare and did the SAM EDAX, and we have also done the SAM EDAX for the GRNP nanomaterial, and we could see that there is in the graphene oxide SSDNA, you can see there is the peak of the nitrogen and phosphorus, while in case of GRNP, we could also see the presence of the SSDNA elements, which is nitrogen and phosphorus, which indicates that there is the successful immobilization of the SSDNA happened onto the nanomaterial. Later, we have characterized throughout this with the XPS and zeta potential, which also proved the hypothesis of the immobilization of aptamers onto the GRNP and gold material. Then in the panel 2, you can see that we have done the enrichment of the aptamers. Here you can see that we have done the enrichment up to round 17, where the one round of the non-specific selection was carried out to increase the efficiency of high affinity aptamers. And this selects process was carried out for the by both materials, GO and GRNPs. And the respective agarose gel electrophoresis was also carried out, which shows the clear single band in all the steps. Later, we have sequenced these aptamers, and in this process, we have found around 8 to 10 unique sequences by both processes. Next slide, please. So, in the gold nanoparticles, so what we have done, we have synthesized the gold nanoparticles and characterized it with the DLS. Okay. So we have characterized these nanoparticles by DLS, zeta and 10, and I carried out the aggregation assays. In this aggregation assay, we have done the series of aggregation assays where we found that two aptamers showed the promising results, which was further characterized by the UV vis spectra, and the KD value was calculated. Next slide, please. Then we have tested the cross-reactivity of both the aptamers with the closely related pesticides and carried out the CD spectroscopy to know its secondary structure, which was G quadruplex and the random coils. Later, the electrode was fabricated and characterized by the SAM and EDAX, and contact angle was measured. Next slide, please. Then the analytical performance of the electrochemical sensor was tested and optimized with scan rate, pH, temperature, and testing of monocrotophos with MPGO130 and 999 was done, and where the limit of detection was 0.58 nanograms per ml and 0.78 nanograms per ml. We have also tested the stability, and the validation with HPLC was also carried out. Next slide, please. Black as the magnetic material. So magnetic properties. So here the waste. So here next slide, toner cartridge from the printer. It's magnetic, please. So here you can see in the panel 1, the cubate carbon black is aggregated kind of material, but when we oxidize the carbon black with the Hammers method, it is soluble. Can you please play this video? This is the short video which can show the readily soluble OCB than the CB material. Next slide, please. Then we have done the characterization of this material by the SEM, EDAX and HR10, where it showed the characteristic amorphous nature of the material and further evident by the XRD, XPS, FTIR and VSM spectra, which showed it has the magnetic properties which we have utilized in the SELEX process to isolate the high affinity aptamers. Next slide. Then we have done the ssDNA adsorption studies and OCB SELEX enrichment tracking by the UV vis spectroscopy, where we would like to understand how much OCB is required to absorb the ssDNA efficiently. So it was 10 milligrams, which was then validated by the fluorescence spectroscopy and the native gel electrophoresis. Then we performed the 16 rounds of SELEX. Yes, sir. Yes, sir. Yes, sir. Thank you. So we have carried out the aggregation assays, and next slide, then DNA displacement assay. Next slide. So we have also developed enzyme-based electrochemical sensor for the monochrotophos detection, where we have made the AU and WWS2 nanosheets for the monochrotophos sensing. Next slide, please. Then we have characterized it with various techniques. Next slide. This is the HR10 of the same. Next slide. This is the XRD and XPS, AFM and electrode characterization. And next slide. Then this we have done the testing and analytical performance. Next slide. So we have also made the chroma grid for the colorimetric detection. This is also best of the waste approach, where we have used the PVC sheets and the rings of the plasmid isolation column, filled it with the chromogenic substrate. So you can immediately see the change in the color if the pesticide is present into that. So finally, I would like to acknowledge my group and CRS for selecting me for the CRS album medal. Thank you.
Thank you, Dr. Sonu. Due to limitation of time, so we are not having any question and answer for this. So let us move on to next. A renowned for her pioneering contribution to the advanced ceramics, nanomaterials, thermal and environmental barrier coatings, oxygen sensors and solid oxide fuel cells. For hydrogen generation and other applications, she has over 126 research publication, 12 patents and H-index 42. And she is also recognized as top top 2% scientist among in the world for her work, which has significantly advanced material science and aerospace technologies. She is a recipient of Professor Satish Dhawan Young Engineering Karnataka State Award, MRSI Medal and several prestigious national honors. She has successfully translated research into industry through technology transfer. So, Madam, over to you. You have 12 minutes. Thank you.
Thank you very much, sir. Hello, am I audible? Am I audible? A very good afternoon to all of you. At the outset, I would like to thank the organizers for giving me this opportunity. CRS1 folder. Yeah, PPT open. not. So I thank the organizers for giving me this opportunity and the CRS for conferring me with this award. And today I will be basically taking you through my journey for how I started as a researcher and how our work has led to some of the technology transfers. So my title is From Laboratory Innovation to Industrial Impact, a journey in advanced materials for energy and aerospace. Next slide, please. So in 1994, I joined IISc for my PhD, and there I had the great opportunity to enter into the world of ceramics. Next slide, please. And there I met Professor K.C. Patil, who was my research supervisor and well-known, like world-recognized person in the area of solution combustion synthesis, which happened, it was a serendipity which happened in the lab of Professor K.C. Patil, wherein they could synthesize nano and micron size important oxide materials within a few minutes. Whatever it takes, by solid state method and all, like it takes like 2 days to synthesize, the same thing you could do within few minutes. That was the beauty of the process, and the process is now well recognized and used internationally worldwide, and many universities, they are practicing this method, and many PhDs have come out of this process in the country also. So I was fortunate to work on two different types of materials. One is the photocatalytic titanium material as a photocatalytic material, and some ferrite-based materials, and also solid oxide fuel cell materials. Those days, fuel cells were just starting, and we synthesized those materials and with the required properties. And can I use the laptop? Okay. So I synthesized this fuel cell materials with the required microstructure and the properties, and this work we have even written books and several review articles. And later I went for a postdoc in Barilan University. I had the opportunity to work on dye-sensitized solar cells, and I think we could achieve around some 11% efficiency at that time. And then I joined CSR NAL, one of the leading laboratories in the country, which is helping in the aerospace domain, doing a lot of service to the nation with respect to civil aircraft program, applied research and testing facilities. And we are closely working with ISRO for all their launching the satellites, mainly the wind tunnel facilities and acoustic test facilities. All the satellites have graduate from our tunnels, so we are very proud of that association. And when I joined NAL, like unlike other places, where you can start your research activities, whatever you have worked on, here we have to align our work towards the work what is going on in the division. So I had to think what I should work. So meanwhile, I just used my earlier combustion synthesis. I used the concept first time mixture of fuels approach to synthesize composite oxides, wherein we could reduce the particle size, increase the surface area, and also decrease the sintering temperature, and so on. And later, like I was thinking on how to use the knowledge. So I have used my solution combustion knowledge to prepare electrocomposites, corrosion resistant coatings, biomedical coatings, thermal barriers, solid oxide fuel cell, and so on. So Mr. William Grips was my senior. He asked me, like, I am working on nickel silicon carbide electrocomposite coatings for the Wankel engines, which are used in UAV Nishant, and which is test flown and certified. Can you replace my silicon carbide with your oxides? So that's a challenge he given me. So I tried to use combustion synthesized materials, cheaper fillers, and so on. So this was the first paper I published, wherein the first time we used the synthesized materials, within 1 month of submission, the paper was accepted in Scripta Materialia. Later we came up with several combinations of the materials, wherein we could get synergistic combination of wear resistance, corrosion resistance, hardness, so on we could achieve with a single this thing. We have also used microcapsules containing oil for increasing the lubrication, particularly decreasing the coefficient of friction, and so on, and used promising pumice pumice material, which is a volcanic material, as a replacement for silicon carbide. Similarly, zircon, xenosphere, all these materials. We also used different shapes of nanoparticles for increasing the corrosion resistance of sol gel coatings, which are replacement to the hard chrome coatings which are used in aerospace industry. So, and then I had the opportunity to work on the thermal barrier coatings, which are very much essential for the aerospace industry, particularly to increase the gas turbine efficiency. These conventional materials are yttria stabilized zirconia, which face lot of problems. So we have to go for different materials and also multi-layer coatings. So these are the facilities available. These coatings are made using thermal spray, that is a plasma spray technique for making the coatings, and the powders are all flowable powders. So I used again the solution combustion method, modified the process so that we get flowable powders, unlike very fine powders what you get in solution combustion method. And these are the materials. There is a lot of demand for these materials, like 1.5 million kilograms per year is imported, and the industries are using in our country. So we have made a comparison with the commercial powders and our powders, and you can see our materials are having good properties at par with the imported materials. And we also have done some work for industry QME to transform their powders which are not flowable to flowable and qualify them for thermal barrier coating applications. Later we have done multi-layer coatings to have better hard corrosion properties. And CMOS is another problem wherein the silicates attack the coatings and the coating comes off at high temperatures. So we have done CMOS resistant coatings, and also several components have been coated with the thermal barrier coatings and tested in our rigs at the simulated conditions of the aircraft. And we have found that by using thermal barrier coatings, you can increase, like the substrate can withstand another 100 to 150 degrees more than what it can withstand. And in the future, the superalloys will be replaced by ceramic matrix composite. Again, they have to be protected because the silicon gets evaporated in presence of hot steam. So we have to go for a multi-layered TBC, that is the environmental barrier coating properties, which we have made again the flowable powders and the coatings. And we have tested these coatings in steam at 1300 degrees, and you can see that if the coating substrate is not coated, it erodes away. And so this we have filed a patent also. I had also opportunity to work in one project on biomedical hydroxyapatite coatings, and again we have used the solution combustion method and also the solution precursor method for preparing the hydroxyapatite coatings, which has shown better properties. And again some smart materials, that is the shape memory polymers, wherein we have made it can take both the electric stimuli and also the thermal stimuli, so that we can use such materials for morphing wing applications for aerospace applications. This is another process, tape casting process, which is an industrially viable method for the ceramic industry uses this. So we have expertise in our group, and we have used such materials for different applications. So this is a way, since we didn't have access to a facility, we just fabricated this facility with 1.5 lakh investment, and then we have used this. And similarly, a screen printer used for the textile we have modified and used. And particularly for the energy, fuel cells are going to be the future, and solid oxide fuel cells have greater advantages in terms of efficiency and so on. So we have made different types of SOFC materials, and this is the process what is employed by milling the powders and making the tapes and then stacking them and sintering, and finally you use screen printing to do the cell and a single cell. And these are the slurries of the electrode materials which are made using the solution combustion synthesized materials, wherein we require 1 micron as the average agglomerated particle size, whereas for the plasma spray application we require more than 50 to 100 micron size particles. So the process we are tuning to that application. We have also made hydrocarbon compatible SOFCs. Unlike other fuel cells, SOFC is the only fuel cell technology wherein you can feed methane or hydrogen hydrocarbons, even carbon monoxide, carbon dioxide can be used. So we have made several coatings also to protect them. And these are the facilities all indigenously built with our ideas, and the company is now making such facilities and selling in European market. And these are the different types of fuel cell technologies what we have, which are tested in both the fuel cell mode and the electrolyzer mode. So hydrogen is going to be the future. So when fuel cell we operate in the reverse mode, it can generate hydrogen. You can see we have done electrolyte supported, anode supported, wherein you can see 60 watt per cell and even 16.7 liters of hydrogen it can produce. And currently we are working with the BHEL for metal supported SOFC. And this so here we can see the cells being tested for hydrogen generation also. And this technology is transferred to two industries. One is Island Power and Ceramic Consultants, and they are already making these cells, and they are trying to build a stack. And as a future activity, we are planning to use it for the future human space program, wherein we can convert carbon dioxide into pure oxygen and carbon. So this work we are starting with ISRO. And for the electronics industry, we have developed the ceramic substrate instead of the PCBs, particularly ISRO and all, they are using alumina as a ceramic substrate. And here I just want to say to the students, sometimes when you make mistakes, they end up in magic. So what we had done in our lab, we were trying the fuel cells, and people were making zirconia substrate, but we were not getting the conductivity. After 2 months of struggle, we found that it was alumina. The students have filled alumina powder in a zirconia bottle. So, but however, when industry came to us for some other work, they wanted, after seeing our zirconia, they asked, can you make alumina substrate? We readily agreed, and we transferred the technology of alumina substrates for MIC applications, that is microelectronics applications, and it has been tested in ISRO also. And now Carborundum Universe, we have done the technology transfer, help the industry to set up all the facilities. When you go from lab to industry scale, we need to handle the industries and lot of challenges which we have overcome. And now you can see on their website, you can get these substrates from QMI. So this is an example of an Make in India effort. Sir, how much time I have? 1 minute, okay. So we have used high temperature co-fired ceramic technology. Due to lack of time, I'm not showing this. Okay, these are the steps involved. So we make the electronic circuits out of this. So the same process has been used for ISRO, and then we have developed the oxygen sensor for pilot life support system, and similarly oxygen and NOx sensor for automobile application. We have moved from Bharat stage 4 to 6, so oxygen NOx sensors are mandatory. So this technology depends on the high temperature co-fired ceramic technology, which has several layers and electronic circuits, and also heaters are embedded. And this is sensors made, and we have filed the patent, and these are tested also and benchmarked with the commercial sample. And you can see that our sensors are working at par with the NTK sensor, and it has been tested in vehicle also. And currently NOx sensor has been currently tested at Ashok Leyland, and they are very happy with the results. So they are going ahead with the facilities. These facilities have been established with our help at Bangalore, Rotary Electronics, and this has been transferred. So I would like to conclude that I started my research in synthesizing materials. Later we developed products in the lab and qualified them, and finally did the technology transfer. So it's an example of Make in India. I think we should all start innovating in India, and so that we can all reach the goals of Viksit Bharat 2047. Thank you very much, and Jai Hind. So I was really super fast express. You have to be. Yeah.
Yeah. Hello. Yeah. Okay, Dr. Chirantan ma'am, thank you very much for a nice lecture. It's like a tour from the ceramics to the technology. So thank you very much.
Give a big applause to her. Wonderful work. You make India proud, madam.
Thank you, sir.
Nice work, madam.
Yeah. So the next talk by Professor Dr. Sangeeta Kale ma'am. She is a distinguished material scientist, accomplished academic leader and professor at the Defence Institute of Advanced Technology, DIAD, Pune. As Director of International Cell and Dean of Research and Co-Director of Navyukti Innovations Private Limited, ma'am has made pioneering contributions to nanomaterial sensors, biomedical applications and technologies and defense research. Over 160 research publications and several books and some innovative technologies transferred to industry. Ma'am has successfully bridged research and societal impact. A recipient of a national award for women leaders, INSA Teachers Award, MRISI medal and DRDO Science Oration Award. She has inspired excellence in research and innovation and academic leadership. Welcome ma'am, and if I am not wrong, in the same department in 2005 you have delivered the lecture. I remember when I have joined the PhD. Yeah, so thank you.
Can you hear me? So good afternoon and thank you for this opportunity. Thanks to the CRS community as well as Saurashtra University. This is my first visit here and it's a wonderful place. Again, thanks to CRS for the medal as well. So basically I'll talk on this particular topic. I have tuned the topic in such a way that it fits the CRS mandate. However, I'm a physics person and I do a lot of work on physics and electronics, and it goes towards chemistry eventually. So as I go ahead in this particular talk, you'll realize that there is a good amount of chemistry. However, my domain has always been sensors. Sensors we develop, as the earlier madam said, we also work for, since I work for Ministry of Defense, we develop sensors which are required for the defense people. They are related to, they are mostly related to chemical and biological warfare diagnostics. So extremely poisonous kind of nerve gases, poisonous NOx and SOx gases, as well as explosive and propellant materials. So this is the area in which mostly I work. We also work on robotic applications. So as I go ahead mostly, but I'll not talk on all these topics. I'll basically talk on resonators which are used for CBW. So, okay. So it goes, how does it go to the next slide? That I have to tell you, or it should go right? That is inconvenient. That's why. So how did you do that? Wait. Now it's okay. So the motivation for our work is basically this fellow who is a soldier. So we consider soldier as a system. Okay, I will not take much time because we don't have time much. But so basically, soldier, if you consider, then the person will have a helmet, a modular combat equipment. They will have an information and communication module. It will have a energy or a power grid. It will have intelligent clothing components, which will comprise of suit and gloves and NBC clothing. It will have weaponry and ballistic protection, and of course a head protection with a display and so on. So if you consider all these components, you'll find n number of sensors in this. One of the main ones in which is, of course, the chemical and biological protection. Okay, also the nuclear protection. Many times we call it as CBRN. So chemical, biological, radio and nuclear protection. So this is the area in which we work. We've developed good amount of technologies also for healthcare applications and given to DRDO. So there are around 4 to 5 technologies that we have already developed and either given to the industry or to the DRDO labs. Out of which one is something that I will talk about. So I'll talk upon miniaturized RF resonators for versatile industrial sensing applications. So these are basically antenna-like structures. They are very small structures which are excited by using radio frequencies, and once they are excited, depending upon the ambience in which they are placed, depending upon the area in which they are placed, the effective permittivity around this particular sensor module changes. Okay, and that is a way in which sensing occurs. So how do we do this? So we basically do it by initially simulating the structure, optimizing the structure, then actually fabricating the structure, and then making it more and more intelligent by using machine learning algorithms and artificial intelligence. So once we go from the simulation to an AI enabled system, we have actually covered the entire life cycle of a sensor development, and we go from materials and the chemistry therein to an AI enabled intelligent sensor which becomes an adaptive sensor depending upon the environment. Okay, so that's what we do. So what are these resonators? So these are very simple structures. As earlier madam just showed, these are copper structures. Okay, all of you have seen a PCB. So this is simple PCB, and on this PCB we have written a structure. This is a small thing which is written. This is a resonator. It has got two rings in some sense, concentric rings, and on the back side of it is a waveguide. It's a simple copper structure. So if you consider this structure, without going into the details of it, this is its equivalent LC circuit. Okay, all of you have learned this LC resonance circuit in physics, even in 10th, 11th, 12th standard. So this is exactly what it is. Okay, so when we start with this kind of a structure, we initially simulate it. Okay, so for simulation, understand that this is what I'm trying to show you, or this is what I'm trying to show you. So on one side you have the structure, on the back side you have a waveguide, and the equivalent circuit diagram actually looks like this. And if you look into the electromagnetic waves which are created when you put an RF signal on one side and take from the other side, then you'll have electric field and magnetic field perpendicular to each other. Okay, so we can make it either magnetically susceptible material or we can make it electrically susceptible material. So here we choose an electrically susceptible materials, and therefore they are called as electrical metamaterials. So this is what we do. Once we do that, then we will initially simulate it, then we use photolithography to basically make a sensor, then we characterize it, and we later on miniaturize it and make it smarter. So the simulation studies comprises of the following. Okay, what does it do? It basically tries to find out that how much is the size of my device. So let's say it is 10 centimeters by 10 centimeters. In that my structure is, let's say, 5 centimeters by 5 centimeters. So in that, how much would be the parameters that are required when you cut this device? So these are all the different dimensions, and using appropriate software, it will be able to do the simulation, and it will be able to give you the required response. What is the response looking like? So the response looks like that if I give a range of frequencies in the range of, let's say, 100 megahertz to, let's say, 600 megahertz, I have devised the device at, let's say, 300 or 400 megahertz, then at that particular resonant frequency, I'll get a very sharp signature. Okay, a very sharp resonant frequency dip I will get, and this particular dip will be a function of whatever changes happens around. For example, I keep it in normal air, and air is the dielectric around it, and it will show me some signature which is its standard signature. Now I keep it in some poisonous environment, the dielectric material changes, and therefore its peak frequency will shift. Okay, and this is exactly what is used in this particular sensing action. Okay, so what all can we do? So we have done large amount of work. At least 5 to 6 PhDs have completed their PhD degree in this particular work. One particular part of the work that I have completed, I have around 17-18 students passed out up till now. At least of them 6 to 7 have done this work in this particular domain. So these are different areas in which we have worked. For example, gas sensing, high energy materials, SOX, NOx sensing, quality of the oil monitoring, and so on, biosensors and so on. We have no time for all this, but I'll quickly tell you how it works. So basically this is our sensor. Okay, the back side of it, the waveguide is connected to a vector network analyzer. It is very similar to a CRO, and here you have this sensor. Okay, now when you put any particular liquid on the top of the sensor bed, I will get a change in the resonant frequency. Okay. Now, as we put anything on it, instead of air, I put ethanol, I put methanol, I put any other gaseous environment, I put it in a gas chamber, the area around it will experience a change in the electrical permittivity or the dielectric constant. And as that changes, effectively the resonant frequency changes. This is how it works. Okay. So essentially, yeah, so these are the ways in which the values of capacitance and resonances change. Now I'll give you only one or two examples to explain you how they work. So this is a work on high energy material. These are propellant materials or explosive materials. These are also called as generically high energy materials. Now when you consider a conventional sensor, then in a conventional sensor, either the resistance of a particular sensor increases or decreases depending upon whether it is an oxidizing gas or a reducing gas. Here it doesn't happen like this. Here what happens is that every material has got its unique dielectric constant. Since the dielectric constant is unique, this particular sensor gives you a unique signature. And that is the beauty of this sensor vis-a-vis any other commercial sensor that you see in the market. So if you consider this, these are all high explosive, these are propellant materials. Okay, so these propellant materials, if you see, these have very similar kind of groups. There is a nitrogen group, there is a nitrogen group, there is an OH group, then there is a double bond O, there is a double bond O. So all these three materials, if you have to sense them and selectively sense them, this is what you get. Okay, so basically, if you consider this as the original frequency, then you go to one material, it shows you a very nice change in the frequency. This frequency is 4.46 gigahertz. So the change, it may look very small here, that it is just 2 gigahertz. 2 gigahertz is a very big number. Okay, so that way the shift is very unique and very distinct. So I can say that if it is at 4.46 gigahertz, it is a BNP. If it is 4.40, it is AG. If it is at this value, it is AM. So you are able to get very unique signatures, and that's how you can make them work as a sensor. This is the way in which you do the sensor calibration later on and try to fit in as to how much proportion of a particular material will be there in the combination of multiple materials. So this is a work that we have then published. We can also use it for fuel adulteration. Now I'll not go into all those things, but what you can do here is that I have a petrol, okay, and in this petrol there is a good amount of either adulteration done or it is a flex fuel in the sense that in petrol ethanol is added as E5, E10 and so on. So if you do that, can I get the corresponding signatures using these sensors? You can get it. Okay. So if it is E5, then so you just see the dielectric constants are different, and the moment you have this difference, you have the corresponding shift in the sensing activity. So that's what we got with the flex fuel. Now the same sensor, I can do multiple things. For example, I want to put it in a chamber which is a moist chamber. So I can, instead of exposing the entire sensor to a moist environment and completely killing it off, we can put a microfluidic kind of an approach around it. So I can use a microfluidic approach, or I can just use a small syringe through which the liquid is flowing, and it is flowing through the sensor, and I am able to make a live sensor continuous online monitoring. So that can be done. So these are some papers that during that time we published. We can also do the sensor optimization by using for the biosensing applications. Okay, so this is something that we have used nanomaterials for improved sensing. So here the sensor is, we can go to the next stage in which the sensor is functionalized with some material, which is a nanomaterial. Okay, so if I use a nanomaterial which has got a specific affinity towards the analyte molecule which is going to come and sit on it, then we will get a very selective and improved sensing. To take an example, hydrogen sulfide can be sensed by using gold nanoparticles on the top of the sensor bed. So that is what is being done. So we have used gold nanoparticles and we make them active moieties for H2S sensing. So that can be done, and we can see that for H2S we see a very nice shift in the resonance as compared to the others in which we have along with gold we have oxygen, or we have hydrogen, or we have carbon monoxide. You don't get that kind of sensing as what you get for hydrogen sulfide. So that's because we have functionalized it with a molecule which has got a specific affinity. Same thing we can do with multiple other things. So these are just to make you know that what all can be done. So we've used Fe3O4 nanoparticles for exclusive NOx sensing. This is used for the explosives which are NOx and SOx moieties. We can also do it for SOx by using TiO2 nanoparticles. Yeah. You can also do this for bacterial contamination analysis. Again, I'll not go here much, but it is just related to the analyte specific sensitivity of the molecule that you want to detect by putting functionalized molecule on the top of it. So this is something that we have done for dengue detection, and you can see that if you use it for along with the antigen antibody interaction related to dengue, you are able to get specific shifts. But if you use it for along with dextrin sulfate or chitosan, you do not get that kind of shift at all. So this is something that we have done for transformer oil. This one last point I will tell you quickly is that how do you improve it. So now I make a sensor. It is now perfectly working for explosive materials. I'll keep on taking thousands of data. So let's say I take 5,000 data points for multiple samples and I start plotting them on this graph in which there is a change in the frequency and then there is a change in the power. I keep on collecting the data, and as I collect the data, wherever I get the points, I keep on plotting the points. What I understand is that I generate these exclusive circles or the areas or the groups where every time the point falls. Okay, using that I'm able to make the machine learn that if a point comes in this particular domain, let us call it as RDX, for example. If it comes in another point, let us call it as TNT, for example. Okay, all these now what they say names you must have heard, RDX and TNT. These are very popular materials in film industry. This is used for structural health monitoring also you can do, and this is how we get very nice data if we are able to make the sensor learn using machine learning algorithms. So that's what we have done. And then finally, so I'll not go here, but this is something that one can do. We've also done work on nerve agents. Okay, they are extremely toxic nerve agents. Within few seconds and with few ppb concentration, a person dies in no time. Okay, so nerve agents, we have done good amount of work in this area also. But again, you can just go see the papers. Finally, what we are doing is, finally we have made this small fellow. This sensor is ready now. We have to generate and proper electronics so that it becomes a device as small as this, and it can be taken into any big auditoriums and make it sit anywhere and continuously monitor whether there is a biohazard. This is one simple example. Otherwise, it can go to fields where the hazard is something that we have to worry about. So the final point that I want to say is that these are extremely good structures which are very, very good platforms for any sensing which is exclusive and unique. It can be easily tuned, very well simulated, and it can be very easily fabricated. We can use a good amount of chemistry for functionalizing it and improve their efficacy and efficiency. It can be very well engineered for inline monitoring of any in a control system. You can use it in industrial setup. You can use it. Machine learning improves its calibration, and it can be converted into a portable device. Finally, what we want to do is we want to make a single device in which we have done these individual ones. Explosives we have completed, propellants we have completed, biological threads we have done. Everything should sit on a single platform with multiple CSRR sensors on the top of it and a very nice electronic interface, and it can be kept at any particular point in an army camp, in a camp at the border, okay, at the Siachen borders, or at the very high altitude and low high temperatures as well, and it will keep on continuously monitoring the ambience around. So that is what we are now trying to do. The individual pieces are ready. We have to just connect them together. This technology we have also given. We have done this project under Department of Atomic Energy, that is BRNS projects, and we have also given these technologies to DRDO, which is in Gwalior, which is a DRDO lab, and DL Jodhpur. Along with them, we will now go towards making it as a bigger platform sensor. So finally, thank you. These are all my students who have worked directly, indirectly on these projects, and they are working on many other projects as well. And this is my nice group, and Our Chancellor is the Raksha Mantri of the country. So Defense Minister had come, we had given some demo about this particular working to him, and this is a picture taken during that time. So thank you and Jai Hind.
Yeah, thank you, ma'am, for a nice lecture, and from entire team, we are thankful to you. Yeah, please.
We'll be sending some material to you, madam, for the testing. I work on explosive. I'm explosive.
Human explosives we don't
Thank you very much, everyone. I request organizing committee member to please felicitate our session chair and co-chair, Dr. Rangappa and Dr. Piyush Solanki. We are having an additional talk after a tea break. So I request everyone to please proceed for the refreshment of a tea break. We are having a 10 chairperson Dr. V.J. Kaneria and co-chairperson Dr. Jaisuk Marakna. I request both of them to please come forward on this stage and continue for the plenary session.
Fine. Namaskar. Once again, I welcome all of you in RASAYAN-23 from on behalf of Saurashtra University. Now we have one more invited lecture from Professor A. Nirmala Ganesh. Professor A. Nirmala is a distinguished material scientist and internationally recognized expert in energy material and sustainable energy technology. She is pioneer in lots of you can say research area like as a 2D material, graphene, carbon nanomaterial, lots of work she has done on solar cell also, in that especially on perovskite solar cell, on DSSC solar cell. She is also working on super capacitor, variable energy devices, on hydrogen production from chemistry side, CO2 reduction. So story is very long. Once again, I welcome all of you, and I like to invite Madam. And right now we have a 10 minutes talk. So before you can say 8 minutes, we just give a warning bell. Thank you, Madam. Please.
Thank you. Yeah. Thank you, sir, for the nice introduction. A very good evening to one and all. At the outset, I'd like to thank Dr. Elamagar and the entire team for having invited me over here on this wonderful occasion. So I'll be talking on solar cells and what we exactly do in our center. So our center is Center for Nanotechnology Research, where we primarily work on printed and flexible electronic devices for energy sensors and healthcare. So my research group, we work on typically on flexible electrodes, that is flexible conductive electrodes for solar cells and supercapacitors. That's what I'm going to talk in the next 10 minutes. So and where we adopt, so before, like, since there are a lot of students, like I think all of you know why DSSC, out of all the 3 generations of solar cells, DSSC dye-sensitized solar cells, it performs better because of its high energy conversion efficiency, low cost involved in the fabrication, and we do fabricate DSSC in our lab. Abundant supply of component materials, it's environmental friendly, good recyclability, fascinating colors, like you can make it based on your BAPV applications. So DSSC, as we all know, I think the process, I'll just flip through it because many of us know, it's all through the photonic process, where it has photoanodes, photocathodes, TiO2 that is anchored on anodes. It's a wide bandgap semiconductor material, and dye and electrolyte. So depending on the specialization, so myself, material chemist, like we work on photoanodes and photocathodes, like we work on the interfacial engineering aspect of how do we fabricate these photoanodes and cathodes, and we also work with organic people and inorganic chemistry people, where they give us dyes and electrolytes. Now I think I'll skip this, the working operation of DSSC. I'll just emphasize here, it all starts with a photon, where dye gets excited, then it gets transferred to the photo anode, and then it comes to the photocathode, and the whole process it goes on. And there are few dark reactions, as emphasized by our former, like previous speaker. Now, from silicon to soft electronics. So what I want to emphasize is we've been using silicon solar cells for ages, that is on rigid solar cells. So can we make it flexible? As I was mentioning, our center is primarily working on printed and flexible electronics for energy devices here. So from silicon to soft electronics, where a lot of consumer devices, like for indoor applications, wearable electronics, wearable solar panels, transparent panels, and the main challenges involved, what we are facing is that upscaling is. For example, in our lab, we are able to fabricate 10 by 10 centimeter panel, but upscaling of these module dimensions to meet the desired power requirements always remains a huge challenge, and the mechanical stability is again large scale manufacturing, and the tangible solutions for that, what we have established in our center is advanced manufacturing or additive manufacturing techniques for flexible panels using nano inks and certain amount of material engineering. So that's what today I'll be talking about. So why flexible solar cells? Lightweight, portable, as I told you, and these are the challenges and advantages which I'll be again talking. And so these are some of the manufacturing techniques like roll-to-roll processing, where we can print solar cells, like how do we print saris, stuff like that. And then a lot of printing techniques, vacuum deposition techniques, and solution processing. So the key metrics what we are adopting is that manufacturing techniques in terms of how do we manufacture these flexible solar panels, and so in that context, do we need to optimize the electronic e-inks, and the mechanical stability is yet another major factor that needs to be really taken care of, and what are the various substrates I need to really cater to. So specification of the product, this is one product that what we have developed in the lab. This is again a flexible solar cell, where for example we work on typically for materials engineering, we work on 2D materials as of now, like graphene and mexines, which is titanium carbide, ceramic based material, and we use different techniques here. For example, this is a slot-die technique. I'll be talking about that in a few slides later. So we use both roll to roll, we call it as R2R, and slot-die coating techniques for the fabrication of both photoanode and photocathodes, where these are the different parameters, and as of now 10 centimeter squared panels, lab level panels, we are able to achieve. So this is what a slot-die coater looks like, what we have in the lab, and this is a roll to roll where we fabricate these panels, which is stationed inside a clean room. This is again from Infinity PV. This is a laboratory coater, we call it as. So these are some of the, this is a photo, for example, this is a photo anode on which TiO2 has been printed, and this is again a photo cathode on which dye has been anchored, right? So this is typical photo anodes that what we have printed in our lab. So some of the state of art technology that what we have invested in our center is that this is one of the unique facility in our country, roll to roll technique, where we just like, you know, you can make like lens of solar cells once it is being optimized by slot-die coater. Can you please play the video? Yeah. So as you can see here, this is the head or the shim, we call it as, which is just like your inkjet printer, normal, you know, cartridge printer, but replaced with this, we call it as a head or shim, and here the ink is being dispensed, and it just passes across, it's printed. And also we do have a inkjet printer where so depending on the size, depending on the area of panels or solar cells what we need, we use inkjet printers, slot-die coaters, as well as roll to roll for large area coating. And now this, see for example, these are all printing ETLs, electron transport layers, and counter electrodes. Counter electrode is nothing but your photo cathodes using roll to roll, and this is, as I told you, this is again the slot-die coater where we have printed, and these are some of the solar small cell devices or cells what we have printed. And yet another area that I want to emphasize is here, apart from making the solar panel or cell or device flexible, can I also make it transparent? Because see, transparent electronics or transparent solar cells is going to be the future, where it can be directly integrated into for BAPVs, building integrated photovoltaics, or for any application where you need transparency but also you need to generate the power. So we also do work on transparent solar cells. So these are all semi-transparent solar cells where I need molecules which can absorb in the near infrared region and not in the visible region, so that it is not colored. So this is yet another area what we are working on in the area of flexible solar cells. And so this is the protocol device that what we have made. This is a very small level device, but we wanted to make sure whether this additive manufacturing technique of slot-die coating is really worth enough in trying. Then we'll take it to the next level. So, the answer was yes. So as you can see in the video, it was showing some amount of resistance for 4 by 5 centimeter square solar device panel. Yeah. So now coming to the material part, as I was telling, we want both flexible as well as we want to make it transparent or semi-transparent. So coming to the material aspect, this is one work that I wanted to discuss with you. We're working on transition metal carbides, that is nothing but mexines, where it can be easily coated. See, for example, to make it as a conductive, conductive flexible electrode. The current in the market what we have is PET, PEN or polyimide, polyethylene terephthalate, polyethylene naphthalate, which is coated on ITO. And ITO cannot be used for as such for kind of flexible applications because ITO is a rigid substrate. So ITO coated on PET, ITO coated on pen, that is what we are using. But the main problem why we have introduced these third party into the system is that pen deposited on ITO or pen deposited on PET, it faces a lot of called as bandage effect. A lot of fractures are there. So it is not mechanically stable when we are deploying it as an electrode for a solar cell. So we want to introduce a third person into the system that can bind the ITO with the conductive polymer to make the whole entire flexible substrate mechanically stable so that it can be operable for different number of cycles, when it is being tested for a solar cell. So this is one area. I'll just quickly flip through in another 3 minutes where we tried with mixins, right, with these different substrates, ITO PET, pen and PA, and these are all glass transition temperature. So we wanted to really see that which substrate is stable and flexible to make it as a solar cell, and can mixin really help in it, what is optimal thickness and how much of an improvement can we obtain from it. So I'm sorry, yeah, so this is the yeah. So see, as I told you, for all these coating process, the parameters with respect to the ink are the viscosity and the speed with which this is being printing, that is we call it as slot die coating speed, slot die coating speed, and the viscosity, ideal viscosity ranges for different techniques. See, slot die is one what we have in the lab. Apart from that, spray coating, spin coating. So depending on the area of the panel that what we need or the cell what we need, we can go for different types of printing, and these are the ideal viscosity ranges. And then the very important thing is that to make a film coated on a substrate, hydrophilicity plays a major role. So for that, we need to measure the contact angle of these substrates. So to make it hydrophilic, generally what we do is we expose these substrates or the coated substrates, whatever I had emphasized in the earlier slide, to UV ozone at these wavelengths and measure the contact angle. So for example, across all these surfaces, ITO, mixin, pen, PET and PA, as you can see here, this is without UV exposure, there is ozone exposure, and upon ozone exposure, you can see a lesser contact angle measurement for mixin. It means that, as you can see here, the contact angle is less. It means that it's a good substrate for deposition of any types of electron transport layer or hole transport layer. Thank you. Yeah, for that. So, and thin film coating of mixins again. So what we had tried is we found that mixin was really helping good enough for these substrates, to be printed. So we again see these are all iteration of various parameters that what we had tried. And finally, I'm just presenting to you only the optimized, but we do a lot of iterations, right? For example, over a width of 10 mm and 90 mm length, we had printed, and slot die parameters were kept at a constant of this is called die head speed, that is 18 mm per second. It can move across the substrate, and this is the ink flow rate 0.12 ml per minute. And to come to this conclusion, we had done a lot of iterations, and this particular recipe was kind of giving good. And also we measured the thickness of it using AFM and surface profilometer, right, for example, and these were pretty good, like there were not a lot of surface roughness. So these were good substrates. And then to make it operable for UV solar cell, and obviously I need to have the transmittance high so that radiation can pass through my substrate. So we were measuring for example, for all these 5 different substrates, the UV transmittance. So in brief, I can just, in a nutshell, I can say that with mixin coatings, the transmittance was higher. So in the sense like for ITO pen, because this with ITO pen, this was compatible compared to all other substrates. And then sheet resistance, because since it's used for solar cell, obviously you need to have a good conductivity. So in the sense, resistance should be again less. So again, the same the results were pretty good. Like for example, ITO pen had the least sheet resistance, and this is before bending and after bending. See, what I was mentioning is that it's not only about the efficiency, because see, for a rigid solar cell, I cannot compare a flexible solar cell obviously with a rigid solar cell, right? There's a win-win situation. Now should not bother about the efficiency. Can I make a flexible solar cell? Because there's no flexible solar cell in the market. So I don't bother about the efficiency, and I need to bother about whether the solar cell is stable, whether it is giving pretty good appreciable efficiency, whether it is making up the the mark, whether it is mechanically stable. And it has to then undergo a lot of mechanical stress, bending test, etc. So we had bent these substrates and found that again the sheet resistance was pretty good, least for the Mexine coated ITO pen. So what exactly the story behind all these concept is that, see, for example, in this cartoon you can see here this is the ITO pen and this is the bent what we had done, and when it is coated with Mexine, it like, like when a bone is cracked, what happens is that we do a fracturing mechanism, right? Band-aid. So this acts as a band-aids, like for example conductive bandages, which is also conductive, so that's very important. And making a conductive material to act as a band-aid, a fracturing mechanism is really pretty tough. So, but that was possible in this case, where because of this, the sheet resistance both before and after bending, it was pretty good. It was less. So, in a nutshell, these are all for different substrates what we had obtained. And I would like to conclude that ITO pen on Mexine was the good. So, this is again the optical analysis. ITO cracked under bending stress, and when Mexine acts as a bridge, you can see the morphology was kind of quite uniform, and this was a mechanism. So the core finding is that Mexine fundamentally not only used as a conductive ink, but also it helps in fracturing, it helps in healing these small cracks, so that it is mechanically stable when it is being operated as a solar cell under optimal conditions. Yeah, so with this I'll close. So my thanks to my entire research group, where my scholars Swaroop, Sivashri, Satish, Jameson, Ravi and Bharat, we are working on flexible electrodes for either for solar cells or batteries or supercapacitors, and we are trying to optimize a lot of e-inks, electronic inks, to make it operable for these devices. So thank you once again.
Thank you very much, madam, for nice talk on DSSC and flexible solar cell. Can you give mic, please? We have a sort of time, otherwise lecture is so nice, and especially on transparent as well as flexible and DSSC solar cell. Thank you, madam. Huh.
Only this much. Give a round of applause to her. Only this much. No energy.
Now our next speaker, Dr. Anita V. She is a distinguished chemist and professor in Department of Chemistry at Christ, deemed to be university, and renowned for his pioneer contribution for electrocatalysis, sustainable chemistry, and advanced functional nanomaterials. Her research has significantly advanced in innovation in electrocatalytic system for environmental remediation and the clean energy application. With over 160 Scopus Index international publications, she has made a wonderful impact on material chemistry through the research, innovation, and mentorship. She is a recipient of VGST Article Publication Award in Chemistry in 2022-23 and has been recognized among the top 25 women in chemistry in India by the Office of Principal Scientific Advisor to the Government of India. With this, I like to invite Madam.
Thank you for your kind introduction, sir. And I would like to thank CRS for honoring me with this award and giving me an opportunity to present my work. So my theme is Advanced Functional Materials as Electrocatalysts for Sustainable Future. So our research work involves electrocatalysis for sustainable future with different themes such as phytomolecules derived biosensors. We develop biointerfaces by using different phytomolecules extracted from different plant sources and we detect biomarkers, especially cancer biomarkers and other biomolecules and environmental pollutants. So we also develop electrochemical sensors for environmental pollutants and biomolecules by using 2D nanomaterials. And another area which we work on is electrocarboxylation reaction. That is nothing but carbon dioxide fixation. We use carbon dioxide to fix into organic molecules by using different materials. And another area is electro-organic synthesis, and we use different catalytic systems to convert or transform different organic molecules. And another area is carbon dioxide conversion and then electro reduction of oxides of nitrogen. See, these are the materials explored as electrocatalysts. Basically, we are using as electrode substrates the carbon fiber paper electrode. So this carbon fiber paper has high porosity and tunability and highly stable, and they are very good adsorbent. So any kind of modification when you do, so it is highly stable. And for example, if we conduct electropolymerization technique for developing conducting polymers, so these conducting polymers will be stable on this carbon fiber paper. So I will recommend this as a very good electrode substrate for electrocatalytic applications. So next is conducting polymer. As you all know, it is a very good at conductivity, and it has porosity and lot of surface functional groups, and it provides hydrogen bonding to facilitate the movement of analytes. So it is very good for sensing applications and other electrocatalytic applications. So another material which we are using is metal complexes, especially we are using it for electro-organic synthesis. Then especially this coordination polymer or metallopolymers, we are using it for electrocatalytic reduction of carbon dioxide. So here we can avoid the agglomeration of metal ions or metal nanoparticles because the metal nanoparticles exist as islands. It is surrounded by organic ligands, so it can be used for different electrocatalytic applications, especially nitrate reduction and CO2 reduction. So Maxines already madam has explained, it is a 2D material which we are effectively using. And enzymes, it was very challenging for us to develop enzyme modified electrodes. We are covalently immobilizing enzyme on the electrode surface. So that I will be explaining in the upcoming slides. So few examples I will be explaining. The first one is surface engineering of carbon fiber paper electrode through molecular imprinting technique for 4-hexyl resorcinol detection in shrimps. So this is a sensor work, but some techniques we have used to improve the selectivity. For example, 4-hexyl resorcinol is a phenol derivative with many commercial applications as food additives, especially in seafood preservation. So the development of an electrochemical sensor is of high importance. So here we are using bare carbon fiber paper electrode. This electrode is modified by using a monomer that is called the 4-aminothiazole. So this 4-aminothiazole has very good hydrogen bonding sites, and we will mix it with the 4-hexyl resorcinol, which is our analyte. So both 4-aminothiazole and this 4-hexyl resorcinol will mix together and electropolymerize on the electrode. So what is happening is we are developing a non-imprinted electrode, that is the 4-hexyl resorcinol is loaded on the electrode along with the 4-aminothiazole. So this electrode, what we are doing is we are identifying the oxidation potential of this 4-hexyl resorcinol, and through bulk electrolysis we are removing this 4-hexyl resorcinol. So after the removal of 4-hexyl resorcinol, so what is happening is in the polymer it is getting imprinted for 4-hexyl resorcinol. So this electrode will be an excellent electrode for the detection of 4-hexyl resorcinol because it has high affinity for 4-hexyl resorcinol. So it is highly selective for 4-hexyl resorcinol, and we will optimize the experimental conditions. All these details I am not giving here, and it is acting as an excellent selective sensor for 4-hexyl resorcinol. So next example is enzyme immobilized conducting polymer based biosensor for electrochemical determination of ecotoxic pollutant paranonine phenol. So this is a like ecotoxic pollutant which is used in paints, detergents, plastic dispersing agent, surfactants and wetting agents. So this is phytophobic in nature and it has poor degradation, so it is present in soil and water samples, so it is highly desirable to develop a sensor for that. So here we have used what this like enzyme. This enzyme is nothing but lacase enzyme. It is a copper based enzyme. This enzyme is very useful for the oxidation of polyphenols. So we have taken the same carbon fiber paper electrode substrate and we have electropolymerized electrode deposition of anthranic acid, that is orthoamino anthranic acid we have deposited on the electrode. So what is happening is the COH group is freely available on the surface of the electrode and we are immobilizing the enzyme on the electrode by using EDC NHS coupling, that is acid amide coupling. So the enzymes are getting immobilized on the electrode and we can use the heterogeneous electrocatalysis for the oxidation of phenol, that is paranonyl phenol. So we have successfully developed a sensor for this. So next work is on high performance beta cyclodextrin maxine for the electrochemical sensor for the detection of neurological biomarker, that is L-methionine. So it is a very important analyte. So it is sulfur containing amino acid and it has got importance in many biochemical reactions. So here the maxine is modified with beta cyclodextrin, so it provides some host guest interactions and it facilitates the movement of the analyte L-methionine and we can successfully detect that. So next work is based on the enzyme based bioelectrocatalysis for same lacase we have used for a successful conversion of D-ribonofuranose to D-ribonolactone, which is an important precursor for C-nucleoside based drug like remdesivir. So it is a COVID drug, so we have successfully transformed this one. It is an intermediate reaction in the synthesis of remdesivir. So the problem with the traditional synthesis of D-ribonolactone is it has got expensive transition metals, difficult in isolation, longer reaction time, elevated temperature, unwanted side product and toxic reagents. So what we have done is same carbon fiber paper as an electrode substrates. We have thiophene acetic acid we have used as a conducting polymer. So acid groups are free. So we have immobilized lacase enzyme on the electrode and we have this enzyme immobilized electrodes are used as an electrocatalyst for the conversion. So here we have used tembo as a mediator. So it is undergoing oxidation and oxoammonium salt is forming and this oxoammonium tembo is mediating as acting as a mediator for the conversion of ribonofuranose to ribonolactone. So another research work is based on metallopolymers as electrode modifiers. I have already mentioned that the polymer with metal centers are covalently bound or coordinately bound. It has got high tunability because we can change the metal as well as the organic ligand for different applications, especially for CO2 reduction. This is an excellent modifier and it is bridging the gap between heterogeneous and homogeneous catalysis. Easy separation of this electrode like a catalyst. We can easily separate the catalyst and we can isolate the product also. So as you all know, the carbon emission is a rising concern for us and we have to go towards the net zero carbon emission also. Like some important general scheme I have given here for CO2 utilization reaction. So carbon fiber paper electrode material we are taking, we are doing the electropolymerization along with a monomer and a metal ion so that we are getting coordination polymer on the electrode. This metallopolymer will be used for the conversion. Same electrode material, especially mixing with composites, different nano composites we are using for electrocarboxylation reaction too. So this is one example which I have prepared the coordination polymer and dimercaptothiazole and copper based material. So successfully we have synthesized, very easy to prepare, and directly we can electrode deposit on the electrode, and this electrode will be utilized for the CO2 conversion. And we found that through electrochemical analysis LSV curve, which shows that the finely modified electrode gives the maximum activity, and we have proved the product analysis has done through the NMR. And the same material we have deposited silver, and we have studied how silver is affecting the product formation, and we found that silver also will give enhance the product by synergic effect. So the last work which is we have just started, not yet reported so far. So electrochemical reduction of oxides of nitrogen. Nitrate contamination in water is global issue due to rapid progress of agriculture, industrial and serious anthropogenic activities. So what is happening is oxides of nitrogen we can convert into a very good product of ammonia, which has lot of synthetic use. So we have prepared graphite carbon nitrate, which is decorated with iron oxides, and this catalyst is used as electrocatalyst for conversion of oxides of nitrogen to ammonia. So here the graphite carbon nitride has lot of amine functional group which will suppress the side reactions of HER. That is the advantage of using graphite carbon nitride. So we have successfully synthesized ammonia, and we have taken the NMR to even isotopic labeling studies also we have done to confirm that the ammonia is synthesized only through oxides of nitrogen. So the future perspective of our work is how to scale up these reactions. Like we are synthesizing, we are developing the proof of concept, but how to scale up. So we are trying to develop electrochemical flow reactors by using all these modified electrodes to scale up the reaction. So thank you so much, and I would like to thank all my research scholars who was working towards all these electrocatalytic systems. Thank you.
Thank you, madam, for nice talk. Thank you, madam. Now we have a next Silver Star awardee, Dr. R. Mittal, scientist and head inelastic neutron scattering section, BRC, Bhabha Atomic Research Center at Mumbai. Okay. So next one, Dr. Anita Varghese. She is a distinguished chemist. Okay. Oh, sorry. One more. Shiv Kumar ji. Okay. Dr. Shiv Kumar is a distinguished material chemist and professor in Department of Chemistry, Indian Institute of Technology, Hyderabad. And he is working on luminescent material, inorganic chemistry, molecular material, optoelectronic devices. His research on lanthanum-based phosphorus, OLED material and advanced functional material has a significant advancement in lighting, because this material ultimately used to make a LED kind of devices and display technology. And alumni of IIT Madras, he has undertaken prestigious postdoctoral research at KAIST, South Korea, as well as in France, and was awarded the Professor Alfred Werner Medal for the best doctoral thesis in inorganic and analytical chemistry. With this, I like to invite sir, please. Sir, we have 10 minutes only, so I will give
5 minutes. I'll come. Yeah. Good evening, everyone. It's nice to be here. I thank the CRS President and Secretary, especially the Secretary,
So, and he has given a call to confirm that I have been awarded. It was surprise for me. So then. No, that's what he was telling. So I believe that these are the CRS doing wonderful thing because they are closely monitoring the work of the peers, how they are working. So it is very important. So because some of the researchers don't go behind their awards, so they just keep going on whatever they want to do. So it was big surprise, and thanks to the CRS for giving an opportunity. And also I thank the Saurashtra University colleagues who have taken very good initiative for making this happen. And today I'm going to talk about the proactive design and synthesis of luminescence for smart lighting. So actually this, our IIT is, only 15 years old, second generation IIT. So this is the beautiful building, first building that has been dedicated to chemical engineering. And recently in August 2022, Professor Mehta dedicated chemistry building to, chemistry faculties. This is having some unique structure where you can appreciate, we have a periodic table mimicking here. So you have, S block, D block, color glasses, then you have a P block, a gaseous state to show the transparent window, and then you have a lanthanides and actinides kept it out down here. So we have a lecture theaters are here, and our laboratories are located here, and I am sitting here in the same corridor. So this is very wonderful structure, and we supposed to be thankful to the Japanese people. We have a friendship program. We have a lot of good facility which has been dedicated. We can come sometime and enjoy research as well as the infrastructure of our thing. And in our laboratory, materials which is glow in the under UV, it can show some lights that we are interested. So starting from ceramic inorganic phosphors, nanomaterials, organic fluorophores, especially blue and red and NIR materials. Then some of the European organo-lanthanide complexes which shows different types of LEDs, which shows single component white LED, hybrid LEDs where organic molecules are conjugated with the inorganic LEDs, show the white light. And then we also work on recently room temperature phosphorescent material which can show glow few seconds. Can you go next slide? Yeah. Sorry. So this is my outline of my presentation. So we mainly work on solid state lighting. If you see the mobile phone, the front side is dedicated to OLED, organic light emitting diodes. The back side we have a kind of flash lamp, which is a inorganic LED. So we both our group work both side, front and back side, which our idea is to make a better material to sustain, to give a better efficiency. So in this contest, mainly we work on red emitting phosphor for the solid state lighting, and then TADF emitters for organic light emitting diodes. Yeah. So in introduction, if you see this photoluminescence can be explained by Jablonski diagram. Basically, the molecular system getting excited by applying UV photon that goes to the excited state and comes to the S1 state and emitting photon. The whatever may be the excitation, the emission start from S1 state, which follows the Casas rule. And then if you have a spin orbit coupling, the intersystem crossing facilitated, and you can get an emission from T1 state which called phosphorescence. The difference between the fluorescent and phosphorescence is only a time scale, which is the first one is in terms of a nanosecond, the other one is a few seconds to hours. The electroluminescence, we are interested both photoluminescence and electroluminescence. The electroluminescence, you have N and P type junction, with forward bias, which goes to the hole and electron moves. In the depletion layer, it recombine and produce light. Basically, when you move from inorganic LED to organic LED is nothing but you have two electrodes. The organic material is sandwiched between two electrodes, and when you forward bias, the electron and hole moves. And when you have these organic molecules, when you talk about molecules, you have a homo-lumo. There will be a band bending. Then electron and hole recombine and produce light in the middle organic layer. So one of the electrodes supposed to be a transparent one, so that you can get the light. So mainly the inorganic phosphor which work like the lighting consumes 15% of the world total economy, and hence if you come up with a smart lighting which can reduce the light power consumption by half due to their high efficiency. Next slide. So inorganic phosphorus is nothing but inorganic host lattice which is having activator and sensitizer. For example, in the traditional lamp, if you see the mercury lamp, you have a calcium allophosphate which is doped with antimony 3 plus and manganese 2 plus. Antimony 3 plus gives a blue light when you excite it with the mercury 254 nanometer, and then partially the energy transferred to the manganese 2 plus ion, and then you get a yellow emission from manganese 2 plus, and which combine and produce light. So that same concept has been used. Inorganic LED, that is indium gallium nitride, which is given a blue LED, and yttrium aluminum garnet, which combine will produce white light. So for that these three gentlemen have got a Nobel Prize in physics. However, this LED phosphor which has been coated on the LED which produce white light, as the lumens output is only 70 to 80% because of the lack of red color in the system. Next slide. So the red light, if you see, there are many ways one can get a red light, but in the periodic table, if you see the European 3 plus ion, which is very narrow band emission it can give, because your human eye sensitivity, if you see, the green color is very good, comfortable for your eye, but red and shallow violet and blue color is very shallow to your eye. So we need to get a narrow band emission in the red region so that it can improve the overall efficiency of the LED, as well as you can get a better color quality of your white light. And hence we have categorized this with inorganic phosphor with a charge transfer band, or because the 4 of electronic transitions are forbidden transition, you need to populate the excited state by means of having charge transfer band, or you need to push europium ion in the more europium ion in the lattice, that is your europium rich compound, or you need to use organic lantana that can populate the excited state, we can produce efficient light. Next. So next. This compound Li3Ba SrLN3, it crystallizes in the tetragonal structure, and which is basically a CaWO4 structure, that is a which has lanthanum as 8-fold coordination. So we try to replace the europium in the lanthanum side. So when you replace the europium by lanthanum, next. So you can see here we systematically moved from 0.3 to 3. So when you move from the europium ion from 0.3 to 3, there is no concentration quenching occurs. That means full the self quenching has been controlled by having this europium 3 plus ion. Next. So this can be explained by a crystallographic view, non-concentration quenching. The distance between the europium and europium, or yttrium is 3.8 angstrom in this axis, but along the C axis it is around 8.3 angstrom. That means the seeing each other, the europium ion has been restricted by having the packing of this crystal structure, and hence the concentration quenching is not been facilitated at low concentration. Next. So if you see that LED, we need to, the phosphor supposed to withstand at around 100 degrees C, because the operating temperature of LED is goes up to 100 degree. So we need to check the thermal stability of our phosphor at the photoluminescence. If you see around 125 degree, you have 87% of PL intensity has been retained. Next. So we have fabricated the LED by coating this one in the inorganic 394 LED. We got a red light, and then we also coated a organic molecule on the blue LED. We got a CRI, color rendering index of 60%. But when you add our phosphor, the color rendering index has been improved from 60 to 83 nanometer. Sorry, 83%, because the CRI is the only the percentage component. You see the object under the sunlight, which use 100%. But the same object, if you see the under the artificial lighting, how the object has been reproduced. So around 83% of the color has been reproduced under artificial lighting. So, but when you see this red light, we wanted to use this light for the plant growth application. For example, if you don't wanted to make it, so you can see that we have to widen this line. So next. So widen this line, we have coated on samarium 3 plus ion. Next. When you have the samarium 3 plus ion, you can get these additional lines with orange red emission. So we can cover full phytochrome R absorption. So that means this LED can be used for plant growth application. Next, next, next. These are the similar materials, sodium, yttrium, tungstate. Next. These also can be explained the similar way. Next, next, next. Yeah, this LED you can see around 79% of CRI we got. Next. So we have moved to cesium calcium lanthanum molybdate, which has both non-concentration quenching as well as the thermal stability. Can you go next slide? Next slide. So you can see that at around 400 degrees C, 500 K, that the PL intensity has been retained 100% normalized intensity. If you see that closely, if we watch that temperature, high temperature, X-ray from the room temperature to 450 degrees C, the structure is not been changed. That means the structure is stable up to 500 degrees C. So both thermal quenching as well as non-concentration quenching can be obtained in this. Next. So we can also fabricate white LED which has CRI of 90%. Next. We can also use them for the anti-counterfeiting application of this. Next. So to summarize this part, we can use the LED for the white light emission as well as the plant growth application, as well as we can use for anti-counterfeiting application. Yeah. Next. So next go to the molecular complexes. We can just go ahead. So this is idea is like just changing the structure. One can able to get, for example, here if you see the meta position CF3 group is there, here para position is there. If you change them, you can get white light emission from the meta CF3 and para CF3 gives pure red emission. Of course, you can also see this. It can be used for anti-counterfeiting application. If you show them HCl, it shows blue color. If you triethylamine, it shows the red color back. So these are the very similar materials. We can also use for the bioimaging application. So you can see this beauty of this. You have a butterfly shaped and triangle shape. The butterfly shape shows the white light emission, whereas the triangle shape shows the red color emission. Similarly, we also have a sulfone based compound. So this is a summary of this, and we also have some kind of organic molecules where you can get the color tunability starting from this donor carbazole to thiophenothiazine and phenoxazine. So we got with the carbazole we got a blue color, and then when you go to the this one locking and unlocking of this, we could able to improve the efficiency from 4 to 11%. And then one is showing green color, other one is showing blue color. And if you see another one, phenothiazine and phenoxazine, we got a exceeding 32%, 31% of external quantification. This is ever reported in yellow color in the literature. Yeah, so, and also recently we have got some 15% SLCT based compound, which is published in Advanced Optical Material. Okay, thank you so much for your kind attention.
So in both department, in physics also, in chemistry also, sir, we are making quantum dots, which same quantum dots are same to same property. Yes. Now next silver awardee, Dr. Sripanna Chatterjee Madam. She is a distinguished material chemist at a CSIR, Institute of Minerals and Material Technology, Bhubaneswar, recognized for her pioneer contribution to the material chemistry, surface engineering and functional material. She is doing interdisciplinary research in lots of area, and she already published 63 SCI publication. She already carried a patent also. She have a lots of technology transfer also. And one more thing, She is a DST Inspire Faculty Award also at Indian Institute of Metal, Bhubaneswar. And with this, I like to invite Madam. Thank you.
Hello? Yeah. Thank you CRS and Saurashtra University for giving this opportunity and this honor of silver medal. So I'm going to narrate a very brief story that how we have translated our research from lab to land. So as you can see, two of my previous speakers mentioned about uses of Maxine. So I'm going to tell you that how we have, translate our work from synthesis to scalable commercialization of 2D Maxine. Now, my expertise is in materials chemistry, my passion is science outreach, and very newly, my newfound love is entrepreneurship. So I have just started a startup, a deep tech startup. Now, being a materials chemist, I do synthesize materials and I study them for oncotherapeutics, clean environment, and energy efficient materials. So these are the materials you can see, like just giving you a glance of different kind of nanomaterials which I was working, and probably on some of them I'm still working since 2006. I started my research career in 2006. But in the meantime, in 2011, this Maxine was discovered by Professor Yuri Gogotsi and Michael Bursum, and like it's a 2D material. Probably you have heard about graphene, but graphene is made up of only carbon. This material is made up of Ti3C2, or like metal carbide or metal carbonitrides. So right now what we will be discussing, this is on Ti3C2. So this is the basically the chemical formula what you can see here, and this is a rough structure. Like there is a core, and on the top of that there is a surface functional group which make the Maxine material very much interesting. Now let us see why Maxine is so popular, why people are so fascinated about Maxine. So if you see, basically the energy sector is using around 28.7% of the Maxine, like electronics and many other fields. You can see optics, catalysis. And if you see, like this report, this is the report of 2013 which was published, and till 2013 there was 13,000 plus paper published on Maxine, and now this is basically 2026. So you can have like an assumption how important this material is. So in IMMT, in my institute, what we are doing with Maxine. So basically we have exploited this material, this 2D nanosheet as sensor, desalination membrane, moisture stable photoanode cathode, energy storage material, luminescent material, field emitter, and of course electrochemical transistor. Now this is the structure of Maxine. This we have synthesized in our lab. This is the TM image. Now when one starts synthesizing Maxine, that has then they have to start from its max phase. That's the precursor phase. Now this max phase is something where basically you can say that it is Ti3AlC2. From this Ti3AlC2, you have to etch the Al, aluminium layer, so that you will get the Ti3C2 kind of structure. Now this process of making max phase like Ti3AlC2 is a bit energy intensive process, because you have to make the pellet and like you have to anneal the material at high temperature and for a longer time. If you see like 1400 degrees centigrade for 2 hours, but you need to follow a very slow ramp rate when you are starting from room temperature to reach out to 1400 degrees centigrade. Now this work we have started during the COVID time, and that time actually we had we all had restrictions regarding accessing lab and everything. So my students, they were thinking that what to do, how to do. And then at the same time we also tried to figure out that like during this whole process, which is the most energy intensive or the most costly process, then we found that actually 57% of the whole process is basically going to the tube furnace part. So basically this heating part is the most energy intensive and costly process. So then what we did, we came up with a solution of flash sintering method. So just within a flash, you synthesize the material. Now, is this the flash sintering method is something unique? People didn't know that? No, it's not like that. So people who work with ceramic engineering, they use flash sintering technique to sinter their ceramic pellets. So then where we are new, what we try to do, we use that process in synthesizing our max material, okay, max phase. Now that gave us a patent, a US patent, and now it is like under PCT application, it is under examination for different country, and of course we filed the Indian patent also. So and after once we had the patent, then we had our publication in one of the most reputed journal of ceramic engineering, there is Journal of American Ceramic Society. So there are then of course we had other publications because we wanted to explore different process parameters and all, we published that. Then from our max, we synthesized magazine and we exploited them as field emitter. We also a few hours back, one of the speakers mentioned that magazine is hydrophilic. Now the problem, there are of course good part of magazine being hydrophilic, but there are bad things also. Because if your material is hydrophilic and if you are using them for the solar cell application, then your solar cell will absorb a lot of moisture, specifically when they are being used in perovskite tandem solar cell, and these perovskite solar cells are basically moisture sensitive. So we tried to make our magazine hydrophobic in nature, and we could do it efficiently. You can see the contact angle. So we started from a very low contact angle, and then we could reach to the hydrophobic level. Again, that work was published. We also exploited magazine gold nanocomposite as detector of pollutants. Then magazine derived TiO2 with nickel oxide composite. They were being used as supercapacitor application, luminescent material. And then a combination of TiO2, NiO, graphene were used for ultra-sensitive herbicide and heavy metal sensor. And you can this is published in small. So if you are interested, you can go through my Google Scholar page. You will find the publication and you can read. I think you will have very good information how we have done that. So we have also used magazine peak composite for desalination application. This work is under process. Just you can see that how nice transparent desalination members we have developed using this magazine only. And this magazine argon composite material is also exploited as a corrosion inhibitor. So you can see that this corrosion inhibition efficiency for magazine material, magazine graphene composite basically, it is around 98.2%, which is a very good result. Again, this manuscript is under preparation. This is a very interesting work. This is basically magazine RGO composite for exosome detection. Basically this we have used to exploit. I told you that I am working in the field of oncotherapeutics. So basically here we have tried to sense the difference between a benign tumor, a prostate cancer tumor, and a person who is healthy. And the accuracy is absolutely nice, very nice. And this is the sensor on PCB preparation protocol what we have followed. And after that we did, the device characterization, exosome characterization, all the sensing thing. And with the help of machine learning and all, we also did some clinical performance assessment. And finally, this paper is also published in small this year. This is a very, nice piece of work. If any of you are interested, you can go through the paper. So, what again, I'm just trying to say. So, we are continuing our research, whatever basic research we are doing, like different application, multifunctional application of magazine. But at the same time, when we got this paper, and then when we did our cost calculation and everything, then we found out that we can synthesize our own magazine at a very cost-effective way, because this flash sintering technique, it is cutting the cost of the most energy-intensive part. So from that thing, actually, we thought that. So right now what we have to do, there is one single company in Ukraine, they basically give very nice, very high quality magazine. And all the other, these Chinese people, Chinese company who are giving magazine, and some Indian company, they are just getting it from China and then reselling. Their quality of magazine is very bad. Okay, mags or magazine, whatever you say. So then why we thought that why don't we start our own venture and then let us start our own company where we can explore this kind of 2D highly, effective material. And from that, actually, the rise of Recipro Lab happened. So basically, Recipro stand for research experts or like a professional. So this is their, this is the contact of this company. Mainly it is led by one of my PhD student who is very enthusiastic. He only told that I don't want to go for a postdoc, rather I want to do my own startup, just please help me. So initially I was a bit skeptic. I thought that you have done a nice PhD with very nice papers, patents. Why don't you go for a good postdoc? But he insisted. He said that, no ma'am, you just help me. I want to start my own thing. So again, he started. Of course, I had some plan in mind, but I was a bit skeptic. So this company, they are of course selling, we are selling this Maxine, Max Phase both. And along with that, we are also working with like the other oxides like titanium, zinc oxide, and mostly they are basically customized product and all other thing they are doing. So if you want, you can just go through the web page of that company also. So this company was conceptualized in 2022. Then of course we got some funding from two, three different sources, and then we got an award, a startup award in 2024. This one is we got awarded by Chief Minister of Orissa, and right now we are at this level. So basically we are prototyping and we are doing our device integration for further validation and like B2B translation for industrial deployment. So this is the lab what we have established as a part of our company, and this is the few equipments. So it's an ongoing process. So yeah, I have one dream, but they are the doers. Most importantly, like these students, this Dibbo, Chandan, they were there as a MSc project. So after that, they have employed in our company. Kishore and Sandeep, they did their PhD in our very close IIT Bhubaneswar, so now they are our employee. And of course, the boy who started this thing, he is Dr. Usha Kiran. He graduated under my supervision. I'm very proud of him. So basically what I can tell that we couldn't do, where is that, this thing? No. So yeah, at this stage, I can't say that I am doing brain gain from abroad and all these things, but what we are trying our best that we are retaining our talent, we are trying to create impact to shape the future. Now, yes, of course, the work what I have very briefly shown, it won't have been possible because, if my collaborators were not there, because many of the things I collaborate with the other scientists for DFT calculation, for desalination and many other things. And this is the girl, Ghrutanjali, who is there right now doing PhD, and she is a very efficient one. Can you go to the next slide? Yeah. So you can go through all the papers for magazine, maybe for other materials through my Google Scholar page. Today we don't have time to interact, but if you are keen to discuss anything, just ping me in my LinkedIn. I'd be happy to discuss with you. Thank you.
Thank you, madam, for nice talk from sensor, solar cell, and at the end startup also. Basically, we have a sort of time, otherwise we like to listen to you. Now we have a last talk from PC Ravi Kumar. He is a professor in Department of Chemistry, IISER Tirupati, Andhra Pradesh. IISER Tirupati, sorry. He is postdoctoral from the two universities, one that is Yale University, USA. He is also alumni of ISC Bangalore. He is an advisor, or you can say board of member of ASC Catalyst. He is also editorial advisor board of the Journal of Organic Chemistry, as well as he also received the CRSI bronze medal in 2003 for very significant research in chemical sciences. She also get the Teaching Excellence Award. That is wonderful thing. So with this, I like to invite sir, please.
Am I audible? Yeah. First of all, I would like to thank CRS for giving me this honor and opportunity. And since there is short time availability, I'm going to talk the essence of our research. We mainly work on CH and CC bond activation. So I will give an overview of all the works that we have done and try to give you some important themes that we are working on. So as you know, carbon-carbon bond forming reactions are very important in organic synthesis. Somehow this is not visible, but that is CC bond forming reactions. As you know, carbon-carbon bond forming reactions are very important in organic chemistry. Invariably, majority of the CC bond forming reactions, if you see carefully, it involves cleavage of carbon heteroatom bond to form a new carbon-carbon bond. For example, in the case of Suzuki couplings and Stille coupling, carbon boron and carbon tin bonds are cleaved, and so on and so forth. Very rarely you will come across reactions wherein you actually cleave a carbon-carbon bond to form a new carbon-carbon bond or carbon-nitrogen bond. This is because carbon-carbon bond is inert and they are having a very high bond strength. But there are few reactions where we can actually break carbon-carbon bond to form a new carbon-carbon bond. For example, if you take donor-acceptor cyclopropane systems, upon heating it will form this dipole, and then dipole can be reacted with different dinophiles to form new carbon-carbon bonds. But the problem with this reaction is that you need to have acceptor and donor atom on the cyclopropane ring, otherwise it will not work. But this problem can be addressed by using metals. For example, metals, actually low valent metals particularly, can insert between a strained carbon-carbon bond and form a carbon-metal bond. This is very reactive. And once we form the carbon-metal bond, this can be used for various type of coupling chemistry to form new types of organic molecules. So we wanted to work on this concept and develop new reactions and new molecules. Another strained molecule, which is cyclopropanol, which also undergoes CC bond cleavage by using a slightly different mechanism called beta carbon elimination. This also gives a carbon metal bond which can also be harnessed for making variety of organic molecules. So these are the strained systems that have been heavily explored before we started our work on carbon-carbon bond activation. So we decided to work on this cyclopropenone molecule, which is not only an aromatic molecule, but it is also stable at very high temperature. So our idea is that we will take cyclopropenone and insert the metal and couple with aniline in a stepwise manner to form this imidazolone molecule. But surprisingly, we got functionalized imidazole. Since imidazoles, functionalized imidazoles are having several applications, we decided to optimize this reaction and make several substitutes, derivatives of imidazoles, melimides. And as you can see, irrespective of the substituent positions, the yields are quite good. And another important molecule that we work on in our group is cyclopropanol, and this is also a strain molecule. As I said before, cyclopropanol also opens up in the presence of metal and gives this reactive metal homoenolate, which can be harnessed for the synthesis of variety of organic molecules. I'll show you some examples. E9s are very useful functional groups present in many natural products and also molecules that show OLED properties. So we thought, but there are not many methods available for the synthesis of E9s. So we decided to develop a new synthetic route for E9s from cyclopropanol. Our idea is to open this cyclopropanol and form this metal homoenolate, which in then react with this diene to give the E9 molecules. And you can see quite a number of derivatives of E9s have been synthesized in our group, and it's working quite well. Another important synthetic intermediate in organic chemistry is 1,6-diketones. And these are the applications of 1,6-diketones. You can do Mech-Mirror coupling to form cyclic system, Pinacol coupling, macrocyclization, and aldol condensation to give systems that are present in many natural products. So we wanted to find a new method of synthesis for 1,6-diketone. So our idea is, as I said, our idea is that we will start with cyclopropanol and make a metal homoenolate in the presence of rhodium and leave it for self-coupling. So in this, in fact, we proved it, we optimized the condition, and as you can see, irrespective of the length, chain length, we can exactly position the ketones at 1,6 position. And variety of substrates undergo this reaction to give 1,6-diketones. And we are a pioneer in this area, and recently we have covered a review on this topic in ACS catalysis. And apart from CC bond activation, we are also working on CH bond activation. This is the general schematic theme diagram of CH activation. In all CH activation reactions, directing group plays a very important role. It brings the metal close to the CH bond and activates it, and then it reacts with different functional groups to get the functionalized products. So the most important thing in CH activation is the directing group. There are two kinds of directing groups: strongly coordinating directing group and weakly coordinating directing group. Strongly coordinating directing groups are often nitrogen based, and weakly coordinating groups are often oxygen based. And these are some of the strongly coordinating directing groups used in CH activation. The problem with these directing groups are they're huge, and they take additional step to install on the substrate, and then after the functionalization, removal becomes very difficult because they are connected by a CC bond. So removal, it requires very harsh conditions, or often it is not removable. So that puts a lot of limitation on its synthetic application, because you have to live with this large group along with your substrate. Whereas if you use weakly coordinating directing groups like ketones, acids, after the functionalization, you can use these groups as a functional handle for further functionalization. So in terms of application, weakly coordinating groups are better than strongly coordinating groups. That's the point I want to make. And apart from the functional groups, directing groups, if you see, majority of the CH activation has been done with heavy metals, iridium, ruthenium, and palladium, and rhodium. They are not only costly, but they are toxic as well. So if we can replace this metal with first row metals such as cobalt, we are not only reducing the cost, but we are also reducing the toxicity. So the other point that I want to make here is that CH activation by using first row transition metals are better than the heavy metals. So considering these 2 points, we can classify CH activation into 4 categories. Strong chelation with 4D, 5D metal, but that is the least sustainable approach. And then, I don't know why this is, I'll just do this here. Yeah. So, can you go forward? I hope I'll get a little time for this. Yeah. Yeah. So among all the approaches, the CH activation by using yeah. Okay. So among all the approaches, CH activation by using weak chelation and phosphor transition metal is the best approach. So we have been working on this concept for quite some time. This is a review that we covered in ChemCom, and it is one of the highly cited reviews. And this is just one or two works I will show in this area. So indole is a very common heterocycle present in many drug molecules. Particularly if you see C4 position of indole is functionalized in many of the natural products and drug molecules. But there are not many methods available for the functionalization of the C4 position at that time when we started the work. So we thought of doing our CH activation route to do the C4 functionalization. As you can see, you can do the C4 functionalization here. So these are some of the substrates that we synthesized using this approach. So I'm almost done. This is just, yeah, so these are some of the publications that we did with different substrates. And yeah, so the work that I presented is mainly done by these three students. Tanmay, she's a Humboldt Fellow in Germany, and Shyam, he joined as assistant professor in IIT Jodhpur, and Vedavyas, he is a postdoc in Scripps Research Institute with Jin Kuan Yu. And I also thank all the funding agencies for their excellent support. And finally, I would like to thank the CRS for taking this initiative and honoring and encouraging a lot of scientists across the country. And I also thank you for your kind attention. And just one few seconds I will take. I'm also editorial advisory board of Journal of Organic Chemistry, which is a very reputed journal. I encourage all of you to submit your papers to JOC. And finally, I would like to thank you all for your kind attention.
We have one more lecture from Dr. Prasanna. Previously I announced that is last, but now this one is last lecture. Sir, please.
Good evening. I thank CRS team, Professor Bag and Secretary Elmagar sir for considering me for the award, and I thank the organizers for arranging this conference in this beautiful city very nicely. So from yesterday we are enjoying the nice hospitality by the organizers. So I will not take much time. So as I am the last speaker, I will take just 5 to 8 minutes. So basically I am a bioorganic and medicinal chemist. Now I am shifting towards material science along with this work. So I will be presenting some of our work which we have carried out in designing of small molecules and their evaluation for their anti-cancer properties. So this is the outline of my talk. I will be talking about cancer statistics, and after that I will be presenting our work based on this quinozoline and benzothioazyl moieties. Okay, so as we all know, cancer is very deadly disease. When you see the statistics, so there is a chance that the number of occurrence of cancer cells, cancer cases will be increasing drastically from 22 to when we see the projection by 50, and you can see 1 in 6 deaths are globally are due to cancer. And when we okay, so we have a lot of research being done with respect to drug discovery for this cancer. So there are some limitations of conventional or existing therapies what we are practicing, like there are drug will be resistance and poor solubility, bioavailability of the drug molecules, or cost wise also we have to think. And there is a need for novel molecules and or therapeutics which enhance the efficacy and which possess the multi-target approaches. What we are nowadays seeing is the uni-targeted, like the one drug, particular drug for particular type of cancer, say lung cancer, one drug, like that. So if we have some drug molecules which can be targeted for multiple type of cancer, that will be better, and affordability cost-wise will be also a issue. So when we talk about targets to treat this cancer, we have various types of target like receptor tyrosine kinases. We have like cell cycle checkpoints. In any of the cell cycle checkpoint we can inhibit, and we have other types also. Angiogenesis, which plays very important role in case of solid tumor. So, and we have various examples for that one, and each type of target will go with separate kind of mechanism, and there are various drugs available for particular type of target. So as I told, we are working on small molecules. There are number of numerous heterocyclic molecules which are being presently used as drugs for treating cancer, and we have worked on most of the heterocyclic molecules like pyridines, pyrimidines, quinozolines, imidazoles, benzothioazoles. So most of the drug molecules, moieties, we have worked on. We have synthesized hundreds of molecules and evaluated their biological activity. When we design the drug molecule, next slide please. So next, skip. So this is one of the example which I am taking is EGFR signal transduction process which takes place in case of tumor cells, where it induces the signal transduction which leads to cell proliferation or angiogenesis or apoptosis, like that. Next. Next please. Next slide. So when you look at the strategies to inhibit this EGFR signaling, we can think of different ways. So we can inhibit that extracellular or intracellularly. So when you click please. So EGFR tyrosine kinase inhibitors which binds to the ATP binding site. Instead of ATP, it competitively binds to the tyrosine kinase and stops the signal transduction process. Next, which anti-EGFR monoclonal antibodies which binds extracellularly. Next, then anti-ligand monoclonal antibodies. Then, click please. Yeah, bispecific ligands which binds both to the receptor and the signaling. Next. Next, please. So when you see some molecule, as I told you, we are targeting for that ATP binding site. We saw the binding site and carefully observed what are the properties of the drug molecule to be there to go and bind at that ATP specific binding site. And we did the structure activity relationship and we found that some of the key factors which kind of group will facilitate that binding. And we designed some of the molecules and synthesized hundreds of molecules in this. I am presenting only few series of molecules. These are the 3 series which we have synthesized. Next, please. We do some simple chemical reactions to get novel molecules. So we synthesized several derivatives and we did anti-cancer studies using MTT, as a preliminary studies during MTT, using MTT, trypan blue exclusion and other assays. Next. Next. And we identified 3 potent molecules from those hundreds of molecules and proceed for the further studies. Next slide, please. And we wanted to know the effect of these molecules on the normal mice models. So as you can see, there is no change in the morphology of the mice when we treated the drug alone in the mice. Next. And we harvested that one and we examined the body parts. Next. We did not observe any changes in the body parts, and later that we induced the tumor to the mice model. So this is the first one is control, and these 3 are treated with our compounds, and this is the strong, standard what we have used. You can observe in the control there is a increase in the size of the mice, and there is a decrease in the size of the mice in the treated compound. Next. And you can see the variation in the body weight also. In control, body weight has increased after we started our treating our molecules on day 6. So as you can see, there is a decrease in the body weight in the treated mice group and increase in the body weight of control. Yeah, okay. So like that, we did several of studies to confirm the, so cell morphology we analyzed, and nuclear morphology using staining assays. We studied the apoptosis where it is inhibiting like that, and we studied this gene expression also. So you can see the ratio of BAX to BCL2 in this. So our treated compounds are giving good results. So like that, we did several studies. So we analyzed the body parts. We found that in our treated group mice, so they are showing the normal properties. So this is the final schematic representation of our study mechanism. And angiogenesis also, as I mentioned, in case of solid tumor, we did lot of studies to prove that they are possessing the anti-angiogenic properties which inhibits the growth of tumor. So like this, we did several moieties for these molecules. So with this, I acknowledge the support from DST and VGST of Government of Karnataka for this work, and I thank my mentors, collaborators, and I thank the organizers for giving me the opportunity.
Really nice talk on anti-cancer drug. Sir, only one question. Right now it is not time, but you are feeding the this molecule via injection or directly?
Injection. Okay, injection. Intraperitoneal injection. I'll call you back.
Thank you, sir. Ladies and gentlemen, yeah, I know that a very tired face is so many bombardments, tumors, anti-cancer drugs, organic molecules, CC bond coupling, CN bond coupling, and so on. Apart from that, there are a lot of pressures from the home or whatever, they want to go back home. And I see that the gathering is really good. You can see a lot of students sitting there, despite the fact that it is already 6:10 or something. On behalf of the organizers and the CRS, I profoundly thank all of you for your patient hearing and withstanding our sort of bombarding. Thank you very much. Thank you. We'll see you tomorrow.